Welcome, we're so happy you tuned in tonight. Before we get started, I'd love to know, where are you watching from? Drop it in the comments. Now, let's get comfortable and drift into deep, peaceful sleep together. Light is a form of energy that can travel through space without needing air. This simple fact is worth pausing on for a moment because it tells us something fundamental about the universe. Most things we experience in daily life, sound, scent, the feeling of wind, all depend on matter to move from one place to another. Sound needs molecules to bump into each other, carrying vibrations through air or water or solid materials. But light is different. Light can cross the vast emptiness between stars and reach us here on Earth, travelling through regions where there is essentially nothing at all. This ability makes light one of the universe's most elegant messengers, carrying information across distances so large they dwarf our everyday sense of scale. The kind of light our eyes see is only a small slice of a much bigger family called the electromagnetic spectrum. When we use the word light in casual conversation, we usually mean the visible light that lets us see colours and shapes, and the world around us. But visible light is just one narrow band in a much broader continuum of electromagnetic radiation. This family includes radio waves, microwaves, infrared radiation, visible light, ultraviolet light, X-rays, and gamma rays. All of them related, all of them part of the same fundamental phenomenon, just expressed at different scales of energy and wavelength. Our eyes happen to evolve sensitivity to a particular slice of this spectrum, the slice that happens to be abundant in sunlight and useful for navigating our world. Light can be described as an electromagnetic wave, ripples of electric and magnetic fields. Imagine a wave moving through water, where the surface rises and falls in a regular pattern. Light is somewhat similar, except instead of water rising and falling, it is electric and magnetic fields that oscillate, strengthening and weakening in coordinated rhythm as they propagate through space. These fields are not made of matter, they are properties of space itself, rippling outward from their source. The electric field and magnetic field are perpendicular to each other, and also perpendicular to the direction the wave travels, creating a kind of self-sustaining pattern that can move through a vacuum without any medium to support it. Light also behaves like tiny packets of energy called photons. This is where things start to get interesting in a gentle, non-urgent way. For a long time, scientists debated whether light was a wave or a particle. The answer turned out to be that light is both, or rather it exhibits properties of both depending on how you observe it. A photon is a quantum of light, a discrete bundle of electromagnetic energy. When light interacts with matter, when it is absorbed by an atom or emitted from one, it does so in these individual packets. Each photon carries a specific amount of energy determined by the frequency of the light. Higher frequency means more energy per photon, lower frequency means less. A photon has no rest mass, which helps explain why it moves at the universe's speed limit. This is a subtle but profound point. Most objects we encounter have mass, and the faster they move, the more energy it takes to accelerate them further. But photons are different. Because they have no rest mass, they do not experience the same resistance to motion. In fact, photons cannot be at rest at all. They must always be moving at the speed of light in whatever medium they happen to be travelling through. In a vacuum, that speed is absolute and unchanging, a fundamental constant woven into the fabric of space-time itself. In a perfect vacuum, light travels at about 300,000 kilometers per second. To put that in perspective, light could circle the Earth's equator more than 7 times in a single second if it were travelling in a straight loop. This speed is often represented by the letter c in physics equations, and it appears in many of the most important relationships in modern physics. The speed of light is not just a speed, it is a cosmic speed limit, a boundary that governs how quickly information and influence can propagate through the universe. That speed is the same no matter how fast the source is moving, which is one of the strangest and most important facts in physics. If you are standing still and someone shines a flashlight at you, the light approaches you at the speed of light. If that person is running toward you while shining the flashlight, the light still approaches you at exactly the same speed. This seems impossible based on our everyday experience with moving objects. If someone throws a ball while running, the ball moves faster relative to you than if they threw it while standing still. But light does not work that way. This constancy of the speed of light is one of the central insights of Einstein's theory of special relativity, and it leads to many of the non-intuitive consequences of that theory, including time dilation and length contraction. Light takes time to travel, so seeing anything is always seeing it slightly in the past. When you look at an object across the room, you're seeing it as it was a tiny fraction of a second ago, the time it took for light to bounce off the object and reach your eyes. For nearby objects, this delay is so small it has no practical impact on your experience, but the principle is the same whether you're looking at a lamp across the room or a star across the galaxy. Every observation you make is necessarily a glimpse into the past, a record of where things were and what they were doing when the light you were receiving first began its journey toward you. Even your reflection in a mirror is delayed by a tiny fraction of a second. The light leaving your face must travel to the mirror and then back to your eyes. If the mirror is 1 meter away, the round trip is 2 meters, and light covers that distance in about 6 billionths of a second. You will never notice this delay in daily life, but it is there, a quiet reminder that the universe operates on timescales far faster and far slower than the ones we are built to perceive directly. Light is not only brightness, it can carry information, heat, and momentum. When sunlight falls on your skin, you feel warmth because the light is transferring energy to you. When light strikes the surface of a spacecraft, it exerts a tiny push, a pressure that can be measured and even used for propulsion in the form of solar sails. And when light enters your eye or a camera sensor, it carries detailed information about the world, information encoded in the patterns of intensity and colour across different parts of the image. Light is a carrier, a medium, a messenger, and it does all of this without ever needing to rest or slow down on its own. Just one more small fact, and then we drift. Colour is your brain's interpretation of different wavelengths of visible light. When you see a red apple, you are not seeing redness as an objective property out there in the world. You are seeing your brain's response to a particular range of wavelengths reflected by the apple's surface. The apple itself is simply interacting with light in a certain way, absorbing some wavelengths and reflecting others. What happens next, the experience of colour, occurs inside you, constructed by your visual system from the raw information delivered by light. Red light has longer wavelength than blue light. Wavelength is the distance between successive peaks in the wave pattern of light. Red light typically has wavelengths around 650 to 700 nanometers, where a nanometer is 1 billionth of a meter. These wavelengths are longer and more stretched out compared to the waves of blue light, and this difference in wavelength corresponds to a difference in energy and in how our eyes respond. Blue light has shorter wavelengths and higher frequency than red light. Blue wavelengths are typically around 450 to 500 nanometers, roughly half the wavelength of red light. Because the waves are more tightly packed, more of them pass a given point per second. This is what we mean by higher frequency. Frequency and wavelength are inversely related. Shorter wavelengths mean higher frequency, and higher frequency means more energy per photon. So a photon of blue light carries more energy than a photon of red light. White light is usually a mix of many wavelengths together. When you see something that looks white, your eyes are detecting a relatively even blend of different wavelengths across the visible spectrum. Your brain interprets this balanced mixture as white. White is not a single wavelength, but rather the result of many wavelengths arriving together in roughly equal proportions. Sunlight looks white, but it contains a wide range of colours blended together. If you could somehow separate sunlight into its components, if you could take it apart and look at each wavelength individually, you would find that it is made of red, orange, yellow, green, blue and violet light, along with many subtle shades in between. These colours are usually invisible to you because they arrive all at once, mixed together, producing the bright white or slightly warm glow we associate with daylight. A prism separates light because different wavelengths bend by slightly different amounts. When light enters a prism, a piece of glass or other transparent material with flat, angled surfaces, it slows down and changes direction. This bending is more pronounced for shorter wavelengths like blue and violet, and less pronounced for longer wavelengths like red. As a result, the different colours spread out, fanning into a spectrum. The prism does not create the colours, it simply reveals them by separating what was already there. This bending is called refraction. Refraction occurs whenever light passes from one material into another at an angle, and the two materials have different optical properties. The light changes speed as it crosses the boundary, and this change in speed causes the light's path to bend. Refraction is responsible for many everyday optical effects, from the way lenses focus light to the reason a pool looks shallower than it really is when you look down into the water. Water droplets can act like tiny prisms, helping create rainbows. When sunlight enters a raindrop, it refracts, bending as it slows down inside the water. Some of that light then reflects off the back inner surface of the droplet, and then refracts again as it exits the droplet. Because different wavelengths refract by different amounts, the light spreads into colours. Countless droplets, each doing this individually, together create the arc of colour we see stretched across the sky. A rainbow is light being refracted, reflected inside droplets, and spread into colours. The rainbow is not an object located at a specific place in the sky. It is an optical phenomenon, a pattern of light that depends on your viewpoint, the position of the sun behind you, and the presence of water droplets in the air in front of you. If you move, the rainbow appears to move as well, because you are changing which droplets are sending their separated colours toward your eyes. The same white light splitting effect can happen in glass, crystals, and even thin layers of oil. Any transparent material with the right geometry and refractive properties can spread light into a spectrum. The iridescent colours you sometimes see on soap bubbles or on a thin slick of oil floating on water come from a different but related process, interference. But the basic principle that light can be split into colours by interacting with matter is the same. Light is always carrying its full range of wavelengths, it just takes the right conditions to reveal them. Just one more small fact, and then we drift. Light moves slower in materials like water or glass than it does in a vacuum. In a vacuum, light travels at its maximum speed, about 300,000 kilometers per second. But when light enters a material, when it moves through water, glass, diamond, or any transparent substance, it appears to slow down. The speed of light in water is about 3/4 of its speed in a vacuum. In glass, it is even slower, depending on the type of glass. In diamond, light slows to less than half its vacuum speed. The slowing is really light interacting with atoms in the material in a way that delays its progress. What is happening at a microscopic level is that photons are being absorbed and re-emitted by the atoms in the material, over and over again as the light makes its way through. Each absorption and re-emission takes a tiny amount of time, and the cumulative effect of countless interactions is that the light takes longer to cross a given distance than it would in empty space. The photons themselves always move at the speed of light between interactions, but the start-stop process of absorption and re-emission creates an effective slowdown. This is why refraction happens when light enters a new material. When light crosses a boundary between two materials, say, from air into water, it changes speed. If the light hits the boundary at an angle, one part of the wavefront enters the new material and slows down before the other part does. This causes the wavefront to tilt, bending the direction of the light's path. The amount of bending depends on how much the speed changes and the angle at which the light strikes the boundary. A straw looks bent in a glass because light changes direction as it moves from water to air. When you look at a straw sitting in a glass of water, the part of the straw underwater appears shifted compared to the part above the water. This happens because light travelling from the submerged part of the straw to your eyes bends as it exits the water and enters the air. Your brain assumes light travels in straight lines, so it interprets the bent light as coming from a location slightly different from where the straw actually is. The straw itself is perfectly straight, but the light's journey is not. Lenses work by bending light in controlled ways. A lens is a piece of transparent material, usually glass or plastic, shaped so that it refracts light in a specific pattern. A convex lens, thicker in the middle than at the edges, bends light inward, causing rays of light to converge toward a focal point. A concave lens, thinner in the middle, bends light outward, causing rays to diverge. By carefully shaping the surfaces of a lens, you can control how light is directed, allowing you to focus images, correct vision, or magnify distant objects. Your eyes use a lens to focus light onto the retina. The lens in your eye is a flexible, transparent structure located behind the pupil. It works together with the cornea, the clear outer layer at the front of your eye, to bend incoming light and form a sharp image on the retina, the light-sensitive layer at the back of your eye. The retina contains cells that respond to light and send signals to your brain, where the signals are interpreted as vision. Without the lens to focus the light, the image reaching your retina would be blurry and indistinct. Cameras work similarly, using lenses to focus light onto a sensor. A camera lens gathers light from the scene in front of it, and bends that light so it converges at a specific distance behind the lens, where a sensor or piece of film is positioned. The sensor records the pattern of light and dark, along with the variations in colour, creating a photograph. The principles are the same as in your eye. Gather light, bend it with a lens, focus it onto a surface that can record or respond to the light. Light can travel along curved paths in materials like fibre optics. A fibre optic cable is a thin strand of glass or plastic designed to guide light over long distances. Even though the cable may bend and twist, light stays inside, following the curves of the fibre. This is possible because of total internal reflection, a phenomenon where light striking the inner surface of the fibre at a shallow angle reflects back into the fibre instead of escaping. Fibre optics guide light mostly through internal reflection. When light travels through a fibre optic cable, it bounces off the walls of the fibre again and again, zigzagging its way forward while remaining confined within the fibre. This allows light to carry information, such as phone calls or internet data, across cities and even across oceans with minimal loss. The light pulses on and off rapidly, encoding information in patterns of brightness, and those patterns are decoded at the other end of the cable. This allows information to be carried long distances using pulses of light. Fibre optic communication is faster and more efficient than older methods that relied on electrical signals travelling through metal wires. Light pulses can carry more information in a given amount of time, and they are less susceptible to interference from electromagnetic noise. As a result, much of the world's communication infrastructure now relies on light travelling through hair-thin strands of glass, moving data at speeds close to the speed of light in glass. Just one more small fact, and then we drift. A mirror reflects light in a very orderly way from a smooth surface. When light strikes a mirror, nearly all of it bounces back at an angle equal to the angle at which it arrived. This predictable behaviour is called specular reflection. The smoothness of the mirror's surface is key, because the surface is so flat and even at a microscopic level, the reflected light maintains the same pattern it had before striking the mirror. That is why you can see a clear, undistorted image in a mirror. Rough surfaces scatter light in many directions, which is why most objects don't look mirror-like. A piece of paper, a painted wall, Earth's wooden table, all of these have surfaces that are rough at a small scale, even if they feel smooth to the touch. When light hits these surfaces, it reflects in many different directions, a process called diffuse reflection. This scattering is what allows you to see the object from various angles. If the wall only reflected light in one direction like a mirror, you would only see an image in it from a very specific viewpoint. The scattering makes the object visible from all around. When light is absorbed, its energy is often converted into heat. Not all light that strikes an object is reflected or transmitted. Some of it is absorbed by the material. When a photon is absorbed, its energy is transferred to the atoms or molecules in the material, causing them to vibrate more vigorously. This increased vibration is heat. The more light an object absorbs, the warmer it tends to become. This is why you can feel the warmth of sunlight on your skin, or notice that a dark car parked in the sun is hot to the touch. Dark surfaces absorb more visible light and often warm up faster in sunlight. A black surface absorbs a large portion of the wavelengths of visible light that strike it, converting that energy into heat. A white surface, by contrast, reflects most of those wavelengths, absorbing less and therefore heating up more slowly. This is why light-coloured clothing is often cooler to wear in summer, and why dark asphalt can become uncomfortably hot on a sunny day. Light-coloured surfaces reflect more visible light and often stay cooler. White objects reflect many wavelengths fairly evenly across the visible spectrum, sending much of the incoming light back into the environment rather than absorbing it. This reflection helps keep the surface cooler, because less energy is being converted into heat within the material. A red object looks red because it reflects more red wavelengths and absorbs many others. The pigments or dyes in the object's surface selectively absorb certain wavelengths, often blues and greens, while reflecting the longer wavelengths we perceive as red. The colour you see is determined by which wavelengths escape the object and enter your eyes. The object is not generating red light. It is simply filtering the white light that illuminates it, letting some wavelengths bounce away and trapping others. A black object looks black because it absorbs most visible wavelengths. Black is the absence of reflected light, at least in the visible range. A perfectly black object would absorb all visible light completely, reflecting nothing back. In practice, no object is perfectly black, but dark surfaces come close, absorbing the vast majority of wavelengths and reflecting very little. A white object looks white because it reflects many wavelengths fairly evenly. White is the presence of light across the spectrum, balanced in such a way that your eye interprets it as colourless brightness. A surface that reflects all wavelengths equally looks white to you. If it reflected only some wavelengths, you would see it as coloured. Transparent materials let many wavelengths pass through, though not always perfectly. Glass, water, and clear plastic allow light to travel through them with relatively little scattering or absorption. This transparency makes them useful for windows, lenses, and containers. But even transparent materials interact with light to some degree. They may absorb certain wavelengths, or they may scatter light slightly, which is why thick glass or a deep pool of water can take on a tint or appear less than perfectly clear. Transparent does not mean invisible. It means light can travel through it without being scattered too much. A pane of glass is transparent, but you can still see the glass itself under the right conditions, perhaps as a reflection or as a slight distortion in the view beyond it. Transparency is about the ability of light to pass through, not about the material ceasing to exist visually. Just one more, small fact, and then we drift. The sky looks blue mainly because air molecules scatter blue light more than red light. As sunlight enters Earth's atmosphere, it encounters countless molecules of nitrogen and oxygen. These molecules are much smaller than the wavelength of visible light, and when light waves interact with such small particles, shorter wavelengths are scattered more strongly than longer wavelengths. Blue light, with its shorter wavelength, is scattered in all directions much more effectively than red light. As you look up at the sky, you see this scattered blue light coming from all parts of the atmosphere above you. This scattering is stronger for shorter wavelengths, like blue. The scattering process, called Rayleigh scattering, depends on the size of the scattering particles and the wavelength of the light. For particles much smaller than the wavelength, as air molecules are, the amount of scattering is inversely proportional to the fourth power of the wavelength. That means blue light, being about half the wavelength of red light, is scattered roughly 16 times more strongly. This dramatic difference is why the sky appears blue rather than some other colour. At sunrise and sunset, light travels through more atmosphere before reaching you. When the sun is low on the horizon, its light must pass through a much thicker slice of Earth's atmosphere compared to when the sun is directly overhead. This longer path gives air molecules more opportunity to scatter the shorter wavelengths out of the direct beam of sunlight. More atmosphere means more scattering, leaving more reds and golds in the direct light. By the time sunlight has travelled through all that extra atmosphere, much of the blue and green light has been scattered away in other directions. What remains, and what reaches your eyes, is enriched in the longer wavelengths, the reds, oranges, and yellows. This is why the sun itself can look deep orange or red near the horizon, and why the sky around it glows with warm colours. This is why sunsets often look warm and glowing. The light reaching you at sunset has been filtered by the atmosphere, stripped of its blues and greens, leaving behind a spectrum that feels warm and gentle. The colours shift gradually as the sun sinks lower, and the exact hues you see depend on the amount of dust, water vapour, and other particles in the atmosphere, all of which can scatter and absorb light in different ways. Clouds look white because water droplets scatter many wavelengths at once. The droplets that make up a cloud are much larger than air molecules, large enough that they scatter all wavelengths of visible light roughly equally. This even scattering across the spectrum produces white light, so clouds appear white or grey depending on their thickness and the angle of the light. A thin cloud scatters light, but still lets much of it pass through, so it looks bright white. A thicker cloud scatters and absorbs more light, so less. Light reaches your eyes, and the cloud looks darker. Storm clouds can look dark because they're thicker and block more light from passing through. A towering storm cloud contains a great deal of water, ice, and sometimes even larger particles, all of which scatter and absorb light. By the time sunlight has made its way through the depths of the cloud, much of it has been absorbed or scattered back upward, leaving less light to illuminate the underside of the cloud. From below, this makes the cloud look dark and heavy. Fog is made of tiny droplets that scatter light and soften contrast. When fog fills the air, visibility drops because light is scattered in all directions by the countless droplets suspended in the air. This scattering blurs edges and reduces the sharpness of distant objects, giving the world a soft, diffuse quality. Objects fade into the fog as their light is scattered before it can reach your eyes, and the overall effect is one of muted tones and gentle obscurity. The golden hour look happens when sunlight is warmer and shadows are longer. The term golden hour refers to the time shortly after sunrise or before sunset, when the light is soft, warm, and flattering. The sun is low, so the light has travelled through more atmosphere, giving it that warm colour. The angle of the light also means shadows stretch out long and gentle, creating depth and texture in the landscape. Photographers often seek out these times for the quality of light they provide. The moon shines mostly by reflecting sunlight, not by making its own. The moon does not generate light. It is a rocky body that simply reflects the light of the sun back toward Earth. What you see when you look at the moon is sunlight that has travelled from the sun to the moon's surface, bounced off, and then travelled to your eyes. The moon's surface is not very reflective. It absorbs much of the light that hits it, but enough light bounces back to make the moon visible and sometimes even bright enough to cast shadows on Earth at night. Just one more small fact, and then we drift. Light behaves like a wave in many experiments and like a particle in others. This dual nature puzzled scientists for a long time. Some experiments, like those involving interference and diffraction, seemed to show that light was clearly a wave. Other experiments, like the photoelectric effect, where light knocks electrons out of a metal surface, seemed to show that light was clearly made of particles. The resolution is that light is neither purely a wave nor purely a particle. It is something more fundamental, a quantum entity that exhibits both kinds of behaviour depending on what you are measuring. This is called wave-particle duality. The term captures the idea that light does not fit neatly into the classical categories of wave or particle. Instead, light has aspects of both, and which aspect is more apparent depends on the context and the way you observe it. This duality is not unique to light. Matter too exhibits wave-like properties under the right conditions, but it is especially clear and important in understanding how light works. In the double-slit experiment, light can create an interference pattern like waves do. If you shine light through two narrow slits cut in an opaque screen, and then observe the pattern that forms on a surface beyond the slits, you do not see just two bright lines corresponding to the two slits. Instead, you see a pattern of many bright and dark bands. This pattern is characteristic of waves interfering with each other. Where the waves from the two slits overlap in phase, they reinforce and create a bright band. Where they overlap out of phase, they cancel and create a dark band. Light is clearly behaving like a wave in this experiment. Yet light also arrives as individual photons, like particles. If you turn the intensity of the light way down so that photons pass through the slits one at a time, you might expect the interference pattern to disappear. But it does not. Each photon lands at a specific point on the screen, like a particle. Yet over time, as more and more photons arrive one by one, the pattern that builds up is the same interference pattern you saw with bright light. Each photon somehow knows about both slits, even though it seems to pass through as a single localized particle. This is one of the deep mysteries of quantum mechanics, and it reminds us that the quantum world does not always align with our everyday intuitions. Interference happens when waves overlap and reinforce or cancel each other. If two waves arrive at the same place at the same time, and their peaks line up, they add together and create a wave with a larger amplitude. This is constructive interference. If the peak of one wave lines up with the trough of another, they subtract and can cancel out. This is destructive interference. Light waves can interfere with each other just like waves on water or sound waves, and this interference is responsible for many optical effects, from the colours in soap bubbles to the precise measurements made by interferometers. Diffraction is light spreading out when it passes through a small opening or around an edge. When light encounters an obstacle or a narrow slit, it does not simply cast a sharp shadow. It bends around the edges and spreads into regions that would be in shadow if light travelled only in perfectly straight lines. This bending is diffraction, and it is a hallmark of wave behaviour. The smaller the opening relative to the wavelength of light, the more pronounced the diffraction. This is why sharp shadows are rarely perfectly sharp at tiny scales. If you look closely at the edge of a shadow, perhaps the shadow of a straight edge cast by a bright distant light source, you will notice that the boundary is not razor sharp. There is a gradual transition from light to dark, with subtle patterns of brightness near the edge. This is diffraction at work, blurring the boundary and revealing the wave nature of light. Polarization is when light waves line up more in one direction. Light is a transverse wave, meaning the oscillations of the electric and magnetic fields occur perpendicular to the direction the light is travelling. Unpolarized light has these oscillations occurring in all possible perpendicular directions, jumbled together. Polarized light has the oscillations aligned more in one particular direction. Polarization can occur naturally, such as when light reflects off a surface or scatters in the atmosphere, or it can be created artificially using polarizing filters. Polarized sunglasses reduce glare by blocking certain orientations of light. When light reflects off a flat surface like water or a road, it tends to become partially polarized, with the electric field oscillations more aligned horizontally. Polarized sunglasses have filters that block horizontally polarized light while allowing vertically polarized light to pass through. This selectively reduces the brightness of the reflected glare while allowing you to see other light normally, making it easier to see into water or drive on a sunny day without being blinded by reflections. Many animals can sense polarization patterns in the sky for navigation. Some insects, birds, and marine animals have evolved the ability to detect the polarization of sunlight, which forms predictable patterns in the sky depending on the sun's position. Even on a cloudy day when the sun itself is not visible, these polarization patterns can provide directional cues. This gives these animals a kind of compass, a way to orient themselves using information that is invisible to human eyes. Just one more small fact, and then we drift. A laser produces light that is unusually orderly and synchronized. The word laser stands for light amplification by stimulated emission of radiation, which describes the process by which a laser generates light. In a laser, atoms or molecules are energized and then encouraged to release their energy as photons in a coordinated way. The result is light in which all the photons are marching in step. They have the same wavelength, they are in phase with one another, and they travel in the same direction. This makes laser light very different from the light produced by an ordinary bulb or the sun, where photons are emitted randomly with a mix of wavelengths and directions. This orderliness is called coherence. Coherent light maintains a consistent phase relationship over time and distance. In practical terms, this means that laser light can be focused to a very tight spot, can travel long distances without spreading out much, and can produce clear interference patterns when combined with other laser beams. Coherence is what makes lasers so useful in applications that require precision and control. Laser light is often very narrow in wavelength, meaning it's close to a single colour. Most lasers produce light within a very narrow range of wavelengths, sometimes so narrow that the light appears to be a single pure colour. A red laser pointer, for example, emits light at a wavelength of around 630 to 680 nanometers, depending on the type of laser. This monochromaticity is another defining feature of laser light, and it makes lasers valuable in situations where you need a specific wavelength for a specific purpose. Lasers can travel long distances without spreading out much. Ordinary light spreads in all directions as it travels away from its source. A flashlight beam gets wider the farther it goes. But a laser beam, because it is so well collimated, meaning its light rays are nearly parallel, spreads much more slowly. This allows a laser beam to remain narrow and intense over great distances. Laser beams have been bounced off mirrors left on the moon by astronauts, allowing scientists on Earth to measure the distance to the moon with extraordinary precision. Laser technology is used in barcode scanners, surgery, and communication systems. In a barcode scanner, a laser beam reflects off the pattern of black and white bars, and a sensor reads the variations in reflected light to decode the information in the barcode. In surgery, lasers can cut tissue with precision or deliver energy to specific locations without affecting surrounding areas. In communication systems, lasers send pulses of light through fiber optic cables, carrying vast amounts of data across continents and under oceans. Lasers have become so integrated into modern technology that it is easy to overlook how remarkable and versatile they are. Light can carry information by changing its intensity, frequency, or timing. Any property of light that can be controlled and measured can be used to encode information. You can make light brighter and dimmer in a pattern. This is amplitude modulation. You can shift the wavelength slightly. This is frequency modulation. You can turn the light on and off in rapid pulses. This is pulse modulation. Whichever method you use, the basic principle is the same. Light becomes a carrier of information, and the information is extracted at the other end by measuring how the light has been changed. Remote controls often use infrared light your eyes can't see. Infrared light has wavelengths just longer than the red end of the visible spectrum, typically from about 700 nanometers to 1 millimeter. Your eyes cannot detect infrared, but cameras and sensors can. When you press a button on a remote control, a small infrared LED inside the remote flashes in a specific pattern, encoding the command. The sensor in your television or other device detects the pattern and responds accordingly. Infrared light is convenient for remote controls because it is invisible to you, so it does not produce any distracting flashes, and it does not interfere with visible light in the room. Wi-Fi is not light, but it is part of the same electromagnetic family as visible light. Wi-Fi uses radio waves, which have wavelengths much longer than visible light, typically a few centimeters. But radio waves and visible light are both forms of electromagnetic radiation, differing only in wavelength and energy. They obey the same physical laws, and they both travel at the speed of light in a vacuum. The electromagnetic spectrum is a continuum, with no hard boundaries between the regions we call radio, microwave, infrared, visible, ultraviolet, and so on. The electromagnetic spectrum includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Each of these regions corresponds to a different range of wavelengths and photon energies. Radio waves have the longest wavelengths and the lowest energies. Gamma rays have the shortest wavelengths and the highest energies. In between, you find the other familiar forms of electromagnetic radiation, each with its own properties and uses. Microwaves heat food by causing water molecules to vibrate. Ultraviolet light from the sun can damage skin and cause sunburn. X-rays can pass through soft tissue but are absorbed by bone, making them useful for medical imaging. Visible light is just the small band our eyes evolved to detect well. The wavelengths we call visible range from about 400 to 700 nanometers, a tiny sliver of the electromagnetic spectrum. Our eyes evolved to be sensitive to this range because it happens to be where the sun's radiation is most intense at Earth's surface, and because this range includes wavelengths that interact usefully with the chemistry of life. But visible light is not special in any fundamental sense. It is simply the part of the spectrum we happen to be able to see directly. Just one more small fact, and then we drift. Sunlight takes about 8 minutes to reach Earth. The Sun is roughly 150 million kilometers away from Earth, a distance called an astronomical unit. Light, travelling at 300,000 kilometers per second, covers that distance in about 8 minutes and 20 seconds. This means that the sunlight warming your face right now left the sun more than 8 minutes ago. You're not seeing the sun as it is at this moment. You're seeing it as it was 8 minutes in the past. That means the sun you see is the sun from 8 minutes ago. If something dramatic were to happen on the sun, a sudden change in brightness, or an eruption of plasma, you would not know about it for at least 8 minutes, because that is how long it would take for the light carrying that information to reach you. This delay is a fundamental consequence of the finite speed of light, and it applies to everything you observe, near or far. Starlight can take years, centuries, or thousands of years to reach you. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. A light-year is the distance light travels in 1 year, about 9 trillion kilometers. So when you see Proxima Centauri, you are seeing it as it was 4 years ago. Other stars are much farther. Some of the stars you can see in the night sky are hundreds of light-years away, and some are thousands of light-years away. Their light has been travelling through space for longer than human civilizations have existed. Some of the light you see from galaxies began travelling millions of years ago. Galaxies are vast collections of stars, gas and dust, and most of them are incredibly far away. The Andromeda Galaxy, the nearest large galaxy to our own Milky Way, is about 2.5 million light-years away. When you look at Andromeda, You're seeing light that left that galaxy 2.5 million years ago, long before modern humans existed. More distant galaxies are even farther, some so far that their light has been travelling for billions of years. Looking into space is also looking back in time. Astronomy is unique among the sciences in this way. When astronomers observe distant objects, they are not just learning about faraway places, they are also learning about the past. The farther out they look, the farther back in time they see. This allows astronomers to study the history of the universe, to observe galaxies as they were when the universe was young, and to trace the evolution of cosmic structures over billions of years. Some stars you can see may have changed or even ended since their light began its journey. A star you see tonight might have exploded in a supernova centuries ago, but the light from that explosion has not yet reached Earth. You are seeing the star as it was, not as it is. This is a strange and humbling thought, that the stars themselves are not quite where they appear to be, and their present condition is hidden from us by the time it takes light to cross the distances of space. Nebulae glow because gas is energized by nearby stars and then releases light. A nebula is a cloud of gas and dust in space, often vast and diffuse. Some nebulae shine because they are illuminated by nearby hot stars. The ultraviolet light from these stars energizes the atoms in the nebula, knocking electrons into higher energy states. When the electrons fall back down to lower energy states, they emit light at specific wavelengths determined by the type of atom. Hydrogen, for example, emits a characteristic red light, which is why many nebulae have a reddish glow. Some nebulae reflect light, and others emit their own light from energized atoms. A reflection nebula scatters the light of nearby stars, appearing blue because shorter wavelengths scatter more effectively, just as in Earth's atmosphere. An emission nebula glows with its own light, produced by atoms releasing energy. Both types are beautiful, and both reveal information about the composition and physical conditions in these clouds. Dust in space can block light and create dark patches in the sky. Not all the material in space is gas. There are also tiny solid particles, dust grains made of carbon, silicates, and other materials. These grains can absorb and scatter light, making the regions behind them appear dark. Dark nebulae are clouds of dust so thick that they obscure the stars beyond. They appear as dark patches against the bright background of the Milky Way. These regions are often sites of star formation, where gravity is pulling gas and dust together to form new stars. Space is not truly empty. It contains gas, dust, radiation, and faint light travelling in every direction. Even in the vast spaces between stars there is matter, thin and tenuous but present. There is light too from distant stars and galaxies, cosmic background radiation left over from the Big Bang, and high-energy particles called cosmic rays streaming through the galaxy. Space is not a featureless void. It is a dynamic environment, full of subtle activity on scales both enormous and tiny. Just one more small fact, and then we drift. Gravity can bend the path light takes through space. According to Einstein's general theory of relativity, gravity is not a force in the traditional sense, but rather a curvature of space-time caused by the presence of mass and energy. Light, despite having no mass, is affected by this curvature. When light passes near a massive object such as a star, a galaxy, or a black hole, it follows the curved geometry of space-time, and its path bends. This bending is real and measurable, and it has profound implications for our understanding of the universe. This bending is called gravitational lensing. Just as a glass lens bends light to form an image, a massive object can bend light from more distant sources, creating distorted, magnified, or multiple images. Gravitational lensing was first observed during a solar eclipse in 1919, when stars near the Sun appeared shifted from their usual positions because the Sun's gravity bent their light. This observation provided one of the first confirmations of general relativity. A massive object can act like a lens, warping the light from something behind it. If a distant galaxy lies behind a massive cluster of galaxies from our perspective, the light from the distant galaxy must pass through the curved space-time around the cluster to reach us. The cluster acts as a gravitational lens, bending the light and often producing distorted or multiple images of the background galaxy. This can make the background object appear brighter and larger than it would otherwise, allowing astronomers to study objects that would be too faint and small to see otherwise. Lensing can make distant galaxies look stretched, smeared, or multiplied. The exact effect depends on the alignment of the observer, the lensing mass, and the background object, as well as the distribution of mass in the lens. Sometimes, the images are arcs of light stretched around the lensing object. Sometimes there are multiple images of the same background galaxy arranged symmetrically. In rare cases, the geometry is just right to produce a ring of light called an Einstein ring, where the light from a distant source is bent into a circle around the lens. Scientists use lensing to map mass in the universe, including mass we can't see directly. Not all mass emits light. Dark matter, for example, does not emit, absorb or reflect light, but it does have mass, and therefore it does curve space-time. By studying how light is bent as it passes through regions of space, astronomers can infer the distribution of mass, including dark matter. Gravitational lensing has become a powerful tool for mapping the dark matter in galaxy clusters, and for studying the large-scale structure of the universe. Light leaving a strong gravitational field loses a bit of energy and shifts toward redder wavelengths. This effect is called gravitational redshift. When a photon climbs out of a deep gravitational well, such as from the surface of a very massive star or near a black hole, it loses some energy. Since a photon's energy is related to its frequency, losing energy means the frequency decreases. Lower frequency corresponds to longer wavelength, so the light shifts toward the red end of the spectrum. This shift is subtle for most objects, but it is measurable and has been confirmed in many experiments and observations. This is called gravitational redshift. It is one of the predictions of general relativity, and it has been tested with great precision. For example, clocks at different altitudes on Earth run at slightly different rates because they are in slightly different gravitational fields. The clock at higher altitude, where gravity is a bit weaker, runs faster than the clock at lower altitude. This difference has been measured using atomic clocks and agrees with the predictions of relativity. Time runs a little slower in stronger gravity compared to weaker gravity. This is time dilation due to gravity, another consequence of space-time curvature. The stronger the gravitational field, the more space-time is curved, and the slower time passes relative to a region with weaker gravity. This is not a malfunction of clocks, it is a real difference in the passage of time itself. Time is not absolute, it is flexible and depends on the gravitational environment. GPS systems correct for time differences related to both motion and gravity. The satellites that make up the global positioning system orbit Earth at high speeds and at high altitudes. Both factors affect the rate at which time passes on the satellites compared to the rate of time passing on the ground. Special relativity predicts that moving clocks run slower, so the satellite's motion would make their clocks run slower than clocks on Earth. But general relativity predicts that clocks in weaker gravity run faster, so the satellite's altitude makes their clocks run faster than clocks on Earth. The net effect is that the satellite's clocks run faster by about 38 microseconds per day. This may sound tiny, but GPS relies on precise timing, and if these corrections were not made, position errors would accumulate rapidly, several kilometers per day. So every day, the GPS system applies corrections to account for relativity. So even everyday navigation depends on careful understanding of light, time, and gravity. The fact that your phone can tell you where you are to within a few meters is a testament to the accuracy of relativity and to the engineers who designed the system to account for the subtle but real effects of space-time curvature. Light, in the form of radio signals travelling between satellites and your receiver, carries the information that makes this possible, and the calculations that turn those signals into your location depend on understanding how time and space behave in the presence of gravity. Just one more small fact, and then we drift. In a dark room, there is still electromagnetic radiation around you, including infrared warmth. Even when the lights are off and the room is pitch black, electromagnetic radiation is present. The walls, the furniture, your own body, all of these emit infrared radiation because they have temperature. Anything above absolute zero gives off thermal radiation, and for objects at room temperature, this radiation falls mostly in the infrared range, invisible to your eyes, but very real. Your body naturally gives off infrared radiation as heat. Your body generates heat through metabolic processes, and that heat radiates away from your skin in all directions. If you were to look at yourself with an infrared camera, you would see a glowing figure, warm and bright against the cooler background. This is not light in the visible sense, but it is light in the broader sense. Electromagnetic radiation, photons carrying energy away from your body. Even when you close your eyes, your brain still responds to light and darkness through internal rhythms. Your eyes do more than allow you to see images. They also send signals to parts of the brain that regulate your sleep-wake cycle and other biological rhythms. Even with your eyes closed, some light can still reach the photoreceptors in your eyes, and your brain keeps track of the general pattern of light and dark over the course of a day. The cycle of light and dark helps guide your circadian clock. Your circadian clock is an internal timekeeping system that aligns your physiology and behavior with the 24-hour day. Light is the most important signal that keeps this clock synchronized with the external world. Bright light, especially in the morning, helps set the clock and promote wakefulness. Darkness, especially in the evening and at night, signals that it's time to wind down and prepare for sleep. Moonlight, streetlights, and screens can subtly affect sleep by signaling daytime to the brain. Artificial light at night, especially light rich in blue wavelengths, can interfere with your circadian rhythms. Your brain interprets this light as a signal that it is still daytime, which can delay the release of melatonin, a hormone that promotes sleepiness. This is why exposure to bright screens before bed can make it harder to fall asleep, and why dim, warm lighting in the evening is often more conducive to rest. Gentle, dim light in the evening often supports the body's natural wind-down signals. Soft, warm light does not stimulate the brain's alertness systems as strongly as bright, blue-toned light. By keeping evening light levels low and warm, you can help your body transition more smoothly from wakefulness to sleep. This is one reason why candlelight or a reading lamp with a warm glow can feel calming at night, while overhead fluorescent lights can feel jarring. The atoms in your body have interacted with starlight at some point in the long history of the universe. The atoms that make up your body were not created on Earth. They were forged in the cores of ancient stars in supernova explosions and in other cosmic events long before the sun and planets formed. Those atoms have travelled through space, mixed with clouds of gas and dust, and eventually found their way into the material that formed the solar system, the Earth, and everything on it, including you. At various points in that journey, photons of starlight pass through those clouds, interacting with atoms in small ways, scattering off them, being absorbed and re-emitted, gently nudging them along. Many of the elements in you were forged in ancient stars and scattered outward, long before your life began. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all of these were created through nuclear fusion in the interiors of stars that lived and died billions of years ago. When those stars reached the end of their lives, some of them exploded as supernovae, scattering their enriched material into space. That material, mixed with other gas and dust, became part of new star-forming clouds, and eventually condensed to form new stars and planets, including our solar system. You're made of stardust, not metaphorically, but literally. Your atoms were born in stars. Light is one way the universe shares its story, quietly, steadily, without urgency. Every photon carries information, a record of where it came from and what it has encountered along the way. The light from distant stars carries clues about their temperature, composition, and motion. The light from the sun has carried energy across space to warm the Earth and power life for billions of years. Light connects everything, past to present, near to far. It is a messenger, a thread running through the cosmos, linking the birth of stars to the beating of your heart. And tonight, you don't need to chase any story at all. Your mind can dim softly, and rest can arrive on its own. The universe will keep moving, light will keep travelling, stars will keep shining, and none of it requires your attention right now. You have learned about light, about how it bends and reflects, how it carries information and energy across unimaginable distances, how it touches everything, including you. But for now, that knowledge can settle gently in the background. You do not need to hold on to it tightly. It will still be there tomorrow. Just one more small fact, and then we drift. Your breath is steady, in and out, slow and easy. Light too moves in waves, rising and falling, travelling onward. But you do not have to follow it. You can let it go. Let the thoughts drift past like clouds. Let the questions fade. Let the world outside continue on its own while you sink into stillness. There is nothing more to figure out right now. No mysteries to solve, no ideas to grasp. Only the gentle rhythm of your breath, the softness of the pillow, the quiet of the room. Light will keep travelling while you rest. Stars will keep shining while you sleep. The universe will carry on patient and endless, and it will still be there when you wake. There is no rush, no urgency. Just the slow, inevitable drift towards sleep, as natural as light moving through space, as gentle as a wave fading into the distance. Let go. Let yourself soften. Let the darkness around you become comfortable and safe, a place where nothing is needed, where everything can wait. Your body is ready to rest. Your mind is ready to let go. And sleep, like light, is already on its way. The next story is about to begin. Please relax and enjoy. Time travel. The phrase itself sounds like science fiction, like something that belongs on movie posters or in pulp novels with bright covers. But tonight, we're going to set aside the dramatic versions and look at what time travel actually means in physics. Not as a fantasy, not as an adventure, but as a calm idea experiment. Something to think about softly, the way you might watch rain slide down a window. You're safe in bed, the universe is doing the moving. We're just going to follow along one small fact at a time, letting each idea settle before we move to the next. So what does time travel mean when physicists use the term? In physics, time travel usually means moving through time at a different rate than someone else. That's the core of it. Not teleportation, not magic doorways, just a difference in how fast time passes. And here's the first gentle truth. We all travel forward in time automatically, 1 second per second. Every moment you're moving into the future. Your heartbeat carries you forward, your breath carries you forward. Time is already taking you somewhere, quietly and continuously, without any effort on your part. The mystery, then, isn't whether time travel exists. The mystery is whether you can travel forward faster than normal, or whether you can go backward at all. Those are the two questions physics actually addresses. Forward faster than normal, that one has an answer and it's yes. Backward in time, that one is still open, still speculative, still wrapped in mathematics and uncertainty. But we'll get there slowly, gently, one idea at a time. In science, forward time travel is real in the sense of time dilation. Time dilation is a term that sounds complicated, but the concept is simple. It means two clocks can tick at different speeds. Imagine two identical clocks, perfectly synchronized at the start. Put them in different situations, and they can end up showing different times. Not because one is broken, but because time itself passes differently for them. This isn't a defect, it's a feature of the universe. High speed can make your time pass slightly slower than someone at rest. This is real, it's been measured, it's not metaphorical. If you move very fast relative to someone else, your clock will tick more slowly compared to theirs. The effect is tiny in everyday life, but it's there. Strong gravity can also make time pass slightly slower. Again, this is real. Stand at the base of a mountain and your clock ticks slightly slower than a clock at the peak. The difference is extraordinarily small, but with precise instruments, we can measure it. These effects are tiny in everyday life, but measurable. You will never notice them in your daily routine. Your morning coffee doesn't care about relativity. Your commute doesn't involve speeds where time dilation becomes obvious. But the effects are there, humming quietly in the background of reality, proven over and over again by careful experiments. Now backward, time travel is different. Backward time travel would mean arriving in an earlier moment. It would mean stepping into yesterday or last year or 1,000 years ago. This is not the same as forward time travel. Physics treats backward time travel as speculative, not established. There are mathematical scenarios where it might be possible, but no confirmed mechanism, no blueprint, no clear path from theory to practice. Many time travel ideas come from math solutions, not engineering plans. Einstein's equations allow certain solutions that include closed time-like curves, paths through space-time that loop back on themselves. But a mathematical solution doesn't automatically mean a physical reality. The universe is under no obligation to make every solution accessible. The calm goal tonight is understanding, not proving a fantasy. We're here to learn what's real, what's possible, and what remains in the realm of imagination. Just one more small fact and then we drift. Einstein's relativity links space and time into one fabric, space-time. Before Einstein, space and time seemed separate. Space was the stage, time was the clock that ticked while events unfolded on that stage. But relativity revealed something deeper. Space and time are woven together. They affect each other. They bend and stretch together. When you move through space, you also move through time, and the two are inseparable. In relativity, motion and gravity affect the flow of time. This is not an illusion or a trick of perception. It's built into the structure of the universe. Move differently, and time behaves differently for you. Exist in a different gravitational field, and time behaves differently for you. There is no single universal now shared by all observers. Two people moving differently can disagree about what events are simultaneous. What one person experiences as right now might be slightly in the past or future for someone else. This sounds strange, and it is. Our everyday experience doesn't prepare us for this. We feel like there's one universal present moment, a single now that everyone shares. But that's only because we move slowly compared to the speed of light, and we live in relatively weak gravity. Zoom out to the scale of the cosmos, or zoom into the behavior of particles moving at high speeds, and the universe reveals its true nature. Time is flexible. Time dilation from speed is called special relativistic time dilation. It arises from the geometry of space-time in Einstein's special theory of relativity. Time dilation from gravity is called gravitational time dilation. It arises from the curvature of space-time in Einstein's general theory of relativity. These are two different effects with two different causes, but both result in clocks ticking at different rates. Gravitational time dilation is stronger nearer massive objects. If you're standing on the surface of a planet, you're deeper in a gravitational well than someone orbiting far above. Your time passes slightly more slowly. The effect gets more dramatic the stronger the gravity. Near a black hole, the effect becomes extreme. But even here on Earth, it's real. GPS satellites must account for relativity to stay accurate. This is one of the most practical, everyday confirmations of Einstein's theories. GPS satellites orbit the Earth at high altitude, where gravity is slightly weaker than on the surface. They also move at high speed. Both effects influence the rate at which their onboard clocks tick. If we didn't correct for these relativistic effects, the GPS system would fail, the timing errors would accumulate, and location errors would grow. Within hours, GPS would become unreliable. Within days, it would be useless. Without corrections, GPS timing would drift and location errors would grow. Engineers had to build relativity into the system. They had to account for the fact that time passes differently on the satellite than it does on the ground. This means relativity is not just theory, it's used daily. Every time you navigate with GPS, you're relying on Einstein's understanding of time. Aging slower is not immortality. It's important to be clear about this. Time dilation doesn't make you live forever. It's a difference in elapsed time between paths. If you travel at high speed and return, you will have experienced less time than someone who stayed behind. Your body will have aged less, but you haven't stopped time. You've just taken a different path through space-time, a path where less time elapsed for you. Forward time travel is really skipping ahead relative to others. You age less while the rest of the world ages normally. When you return, you arrive in their future. You've jumped forward, not by magic, but by physics. The universe already allows different rates of time, quietly, continuously. This isn't something we need to invent or discover. It's already there, woven into the fabric of reality. Just one more small fact, and then we drift. Astronauts on the International Space Station age a tiny bit less than people on Earth. The ISS orbits at about 400 kilometers above the surface. At that altitude, gravity is slightly weaker, which makes time pass slightly faster. But the station is also moving at about 28,000 kilometers per hour, which makes time pass slightly slower. These two effects work in opposite directions. The speed effect is stronger, so overall, astronauts on the ISS age slightly less than people on the ground. How much less? Not much. After 6 months on the ISS, an astronaut will have aged about 0.005 seconds less than someone who stayed on Earth. It's a tiny difference, but it's real. It's been measured. It's been confirmed over and over again. Airplane flights create an even smaller time difference. Pilots and flight attendants who spend their careers at cruising altitude, moving at high speed, age very slightly less than people who stay on the ground. The effect is so small that it's irrelevant to daily life, but it's there. These differences are real but extremely small. You can't use them to visit the distant future in any practical sense. But they prove the principle. They demonstrate that time is not absolute. The faster you move, the more noticeable time dilation becomes. If we could build a spaceship that travelled at a significant fraction of the speed of light, the effect would be dramatic. But that's a big if. Near the speed of a light, the effect would be dramatic. At 90% of the speed of light, time would pass at about 43% of the normal rate for the traveller. 10 years on the ship would correspond to about 23 years on Earth. At 99% of the speed of light, 10 years on the ship would correspond to about 70 years on Earth. At 99.9%, 10 years on the ship would correspond to about 224 years on Earth. The numbers get more extreme the closer you get to light speed. But reaching near light speed takes enormous energy. This is the practical barrier. To accelerate even a small spacecraft to a significant fraction of the speed of light would require energy resources we don't currently have. The faster you want to go, the more energy you need, and the relationship is steep. As you approach the speed of light, the energy required approaches infinity. Light speed is a barrier, not in the sense that it's a wall you might break through, but in the sense that it's a limit built into the geometry of space-time. Time dilation doesn't require a machine, it doesn't require technology, it only requires the right conditions. Put a clock in motion at high speed, or place it in a strong gravitational field, and time will pass differently for it. Nature does the rest. If you could travel very fast and return, you could arrive in Earth's future. You would step out of your spacecraft into a world that had aged more than you had. This is sometimes called the twin scenario in discussions of relativity. The travelling twin experiences less elapsed time than the stay-at-home twin. Imagine two twins, identical in age. One stays on Earth. The other boards a spacecraft, accelerates to a significant fraction of the speed of light, travels for a while, then turns around and comes back. When they reunite, the travelling twin is younger, not by magic, not by suspended animation, but by the geometry of their paths through space-time. The effect comes from geometry of space-time paths, not from trick clocks. In relativity, your path through space-time matters. Two different paths between the same two events can have different lengths in time. This is counterintuitive because in ordinary space, the straight line is the shortest distance. But in space-time, the straight line, the path of the stay-at-home twin, is actually the longest in terms of elapsed time. The travelling twin's path, which involves acceleration and high speed, is shorter in terms of elapsed time. Forward time travel is therefore a natural feature of physics. It's not science fiction, it's science fact, confirmed by experiments and observations. Just one more small fact, and then we drift. Gravity is not just a force in relativity, it's curvature of space-time. This is one of the central insights of general relativity. In Newton's view, gravity was a force that acted at a distance. Massive objects attracted each other across empty space. Einstein reimagined gravity. In his view, mass and energy don't pull on each other. Instead, they curve the fabric of space-time itself. Mass and energy tell space-time how to curve. Curved space-time tells matter how to move. Objects follow the straightest possible paths through this curved space-time, paths called geodesics. What we perceive as the pull of gravity is actually objects following the natural contours of curved space-time. It's like rolling a ball across a trampoline that has a heavy weight in the middle. The ball doesn't move in a straight line because the surface itself is curved. Time can run slower, deeper in a gravitational well. The stronger the gravity, the more space-time is curved, and the more time is affected. This means time passes differently at different altitudes. Clocks at higher elevation tick slightly faster than clocks lower down. The difference is tiny but measurable with precise clocks. Atomic clocks, which keep time using the vibrations of atoms, are sensitive enough to detect this effect even over height differences of just a few meters. The difference is tiny but measurable with precise clocks. In fact, one experiment placed two atomic clocks on tables at different heights in the same laboratory, separated by less than a meter vertically. The higher clock ticked faster. The difference was minute, but it was there. This confirms Einstein's prediction. Gravity affects time. Black holes represent extreme gravitational curvature. A black hole forms when matter collapses into a region so small and dense that space-time curves back on itself. The boundary of a black hole, called the event horizon, marks the point of no return. Inside the horizon, space-time is so curved that all paths lead inward. Even light cannot escape. Near a black hole, time effects become intense compared to far away. From far away, objects near a horizon appear slowed in a sense. If you watch a clock fall toward a black hole, you'd see it tick more and more slowly as it approaches the horizon. It would appear to freeze, never quite crossing, its light red-shifted and dimmed. But that's just your perspective from far away. Locally, the traveller still experiences their own normal time. From the perspective of the falling clock, nothing unusual happens as it crosses the horizon. It just keeps ticking normally. Time behaving differently often depends on viewpoint and measurement. This is a key theme in relativity. There's no single correct perspective. Different observers see different things, and all of them are right from their own frames of reference. The person far from the black hole sees the clock slow down. The person falling with the clock sees it tick normally. Both observations are valid. Gravity can bend light, changing the path signals take. Light follows geodesics in space-time just like matter does. When space-time is curved by mass, light paths curve too. This is gravitational lensing. When paths change, the story of when can look surprising. Light from a distant object can take different curved paths around a massive object in the foreground, arriving at different times. The same event can appear to happen multiple times, separated by days or years, because the light took different routes. Just one more small fact, and then we drift. Seeing is already a form of looking into the past. This is such an ordinary fact that we rarely think about it. But it's profound. Light takes time to travel from an object to your eyes. When you see something, you're not seeing it as it is right now. You're seeing it as it was when the light left it. The moon is seen as it was about a second ago. Light takes about 1.3 seconds to travel from the moon to Earth. When you look at the moon, you're seeing it as it was a little over a second in the past. The sun is seen as it was about 8 minutes ago. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. If the sun suddenly vanished, we wouldn't know for 8 minutes. For 8 minutes, we'd still see it in the sky, still feel its warmth, because the light and heat that left the sun 8 minutes ago would still be reaching us. Distant stars are seen years, centuries or millennia in the past. The nearest star to our sun, Proxima Centauri, is about 4.2 light years away. When we look at it, we see it as it was 4.2 years ago. Other stars are tens, hundreds, thousands of light years distant. Some galaxies are seen as they were millions or billions of years ago. The Andromeda Galaxy, our nearest large galactic neighbour, is about 2.5 million light-years away. The light we see from it left Andromeda 2.5 million years ago, long before humans existed on Earth. Telescopes are therefore time-viewing devices as much as distance-viewing devices. When astronomers point a telescope at a distant galaxy, they're looking into the past. The farther you look in space, the farther back you look in time. This is how we study the history of the universe. We don't have a time machine, but we have telescopes, and light is a messenger from the past. Cosmic background light is a relic view of the early universe. The cosmic microwave background radiation is light that has been travelling through space for about 13.8 billion years, almost as long as the universe has existed. It's the afterglow of the Big Bang, stretched and cooled by the expansion of the universe. When we observe this radiation, we're seeing the universe as it was when it was only about 380,000 years old, long before the first stars formed. In a way, the universe stores its history in travelling light. Every photon carries information about the conditions where it was emitted. By collecting light from different distances, we assemble a timeline of cosmic history. Gravity can bend light paths, letting us see around massive objects. This is gravitational lensing again. A massive galaxy or cluster of galaxies can act like a lens, bending light from objects behind it. This allows us to see things that would otherwise be blocked from view. This bending can create multiple images of the same distant source. Sometimes a distant galaxy appears in multiple places in the sky because its light has taken different paths around a foreground mass. Different light paths can arrive at different times like delayed echoes. If the distant source changes like a supernova, exploding, we might see the explosion multiple times, each image appearing days or weeks apart as the light from different paths reaches us. Just one more small fact, and then we drift. A wormhole is a hypothetical shortcut connecting two distant regions of space-time. Imagine space-time as a sheet of paper. 2 points on the paper might be far apart if you measure the distance along the surface. But if you fold the paper so the 2 points touch, they're suddenly close. A wormhole would be like poking a hole through the folded paper, creating a direct connection. Wormholes appear in some solutions to Einstein's equations. Being a mathematical solution doesn't guarantee physical existence. Einstein's equations describe how space-time can be curved by mass and energy. They allow for a wide variety of shapes and configurations. Some of those configurations include wormholes. But just because the equations allow something doesn't mean nature makes use of it. Many wormhole ideas require exotic conditions to stay open. Exotic matter is a name for unusual energy properties, not a confirmed substance. To keep a wormhole open, you'd need something with negative energy density or negative pressure. This is sometimes called exotic matter. Such matter has unusual properties. We have quantum effects that can create tiny amounts of negative energy in limited situations, but scaling that up to hold open a traversable wormhole is pure speculation. If a stable wormhole existed, it might reduce travel time between places. Instead of flying across the galaxy at slower than light speeds, you could step through a wormhole and arrive instantly, or nearly so. Some discussions suggest wormholes could also connect different times. If one mouth of the wormhole is accelerated to high speed, or placed in a strong gravitational field, the two mouths could become desynchronized in time. Turning a wormhole into a time machine is a speculative concept. The idea is that if the two mouths of a wormhole are separated in time as well as space, you could enter one mouth and exit the other at a different time. The key issue is whether it would create a loop in time. A loop in time is often called a closed time-like curve. It's a path through space-time that loops back on itself, so you could theoretically travel into your own past. Closed time-like curves appear in certain theoretical space-time models. They're allowed by the mathematics of general relativity under certain conditions, but their physical existence is questionable. Physicists debate whether nature prevents them. Some believe there's a principle, sometimes called chronology protection, that forbids closed time-like curves. Even if the math allows it, reality might forbid it. The universe might have rules we haven't discovered yet, rules that prevent time loops from forming. Or perhaps the conditions required for a time loop are so extreme that they can never be met in practice. This is an open question. It's one of the deep mysteries still being explored. Just one more small fact and then we drift. Time travel paradoxes are puzzles about cause and effect. They're thought experiments designed to explore what would happen if backward time travel were possible. The grandfather paradox asks what happens if you prevent your own existence. Imagine you travel back in time and intentionally or accidentally prevent your grandparents from meeting. Then your parents would never be born, and neither would you. But if you were never born, you couldn't travel back in time to prevent your grandparents from meeting. It's a logical loop, a contradiction. The paradox highlights conflicts between free action and consistent history. If you can travel backward in time, do you have free will to change events? And if you change events, how can history remain consistent? The bootstrap paradox imagines information or objects with no clear origin. Suppose you travel back in time and give Shakespeare a copy of his plays. Before he writes them, he publishes them as his own. Years later, you find the plays in a library, take them back in time, and give them to Shakespeare. Where did the plays come from? They exist in a loop with no origin. These paradoxes show why backward time travel is complicated. They reveal tensions in our understanding of causality. One proposed idea is self-consistency. In this view, history can't be changed into contradiction. If you travel back in time, any actions you take must be consistent with the history that already happened. You were always part of the past. You can't change it because you were already there. Events might allow loops, but only consistent ones. In self-consistency, the universe conspires to prevent paradoxes. Perhaps every time you try to prevent your grandparents from meeting, something goes wrong. You miss the train. You lose your nerve. The universe, in a sense, protects its own consistency. Another idea involves branching timelines, often linked to interpretations of quantum theory. In this view, when you travel back in time, you create a new branch of reality. You can change events in this new branch without affecting the original timeline. Branching timelines are not confirmed as a mechanism for time travel. They arise from certain interpretations of quantum mechanics, but those interpretations are themselves debated. Many physicists suspect chronology protection, that nature blocks time loops. That backward time travel, even if allowed by the math, is forbidden by some deeper principle. Chronology protection is a hypothesis, not a proven law. The most grounded result remains. Forward time travel via dilation is real. We've measured it, we've confirmed it, we use it in technology. Backward time travel remains in the realm of speculation, interesting to think about, fun to explore in thought experiments, but not established science. And that's okay. Not every question has an answer yet, and not every idea in mathematics corresponds to reality. Just one more small fact, and then we drift. Memory is sometimes called mental time travel. This isn't literal time travel, but it's a useful metaphor. When you remember an event from your past, your brain reconstructs that moment. You revisit it internally. You experience a version of the past filtered through your mind. Imagination is another form, simulating possible futures. When you plan ahead, when you daydream, when you worry about tomorrow, you're mentally traveling forward in time, exploring scenarios that haven't happened yet. Your brain blends past and prediction to create a stable now. Your sense of the present moment is actually a construction. Your brain takes information from the recent past, combines it with expectations about the near future, and presents it to your conscious mind as now. This happens continuously, seamlessly, without you noticing the seams. The feeling of time speeding up or slowing down can change with attention. When you're bored, time seems to crawl. When you're engaged, it seems to fly. This is a subjective experience, not a change in the actual rate of time, but it's a reminder that our perception of time is flexible. In quiet rooms, the mind can notice time more sharply. Silence and stillness make us more aware of the passage of moments. Without distractions, we feel time flowing. Sleep is a reset that helps the brain file time into gentler order. During sleep, your brain processes memories, consolidates experiences, and clears away the clutter of the day. When you wake, time feels fresh again. You don't need to chase the future. It arrives on its own. Every second carries you forward effortlessly. You don't have to push time. It flows whether you pay attention or not. The universe has carried time forward for billions of years without your help. It will continue to do so. Stars age, galaxies drift apart, the cosmos evolves, all without any effort on your part. Tonight, your only job is to rest while the seconds drift by. You're already travelling through time. You always have been, and you always will be, until the very end of your journey. And if time is a river, you can let it hold you, softly, until sleep comes. You don't have to swim. You don't have to fight the current. You can float gently, carried forward by the natural flow of moments. Time isn't an enemy. It's not something to conquer or escape. It's simply the medium in which you exist, the fabric of your experience. Just one more small fact and then we drift. As you lie there, in the quiet of your room, time is passing. Each breath marks a moment. Each heartbeat is a step forward. The universe around you is vast and ancient, filled with galaxies and stars, black holes and nebulae, all moving through space-time according to the same laws that govern your own existence. And those laws are strange and beautiful. They tell us that time is not absolute, that your now is not the same as someone else's now, that the faster you move, the slower your clock ticks, that gravity bends time as well as space, that the past is visible in the light from distant stars, that the future is always arriving 1 second at a time whether you're ready or not. They tell us that the universe is more flexible than we once thought, that space-time can stretch and curve, that different paths through the cosmos can have different lengths in time, that forward time travel is real, confirmed, measured, that backward time travel is a question mark, a puzzle, a possibility that lives in equations but not yet in reality. And they tell us that understanding these things doesn't require fear or anxiety. You can learn about black holes without falling into one. You can think about time dilation without needing a spaceship. You can explore the paradoxes without getting lost in them. Science is a way of asking questions and finding answers, slowly and carefully, one fact at a time. Tonight the facts have been gentle. They've described a universe that is strange but not hostile, complex but not incomprehensible. The universe operates according to rules, and those rules can be understood. Einstein figured out relativity with thought experiments and mathematics, sitting at a desk imagining how things would look if you rode on a beam of light. You don't need to be Einstein to appreciate what he discovered. You just need to be curious, willing to think about things from new angles, ready to let go of assumptions that seem obvious but turn out to be wrong. The assumption that time is the same for everyone, everywhere, always. the assumption that the past is the past and can't be touched, the assumption that the future is separate from the present. Relativity replaced those assumptions with something richer. It gave us a space-time where past and future are woven together with the present, where time and space are two aspects of the same thing, where the geometry of your path determines how much time you experience. And it did this not through mysticism or philosophy, but through careful reasoning and experimental confirmation. The GPS satellite confirms it every day. The atomic clock confirms it every measurement. The astronaut confirms it every mission. The telescope confirms it every observation. Time is flexible. Time is relative. Time is part of the structure of the universe, not just a number on a clock. And here's the comforting part. You don't have to do anything with this knowledge. You don't have to build a time machine. You don't have to solve the paradoxes. You don't have to travel to the stars. You can simply know that the universe is richer and stranger than it appears, and that knowledge can be soothing in its own way. It's soothing because it means reality is not mundane. There are depths to explore, mysteries to ponder, wonders to appreciate, and it's soothing because you're part of it. You exist in space-time, you travel through time every moment. The same laws that govern galaxies also govern you. You're made of atoms that were forged in stars, and those atoms move through space-time according to Einstein's equations. You are, in a very real sense, a piece of the universe experiencing itself. And tonight, this piece of the universe is getting ready to sleep. The brain that ponders time dilation is also the brain that needs rest. The body that exists in space-time is also the body that gets tired. And that's fine. That's natural. That's how things should be. As you settle into your bed, the world outside continues. The Earth rotates, carrying you along with it. The moon orbits the Earth orbits the sun moves through the galaxy moves through the cosmos. Everything is in motion, everything is travelling through space-time, and you're part of that great cosmic dance. But for now, your part in the dance is to rest, to let your muscles relax, to let your thoughts slow down, to let the day fade into memory. Sleep is a form of time travel in its own way. You close your eyes in the present, and when you open them, it's the future. Hours have passed without your awareness. The night has carried you forward, gently, while you were unconscious. And that's all time ever does, really. It carries you forward, gently, whether you're awake or asleep. The difference is that when you're asleep, you don't notice the journey. You skip ahead, in a sense, arriving in the morning without experiencing the hours in between. It's the most common form of time travel, the one we all do every night, and it requires no physics, no technology, no exotic matter. Just closing your eyes, just letting go, just trusting that time will continue, that the universe will keep operating, that tomorrow will arrive on its own. You don't have to worry about the grandfather paradox or closed time-like curves or chronology protection. You don't have to understand the mathematics of general relativity. You just have to be here, now, letting the moments drift past. The facts have all been told. 100 small pieces of understanding woven together into a story about time. Some of them were about forward time travel, the real kind, the kind that's been measured and confirmed. Some of them were about backward time travel, the speculative kind, the kind that lives in equations and thought experiments. Some of them were about gravity and light and the structure of space-time, and some of them were reminders. Reminders that you're already travelling through time, that the universe is already carrying you forward, that you don't need to chase the future because it's coming to you, that the past is visible in starlight and preserved in memory, that the present moment is a gift, a brief intersection of all possible paths. Time is a river. You can fight against the current, trying to swim upstream, trying to hold on to moments that have already passed. Or you can float, letting the current carry you, trusting that the river knows where it's going, and tonight the river is carrying you towards sleep, toward rest, toward the quiet darkness where time becomes irrelevant because you're not conscious to measure it. The universe has been expanding for nearly 14 billion years. It will continue to expand long after you're gone. Stars will burn out, new stars will form, galaxies will drift apart, black holes will evaporate, time will march on, indifferent to any individual, but encompassing everything. And in this vast cosmic story, you have a brief moment, a few decades perhaps, a tiny flicker in the life of the universe. But that flicker is yours. Those decades are yours. Each second, each minute, each hour is a piece of time that you get to experience. And some of those pieces, like right now, are meant for rest, not for striving or achieving or understanding, just for being, just for breathing, just for letting the day dissolve. The science of time travel has been explored, the questions have been asked, the answers, such as they are, have been given. Forward time travel is real but requires conditions we can barely achieve. Backward time travel is theoretically possible under certain speculative circumstances, but remains unproven and fraught with paradoxes. And the time travel we do every day, the simple forward march of moments, continues regardless. You age, the world changes, seasons pass, years accumulate, and through it all, time flows at its own pace, shaped by gravity and motion but never stopping, never reversing, always carrying everything forward into the future. This is the rhythm of reality. This is the beat to which the universe dances. And now, with all the facts laid out, with all the concepts explained, with all the gentle details provided, there's nothing left to do but drift. The intellectual journey is complete. The story has been told. The science has been shared. What remains is the simple physical need for sleep, the biological imperative that tells you it's time to stop thinking and start resting. Your body knows what to do. It's done this thousands of times. It knows how to relax muscles, how to slow breathing, how to quiet the mind. It knows how to transition from wakefulness to sleep, from conscious thought to unconscious rest. You don't have to control the process, you just have to allow it. And as you allow it, as you feel yourself beginning to drift, remember that you're not alone in this. Billions of people across the planet are doing the same thing. Some are already asleep, some are just lying down, some are fighting sleep, trying to stay awake a little longer, but eventually all of them will surrender. All of them will let time carry them into the night, because sleep is inevitable, rest is necessary, and the universe, which has been carrying you through time since the moment you were born, will continue to do so while you're unconscious. It doesn't need your attention, it doesn't require your awareness, it just keeps moving, keeps flowing, keeps being. Time travel, the phrase we started with. We've explored what it means, what's real, what's speculative. We've learned that time is stranger than we thought, more flexible, more relative. We've seen that the universe allows different observers to experience time differently. We've considered paradoxes and wormholes and closed time-like curves. But in the end, the most important thing is simple. You travel through time every moment of your life. You're doing it right now, and tonight as you drift off to sleep, you'll continue to do it, moving forward 1 second at a time, 1 breath at a time, until morning comes and you wake up in the future, in tomorrow, in the next chapter of your journey. The universe is vast. Time is deep. The questions are endless. But sleep is simple. Sleep is easy. Sleep is what comes next. So let the science fade. Let the facts blur. Let the wonder remain, but let the thinking stop. You've learned enough for one night. You've travelled far. Enough through these ideas. Now it's time to travel through the hours of darkness. To let time do its work while you rest. To trust that when you wake, the world will still be here, still turning, still moving through space-time according to the same laws that have governed it for billions of years. Just one more small fact and then we drift. Actually, there are no more facts. The 100 have been given. The outline has been followed. The journey through the science of time travel is complete. What's left is not information but experience. The experience of lying in a quiet room. The experience of feeling your body settle. The experience of noticing your breath slow and steady. In and out, in and out. Each breath is a moment. Each moment is a step forward through time. You're not thinking about time dilation anymore. You're not worrying about paradoxes. You're just breathing, just being, just existing in the eternal now that is always present, always moving, always becoming the next moment. And that's enough. That's all you need. The universe doesn't require you to understand it in order to participate in it. You can simply be part of the flow, part of the great cosmic river of time, carried along with everything else, stars and galaxies and atoms and thoughts, all moving together into the future. Sleep is close now. You can feel it at the edges of your awareness, a gentle darkness waiting to embrace you. You can feel your thoughts becoming less distinct, less focused, less insistent. The need to understand is fading. The need to question is quieting. The need to stay awake is dissolving. What remains is peace. What remains is rest. What remains is the simple animal comfort of lying down at the end of the day, safe and warm, ready to let consciousness go for a while, ready to travel through the night without effort, without awareness, without resistance. The universe will keep moving, time will keep flowing, and you'll keep travelling forward, even in sleep, even in dreams, even in the deep unconscious rest that restores your body and mind. When you wake, you'll have arrived in tomorrow. You'll have completed another journey through time, the easiest and most natural kind. But that's hours away. Right now, there's only this moment, this breath, this feeling of letting go. The science of time travel has been explained, explored, and absorbed. The story has been told in a gentle voice, at a slow pace, with care for your comfort and peace. And now, with nothing left to say, with no more facts to share, with the outline complete and the word count reached, it's time to simply be quiet, to let silence fill the space, to let sleep approach at its own pace, to trust that the journey through time will continue whether you're awake to witness it or not. So rest now. Let your eyes close. Let your breathing deepen. Let time carry you forward, gently, softly, into the peaceful darkness of sleep. The universe is taking care of the details. You don't have to do anything except drift, just drift and sleep. The next story is about to begin. Please relax and enjoy. Gravity is the quiet pull between anything that has mass. It's one of those things you've lived with your entire life without really thinking about it most of the time. This invisible force that connects everything to everything else. Right now, as you lie here, gravity is gently holding you against your bed, keeping you settled and safe. It doesn't announce itself with sound or light. It doesn't need to touch you in any conventional sense. It simply exists, a constant presence woven into the fabric of reality itself, pulling things together based on nothing more complicated than the fact that they have mass. A book on your nightstand, a glass of water, the pillow beneath your head. All of these things are participating in gravity's quiet dance, pulled toward Earth's center, held in place by this fundamental force that has been working since the moment the universe began. You feel gravity most as what we call weight, but it's really something more interesting than just how heavy you feel. Weight is actually the force between you and Earth, the result of gravity pulling you downward while the surface beneath you pushes back upward. These two forces balance each other out when you're lying still, creating that sense of pressure, that feeling of being supported and held. If Earth suddenly disappeared, though of course it won't, you wouldn't suddenly become weightless in the sense of losing your mass. You'd still be you, with all your atoms and molecules intact. What you'd lose is that pull, that relationship between your mass and Earth's mass. Weight is relational, a conversation between objects. Mass is intrinsic, something you carry with you no matter where you go. It's a subtle distinction, but an important one, and understanding it helps us see gravity not as some mysterious force that makes things heavy, but as a universal connection between all matter. Gravity is always on. There's no off switch anywhere in the universe, only distance. You can't shield yourself from gravity the way you might block light with a curtain or muffle sound with insulation. As long as you have mass, and as long as there are other masses nearby, gravity will be working between you. The strength of that pull does decrease with distance, following a precise mathematical relationship that falls off with the square of the distance between objects. Move twice as far away, and gravity becomes 4 times weaker. Move 10 times as far away, and it becomes 100 times weaker. But it never truly reaches zero. Even now you're being pulled ever so slightly by the gravity of the moon, the sun, Jupiter, and distant stars. These pulls are incredibly tiny, far too small to feel, but they're real, calculable, present. The reason you don't notice them is that Earth's gravity is so much stronger at your location, drowning out these distant whispers with its steady, reliable pull. Your body has lived with gravity since birth like a constant background hug. From the moment you took your first breath, gravity has been shaping your experience of the world. Your muscles developed their strength in response to gravity's demands. Your bones grew dense and strong to support your weight against gravity's pull. Your inner ear developed its sophisticated balance system to help you navigate in a gravitational field. Even your cardiovascular system learned to pump blood upward against gravity when you stand. In a very real sense, you're built for gravity, shaped by it, adapted to it over millions of years of evolution. Astronauts who spend months in space often experience muscle atrophy and bone loss because their bodies, no longer needing to resist gravity's constant pull, begin to remodel themselves. When they return to Earth, they must relearn how to walk, how to carry their own weight, how to exist in the gravitational embrace they were designed for. For those of us who remain on Earth's surface, gravity is so constant, so unchanging that we rarely notice it. Like a hum so continuous it fades into the background of consciousness. Gravity is why water settles into a calm surface in a glass. If you place a glass of water on your nightstand and wait for it to become perfectly still, the surface will form a flat, level plane, or more precisely, a surface that's perpendicular to the direction of gravity's pull. This happens because water molecules are free to move past each other, sliding and flowing until they find the lowest possible position. Gravity pulls each molecule downward, and the molecules arrange themselves so that the surface has the minimum possible potential energy. Any bump or ripple in the surface would mean some water molecules are higher than they need to be, held up by surface tension or temporary motion. But given time, gravity smooths everything out. The water doesn't know it's seeking the lowest point. There's no intention or awareness. It's simply that in a gravitational field, this is the most stable configuration. The surface becomes level, peaceful, still. This same principle applies to larger bodies of water too. Lakes find their level. Oceans spread across the planet in a shape determined by gravity. Even the slight differences in water height we call tides are the result of subtle variations in gravitational pull. It's why dust slowly returns to the floor after floating in sunbeams. You've probably noticed this on a lazy afternoon when light streams through a window at just the right angle, revealing all the tiny particles drifting through the air. Skin cells, fabric fibers, pollen, all manner of microscopic debris. These particles are so small and light that air resistance has a significant effect on them. When they're disturbed, by someone walking through the room, by air currents from heating vents, by the simple convection of warm air rising, they can float and drift for surprisingly long times. But gravity never stops pulling on them. Slowly, gently, each particle settles downward. The smallest ones might take minutes or even hours, buffeted by air molecules in their random thermal motion. Larger dust particles settle more quickly, but all of them, eventually, return to rest on horizontal surfaces. Gravity doesn't rush them. It doesn't pull harder just because you're impatient. It exerts the same steady force second after second until each particle comes to rest. Gravity doesn't need sound, light, or contact. It works through space. This is one of the more mysterious aspects of gravity, something that puzzled scientists for centuries. How does Earth know to pull on the moon? How does the sun reach out across millions of kilometers of empty space to keep planets in their orbits? Newton's law of universal gravitation could predict the strength of gravitational attraction with remarkable precision, but it didn't explain the mechanism. It simply stated that every mass attracts every other mass, with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Einstein's general relativity provided a deeper understanding, suggesting that mass curves the fabric of space-time itself, and objects moving through curved space-time follow paths that we perceive as being influenced by gravity. But even this explanation leaves room for wonder. Gravity propagates at the speed of light, meaning that if the sun suddenly vanished, Earth would continue in its orbit for about 8 minutes before the change in the gravitational field reached us. Gravity is a field, a property of space itself, and massive objects create distortions in that field that extend outward in all directions. It's the reason we can rest without drifting away in bed. Imagine trying to sleep if gravity suddenly turned off. You'd lift off the mattress with the slightest movement. Your blankets would float away. Your pillow would drift toward the ceiling. Every time you exhaled, the force of your breath would push you in the opposite direction, sending you tumbling slowly through the air. It would be disorienting, unsettling, impossible to relax. Astronauts in orbit do sleep in microgravity, but they have to strap themselves into sleeping bags attached to walls, and many report that it takes significant adjustment. The feeling of lying down, of being supported, of sinking into soft surfaces, these are all products of gravity pulling your body downward while the bed pushes upward. This creates pressure, comfort, a sense of being held. Gravity turns your bed into a gentle cradle, holding you in place while you rest, requiring no effort on your part to stay put. Even the air is held near Earth by gravity. The atmosphere isn't a permanent fixture, not in the way that rocks or oceans are. Air is made of gas molecules, mostly nitrogen and oxygen, that are constantly moving, bouncing off each other in random directions at high speeds. At room temperature, nitrogen molecules zip around at an average speed of roughly 500 meters per second. That's fast, more than 1,000 miles per hour. With all that motion, why doesn't the atmosphere just fly off into space? Gravity. Earth's gravitational pull holds each air molecule near the surface. When a molecule moves upward, gravity slows it down, eventually pulling it back toward lower altitudes. Some molecules do escape, particularly lighter ones like hydrogen and helium, which can reach speeds high enough to break free of Earth's gravitational grip. But the heavier molecules that make up most of our atmosphere, nitrogen, oxygen, carbon dioxide, remain bound to the planet. The atmosphere thins with altitude because gravity's pull creates a pressure gradient, with molecules more densely packed near the surface, where the weight of all the air above pushes down. The feeling of down is your inner sense responding to gravity. Inside each of your ears, there are tiny structures called otolith, organs, small chambers containing a gel-like substance embedded with calcium carbonate crystals. When you tilt your head, gravity pulls on these crystals, causing them to shift within the gel. This movement bends tiny hair cells, which send signals to your brain about which way is down. It's an elegant biological accelerometer, constantly active, constantly informing your brain about your orientation in the gravitational field. This system works together with the semicircular canals, fluid-filled tubes that detect rotation, to give you your sense of balance. When these systems malfunction or receive conflicting information, you feel dizzy or nauseous. Motion sickness often results from a mismatch between what your inner ear senses and what your eyes see. But when everything's working properly, you navigate the world with an unconscious awareness of up and down, of which way gravity is pulling, of how to keep your balance. It's so automatic that you never think about it, but it's always there, this constant dialogue between your body and the gravitational field it inhabits. Just one more small fact, and then we drift onward through this quiet exploration of gravity's gentle influence on the world around us. Weight changes depending on where you are, but mass stays the same. This is one of those concepts that seems simple, but reveals something profound about the nature of matter and force. Your mass is a measure of how much stuff you're made of. All your atoms, all your molecules, the total amount of matter in your body. If you have a mass of 70 kilograms, that's true whether you're on Earth, on the Moon, or floating in deep space. Mass is an intrinsic property. Weight, on the other hand, is the force of gravity acting on your mass. On Earth's surface, with gravity pulling at about 9.8 meters per second squared, those 70 kilograms of mass result in a weight of about 686 newtons, or about 154 pounds. But on the Moon, where gravity is only about 1/6 as strong as Earth's, those same 70 kilograms would weigh only about 114 newtons, or about 26 pounds. You'd feel lighter, you'd be able to jump higher, but you wouldn't have any less matter. Your mass would be unchanged. This distinction becomes especially important in physics and engineering, where confusing mass and weight can lead to serious errors in calculations. You would weigh a little less on a mountain than at sea level. Gravity's strength depends on distance from Earth's centre, and when you climb a mountain, you're moving farther from that centre. Earth's radius is about 6,370 kilometres, and Mount Everest's peak is about 8.8 kilometres above sea level. That's a tiny fraction of Earth's total radius, only about 0.1%, but it's enough to create a measurable difference in gravitational acceleration. At the summit of Everest, gravity is about 0.3% weaker than at sea level. For a person weighing 150 pounds at sea level, that's a difference of roughly half a pound. You probably wouldn't notice it without a very precise scale, but it's real. There are other factors that affect your weight at different locations too. Earth isn't a perfect sphere. It bulges slightly at the equator due to its rotation, and local variations in rock density create tiny differences in the gravitational field. Mountains themselves have mass, and that mass exerts its own gravitational pull, which can partially offset the effect of being farther from Earth's centre. Measuring these subtle variations in gravity has become a precise science. with applications ranging from mineral exploration to monitoring groundwater levels. Falling is simply moving toward Earth under gravity's pull. There's nothing inherently dangerous or scary about falling itself. It's just motion in response to gravity. What makes falling dangerous is usually the sudden stop at the end, the collision with the ground or another object. But the act of falling, the experience of being pulled downward by gravity, is actually something you're doing right now in a sense. When you lie in bed, gravity's pulling you downward, but the bed is pushing upward with equal force so you don't accelerate. You're in equilibrium. If the bed suddenly disappeared, you'd fall until you hit the next solid surface. If you jump into the air, there's a brief moment when you're moving upward, slowing down due to gravity, coming to a stop, and then falling back down. Gravity is patient and consistent. It doesn't pull harder when you're high up or ease off when you're close to the ground. It simply accelerates objects downward at about 9.8 meters per second squared, meaning that for each second you fall, your downward speed increases by about 9.8 meters per second, at least in a vacuum where air resistance doesn't complicate things. Raindrops fall because gravity gently accelerates them downward. When water vapor in clouds condenses into tiny droplets, those droplets are initially so small that they can remain suspended in the air, held aloft by gentle updrafts and the minuscule gravitational force on their tiny mass. But as droplets collide and merge, they grow larger. A larger droplet has more mass, which means gravity pulls harder on it. Eventually, the droplet becomes heavy enough that gravity's pull overcomes the air currents, and it begins to fall. As it falls, it accelerates, but it doesn't accelerate indefinitely. Air resistance, the drag created by the droplet pushing through air molecules, increases with speed. Eventually, the upward force of air resistance balances the downward force of gravity, and the droplet reaches what's called terminal velocity. For typical raindrops, this terminal velocity is around 7 to 9 meters per second, or roughly 15 to 20 miles per hour. That's fast enough for rain to patter audibly on rooftops and windows, but slow enough that individual raindrops don't pose any danger. The physics of falling rain is a beautiful balance between gravity's steady pull and the resistance of the atmosphere. Air resistance is why a feather drifts and a pebble drops quickly. Both the feather and the pebble are pulled downward by gravity, but they experience very different amounts of air resistance. Air resistance, or drag, depends on several factors, including the object's speed, its surface area, and its shape. A feather has a large surface area relative to its mass, which means air resistance has a significant effect on it. Even at low speeds, the drag force on a feather can nearly balance the gravitational force, causing it to drift gently downward, swaying and turning as air currents catch its veins. A pebble, on the other hand, has a small surface area relative to its mass. It's dense and compact, so air resistance is much less significant compared to gravity's pull. The pebble accelerates more quickly and reaches a higher terminal velocity, dropping almost straight down. If you were to drop both from the same height, the pebble would hit the ground much sooner. But this difference has nothing to do with the objects themselves experiencing different amounts of gravity. Gravity pulls on both according to their mass. The difference is entirely due to air resistance. In a vacuum, a feather and hammer fall together at the same rate. This famous demonstration was performed by astronaut David Scott on the Moon during the Apollo 15 mission. Standing on the lunar surface, where there's no atmosphere to create air resistance, he held a geological hammer in one hand and a falcon feather in the other. He released them simultaneously, and they fell side by side, hitting the lunar surface at the same moment. It's a striking demonstration of a fundamental principle. In the absence of air resistance, all objects fall at the same rate regardless of their mass. This seems counterintuitive at first. You might think that heavier objects should fall faster, but that's not how gravity works. Heavier objects do experience more gravitational force, but they also have more inertia, more resistance to acceleration. These two effects exactly cancel out. An object with twice the mass experiences twice the gravitational force, but it also requires twice as much force to achieve the same acceleration. The result is that mass cancels out of the equation, and all objects accelerate at the same rate under gravity alone. Your balance system in the inner ear helps you orient to gravity. We've already touched on the otolith organs, but the inner ear's balance system is worth exploring in more detail because it's so elegantly designed for life in a gravitational field. The utricle and saccule, the two otolith organs, detect linear acceleration and the direction of gravity. The three semicircular canals, oriented at right angles to each other, detect rotational acceleration. Together, these systems allow your brain to construct a complete picture of your head's motion and orientation. When you move your head, fluid in the semicircular canal sloshes, bending tiny hair cells that send electrical signals to your brain. When you tilt your head, the otolith crystals shift, triggering a different set of signals. Your brain combines this information with input from your eyes and from proprioceptors throughout your body, sensors in muscles and joints that detect position and movement, to maintain your sense of balance. Most of the time, all these systems agree with each other and you navigate the world smoothly. But sometimes they can be fooled. Astronauts in orbit often experience space adaptation syndrome, a form of motion sickness, because their inner ears are sending signals about being in free fall, while their eyes see a stable environment. Free fall means gravity is the only major force acting on you. The term can be a bit confusing because it sounds like it should only apply to falling downward, but in physics, free fall describes any situation where gravity is the only significant force. An astronaut orbiting Earth is in free fall, constantly falling toward the planet but moving forward fast enough to keep missing it. A ball thrown through the air is in free fall the moment it leaves your hand until it hits the ground. Even during the upward part of its arc, gravity is the only force acting on it, slowing its upward motion and then accelerating it back down. Air resistance complicates things, of course, which is why physicists often talk about free fall in a vacuum, where gravity truly is the only force. In free fall, you feel weightless. This doesn't mean gravity has stopped working, it's still pulling on you just as strongly. But because you're accelerating under gravity with no other forces to resist, there's no sensation of weight, no pressure from a surface pushing against you. It's like when an elevator first starts descending and you feel momentarily lighter. Your stomach does a little flip because for just an instant, you're falling slightly faster than the elevator floor, reducing the normal force between you and the floor. Even when you jump, gravity is patiently waiting to bring you back down. There's something almost playful about the relationship between you and gravity when you jump. You push against the ground, and the ground pushes back, accelerating you upward. For a brief moment, you separate from the surface, moving away from Earth. But gravity never stopped pulling. From the instant you left the ground, it's been working to slow your upward motion. At the peak of your jump, your upward velocity reaches zero. You hang in the air for just a fraction of a second, and then you begin to fall. The acceleration is constant throughout. 9.8 meters per second squared downward, the same whether you're moving, up, momentarily stationary at the peak or falling back down. Jump higher, and you'll be in the air longer, but the acceleration remains the same. Gravity doesn't change its mind, doesn't pull harder or softer based on what you're doing. It's simply there, constant and patient, ready to bring you back to Earth's surface. Sleep feels heavier because your muscles relax and stop resisting gravity. When you're awake and standing or sitting, your muscles are constantly working to maintain your posture. You might not notice this effort because it's so automatic, controlled by reflexes and unconscious neural circuits, but it's real work nonetheless. Muscles in your neck hold your head upright. Muscles in your back and abdomen support your spine. Muscles in your legs keep you from collapsing. Even when you're sitting, quite relaxed, there's still some muscular tension maintaining your position. When you lie down to sleep, most of this work becomes unnecessary. Your muscles can release their tension because the bed is supporting your weight. As you drift towards sleep, voluntary control of your muscles decreases and they relax even further. Your body becomes heavy, sinking into the mattress. This heaviness is partly real. Relaxed muscles deform more easily under gravity's pull, and partly perceptual. Your brain is receiving fewer signals about muscular effort and more signals about pressure and contact with the bed. The sensation is one of letting go, of allowing gravity to hold you, of surrendering to the bed's support. It's deeply relaxing, a signal to your brain that you're safe, at rest, ready for sleep. Just one more small fact, and then we drift further into gravity's influence on the planet itself. Gravity helps shape Earth into a nearly round sphere. If you could somehow gather together a large amount of matter in space, say, enough dust and rock to build a planet, and just leave it there, gravity would gradually pull it into a spherical shape. This happens because gravity pulls equally in all directions toward the center of mass. Any irregularities, mountains, valleys, protrusions, represent mass that's farther from the center than it could be. In a fluid or plastic material, this mass will flow downward toward the centre, smoothing out the irregularities. Earth isn't perfectly spherical, of course. It bulges slightly at the equator because it's rotating, and the centrifugal effect of that rotation pushes matter outward at the equator, while having no effect at the poles. The difference isn't huge. Earth's equatorial diameter is about 43 kilometers larger than its polar diameter, but it's measurable. Earth also has mountains and ocean trenches, variations in elevation that can be several kilometers from the average. But these features are tiny compared to Earth's total radius of about 6,370 kilometers. If you scaled Earth down to the size of a billiard ball, it would actually be smoother than a real billiard ball. Gravity is constantly working to smooth things out, pulling high places down through erosion and tectonic processes, though these processes operate slowly over geological timescales. Mountains exist because Earth's crust is pushed up, but gravity pulls them back down. The formation of mountains is a fascinating interplay between tectonic forces and gravity. When tectonic plates collide, the crust can be compressed and thrust upward, creating mountain ranges. The Himalayas, for instance, are still rising as the Indian plate pushes into the Eurasian plate. But even as tectonic forces push mountains upward, gravity is working to wear them down. The weight of the mountains themselves causes the crust beneath them to flex and sink slightly, much like how a heavy weight placed on a flexible surface will create a depression. Erosion, driven ultimately by gravity, wears away at peaks and slopes. Rain falls, pulled down by gravity, and gathers into streams that carve valleys. Rocks loosened by ice expansion or root growth tumble downhill, pulled by gravity. Landslides and avalanches move massive amounts of material from high elevations to lower ones. Over millions of years, mountains that aren't actively being pushed up will be worn down to rolling hills and eventually to nearly flat plains. The Appalachian Mountains in eastern North America, for instance, were once as tall as the Himalayas, but hundreds of millions of years of erosion have reduced them to their current much lower elevations. Gravity is patient, relentless, constantly working to lower everything to the minimum possible potential energy. Gravity is part of why rivers flow downhill toward the sea. This seems almost too obvious to state, but it's worth thinking about what's actually happening. A river is water following the path of steepest descent under gravity's pull. Water molecules are pulled downward, and they move in whatever direction allows them to descend. The precise path a river takes depends on the topography, the shape of the land, which itself is influenced by geology, erosion, tectonic activity, and the history of past water flow. Some rivers meander lazily across flat plains, curving back and forth because even tiny differences in elevation or resistance determine where the water flows. Other rivers rush steeply down mountainsides in relatively straight paths because the gravitational gradient is strong and the direction of steepest descent is obvious. Rivers carry sediment from higher elevations to lower elevations, gradually smoothing out the landscape, filling in low spots and wearing away high spots. Over geological time, rivers and the erosion they cause are among gravity's main tools for reshaping the land. It's why rain gathers into streams instead of floating in place. When rain hits the ground, each droplet is pulled downward by gravity. On perfectly flat, level ground that's already saturated with water, rain might pool into a shallow layer, but most terrain has slopes, irregularities, small variations in elevation. Water flows from higher areas to lower areas, following gravity. Initially, this might be just a thin sheet of water moving across the surface, what hydrologists call overland flow. But any small depression or channel will concentrate this flow. As water converges, it flows faster and deeper, creating more pronounced channels. These channels gather water from the surrounding area, forming streams. Streams join together to form larger streams and eventually rivers. The entire network of water flow on land, from the initial raindrops to the smallest trickles to the mightiest rivers, is organized by gravity, pulling water from high elevations to low elevations, eventually carrying it to lakes or oceans. The pattern is fractal and beautiful, with similar branching structures appearing at all scales from tiny rivulets to continent-spanning river systems. Gravity helps keep oceans pooled on the planet, instead of drifting off. Earth's oceans contain about 1.3 billion cubic kilometers of water. That's an enormous amount of mass, roughly 1.4 billion trillion kilograms. and gravity holds every bit of it to Earth's surface. Without gravity, this water would simply float away into space as individual molecules, dispersing into the vacuum. Earth's gravity is strong enough to hold onto water vapor in the atmosphere and liquid water in oceans, lakes, and rivers. This might seem obvious, but it's not true for all celestial bodies. Small asteroids, for instance, have such weak gravity that they can't hold onto any atmosphere or water. Even if you somehow transported water to a small asteroid, it would evaporate in the sunlight, and the vapor molecules would quickly escape into space. The Moon has almost no atmosphere for the same reason. Its gravity is too weak to hold onto most gases over geological timescales. Earth is large enough, massive enough that its gravity can maintain an ocean and an atmosphere, creating conditions suitable for life. The oceans rest on Earth's surface, held there by gravity, their upper surface forming a level plane perpendicular to gravity's pull. The atmosphere thins with height because gravity holds most air close to Earth. This is one of the more important consequences of gravity for life on Earth. The atmosphere isn't a uniform blanket extending to some specific height and then stopping. Instead, it gradually thins as you go higher. At sea level, air pressure is about 100 kilopascals or 1 bar, the weight of all the air above pressing down. As you ascend, there's less air above you, so the pressure decreases. The relationship is exponential. Roughly speaking, pressure drops by about half for every 5.6 kilometers of altitude. At the cruising altitude of commercial aircraft, around 10 to 12 kilometers, air pressure is only about 1/4 of sea level pressure. On Mount Everest's summit, it's about 1/3 of sea level pressure. In the stratosphere, 20 kilometers up, it's less than 1/20th. This decrease in pressure is directly caused by gravity. Air molecules are pulled downward, accumulating near the surface where they're compressed by the weight of the air above. Higher up, there's less air above to create that compression. Eventually, at high enough altitudes, the atmosphere merges imperceptibly with the near vacuum of space. There's no sharp boundary, just a gradual thinning until individual atoms and molecules are so sparse that they rarely collide. Earth's gravity slightly compresses the planet's interior. The weight of overlying rock creates immense pressure deep within Earth. At the center, roughly 6,400 kilometers below the surface, the pressure is estimated to be about 360 gigapascals, roughly 3.6 million times atmospheric pressure at sea level. This pressure is created by gravity pulling all of Earth's mass toward the center. The rock in Earth's mantle and crust is compressed by this pressure, becoming denser than it would be at the surface. Even solid iron is compressed significantly. Earth's inner core is solid iron-nickel alloy that's under such extreme pressure that its atoms are squeezed closer together than they would be in iron at the surface. This compression, combined with the heat from Earth's formation and from radioactive decay, keeps Earth's interior hot and partially molten, driving plate tectonics and creating Earth's magnetic field. Gravity not only shapes the planet's exterior into a sphere, but also creates the conditions in the interior that make Earth geologically active. Gravity helps keep lakes level. Water seeks the lowest energy arrangement. A lake's surface is almost perfectly level because water flows until it finds equilibrium. If one part of the lake's surface were higher than another, gravity would pull that water downward, creating a flow toward the lower area until the surface leveled out. The only things that can create lasting variations in a lake's surface elevation are barriers like dams or differences in water density due to temperature or salinity, which can create very slight tilts. But for a typical lake with uniform water temperature and composition, the surface will be level, more precisely, perpendicular to the local direction of gravity's pull. This is such a reliable phenomenon that humans have used water levels as tools for thousands of years. Ancient builders used water-filled troughs to establish level surfaces for construction. The principle remains the same today in spirit levels and surveying equipment. Water finds its level because gravity ensures that any deviation from level creates a force that moves water to restore equilibrium. Sea level is basically a gravity-shaped surface across the planet. When we talk about sea level, we're referring to the surface that the ocean would form if it were perfectly still and not disturbed by waves, tides, currents, or winds. This surface, called the geoid, is perpendicular everywhere to the local direction of gravity. Because Earth isn't perfectly spherical, and because the distribution of mass within Earth isn't perfectly uniform, the geoid isn't a perfect ellipsoid either. It has slight variations, bumps and dips, that reflect variations in gravity. Where there's denser rock beneath the surface, gravity is slightly stronger, and the geoid is slightly higher. Where there's less dense material, gravity is slightly weaker, and the geoid is slightly lower. These variations are small, typically less than 100 meters of variation globally, but they're measurable and important for precise mapping and navigation. Satellites equipped with gravimeters have mapped Earth's geoid in detail, revealing the subtle variations in gravity across the planet. When we say a mountain is a certain height above sea level, we're really measuring its height, above the local geoid, above that gravity-shaped reference surface. Your body's circulation subtly works against gravity when you stand. Your cardiovascular system has to pump blood upward from your legs and lower body back to your heart, fighting against gravity's pull. When you're lying down, this is easy. Blood can flow horizontally with minimal effort. But when you stand up, blood tends to pool in your legs due to gravity. Your body has several mechanisms to combat this. Valves in your leg veins prevent blood from flowing backward. Muscles in your legs, when they contract during movement, squeeze the veins and help push blood upward. Your autonomic nervous system adjusts your heart rate and constricts blood vessels to maintain proper blood pressure to your brain. Sometimes these mechanisms don't work fast enough, especially if you stand up quickly after lying down for a while. The sudden shift in blood distribution can cause a temporary drop in blood pressure to the brain, leading to dizziness or lightheadedness, a phenomenon called orthostatic hypertension. Astronauts returning from space often have difficulty with this because their cardiovascular systems have adapted to microgravity, where pumping blood doesn't require fighting gravity. Their hearts become slightly less muscular, and the mechanisms for preventing blood pooling become less active. It can take weeks to readapt to Earth's gravity. Just one more small fact, and then we drift into the graceful mechanics of orbits. An orbit is a continuous fall around something, not straight into it. This is perhaps one of the most beautiful insights in physics, and it took humanity a long time to fully understand it. When you throw a ball horizontally, it follows a curved path, moving forward due to its initial velocity, while simultaneously falling downward due to gravity. The faster you throw it, the farther it goes before hitting the ground. Now imagine throwing it faster and faster. At some point, if you could throw it fast enough, about 7.9 kilometers per second at Earth's surface, the ball would fall toward Earth at the same rate that Earth's surface curves away beneath it. The ball would never hit the ground. It would be in orbit, continuously falling around the Earth. This is exactly what satellites do. They're not beyond Earth's gravity. They're very much within it, falling toward Earth constantly. But they're moving sideways so fast that they keep missing the planet, falling around it in a closed path. From the satellite's perspective, or from the perspective of someone inside, this feels like weightlessness, because there's no normal force from a surface pushing up. Everything is falling together at the same rate. Satellites stay up because they move forward fast while falling downward. The key to understanding orbits is recognizing that an orbiting object is simultaneously doing two things: falling toward the body it's orbiting due to gravity, and moving forward in a straight line due to its velocity. The combination of these two motions creates a curved path. If the forward velocity is just right, neither too fast nor too slow, the curve will form a closed loop, an orbit. Too slow, and the object will spiral inward, eventually crashing into the planet or whatever it's orbiting. Too fast, and the object will escape, following a curved path that doesn't loop back, heading off into space. The precise speed required for a circular orbit depends on the altitude. Closer to Earth, gravity is stronger, so you need to move faster to maintain orbit. The International Space Station, orbiting at about 400 kilometers altitude, travels at roughly 7.7 kilometers per second, over 17,000 miles per hour. Satellites in geostationary orbit, much higher at about 36,000 kilometers, move more slowly at about 3 kilometers per second, but still fast enough to complete one orbit in exactly 24 hours, matching Earth's rotation. The Moon is constantly falling toward Earth and constantly missing it. The same principle that keeps artificial satellites in orbit applies to natural satellites like the Moon. The Moon is falling toward Earth right now, pulled by gravity. But it's also moving sideways at about 1 kilometer per second. The combination of falling toward Earth and moving sideways means the Moon follows a curved path around Earth, orbiting approximately once every 27.3 days. The Moon doesn't feel like it's falling. From the Moon's perspective, or from the perspective of someone standing on the Moon, there's no sensation of falling. But from Earth's perspective, we can calculate that the Moon is indeed accelerating toward Earth at about 0.0027 meters per second squared. That's much smaller than the 9.8 meters per second squared we experience at Earth's surface because the Moon is much farther away, about 384,000 kilometers on average, and gravity decreases with the square of distance. The Moon's orbit isn't perfectly circular, it's slightly elliptical, so the Moon's distance from Earth varies a bit. But the fundamental principle remains. The Moon is in a stable orbit because its sideways velocity is balanced with the inward pull of gravity. Earth is constantly falling toward the Sun in the same gentle way. Just as the Moon orbits Earth, Earth orbits the Sun. Earth is falling toward the Sun, pulled by the Sun's enormous gravitational attraction, while simultaneously moving sideways at about 30 kilometers per second. The balance between these produces Earth's nearly circular orbit, which Earth completes once per year. The Sun's mass is about 330,000 times Earth's mass, and even though Earth is about 150 million kilometers from the Sun, the gravitational attraction is strong enough to keep Earth in a stable orbit. All the planets orbit the Sun by the same principle, Mercury whipping around quickly in its close orbit, Neptune slowly tracing its distant path, each one falling toward the Sun while moving sideways fast enough to keep missing it. The mathematics of orbital motion, worked out by Johannes Kepler in the early 17th century and explained by Isaac Newton later that century, revealed beautiful regularities. Planets closer to the Sun orbit faster. The square of a planet's orbital period is proportional to the cube of its average distance from the Sun. These patterns aren't coincidences, they're direct consequences of gravity's inverse square law. In space, astronauts feel weightless because they're in free fall. This can be confusing because we often think of space as being beyond gravity, but that's not accurate. The International Space Station orbits at an altitude where Earth's gravity is still about 90% as strong as it is at the surface. Astronauts feel weightless not because gravity has stopped working, but because they're falling toward Earth continuously, along with the space station and everything in it. When you're in free fall, there's no normal force, no floor pushing up on your feet, no chair pressing against your body. You and everything around you are accelerating together under gravity. This creates the sensation and practical reality of weightlessness. Objects float because they're not being pushed by anything. You can push off one wall and drift to the opposite wall without falling. It's a strange and beautiful environment, one that requires significant adaptation. Many astronauts experience nausea during their first few days in orbit, as their sensory systems adjust to the unusual situation of constant free fall. Microgravity means tiny leftover forces, not zero gravity. The term microgravity is more accurate than zero gravity for describing the environment on orbiting spacecraft. While the main effect of gravity is eliminated by free fall, there are still tiny residual forces. For instance, the space station is large enough that different parts of it are at slightly different distances from Earth, so they experience slightly different gravitational pulls. This creates tidal forces, very small forces that try to stretch the station slightly. There are also tiny forces from atmospheric drag, even at the station's high altitude. Solar radiation pressure, photons from the Sun pushing on the station's surfaces, creates a small force. Astronauts moving around inside create vibrations and small accelerations. All of these effects are tiny compared to Earth's gravity at the surface, but they're not zero, hence microgravity rather than zero gravity. These small forces can be important for certain experiments. Scientists studying crystal growth or fluid dynamics in space have to account for these residual accelerations because they can affect results. The International Space Station is still quite close to Earth. Gravity is strong there. 400 kilometers might sound like a lot, but it's really not very far in terms of escaping Earth's gravity. Earth's radius is about 6,370 kilometers, so the space station is only increasing its distance from Earth's center by about 6% compared to being on the surface. Gravity decreases with the square of distance from Earth's center, so at the space station's altitude, gravity is about 88% as strong as at the surface. If you could somehow place a scale at the space station's altitude and stand on it, while somehow being supported and not falling, you'd weigh only about 12% less than on the surface. The reason astronauts are weightless isn't that they're beyond gravity, but that they're falling freely within gravity's grip. They're in orbit, continuously falling around Earth. The edge of space is conventionally defined as 100 kilometers altitude, the Kármán line. But this is just a convenient boundary. There's no physical phenomenon that occurs exactly there. The atmosphere gradually thins and gravity gradually weakens, with no sharp transitions. Orbits can be circular or stretched into ellipses. While we often picture orbits as perfect circles, most natural orbits are actually ellipses, ovals with the body being orbited located at one focus of the ellipse. A circle is just a special case of an ellipse, where the two foci coincide. The shape of an orbit depends on the object's speed and direction when it reaches a particular point. If an object is moving at exactly the right speed, perpendicular to the direction toward the body it's orbiting, the orbit will be circular. Any other speed or direction produces an ellipse, assuming the object doesn't have enough energy to escape entirely. Earth's orbit around the Sun is nearly circular, but not quite. The distance varies by about 5 million kilometers between perihelion, when Earth is closest to the Sun in early January, and aphelion, when Earth is farthest in early July. Comets often have highly elliptical orbits, swooping in close to the Sun and then swinging far out into the outer solar system. The shape of an elliptical orbit is described by its eccentricity, a number between 0 and 1. 0 is a perfect circle, and as eccentricity approaches 1, the ellipse becomes more and more elongated. The closer you orbit, the faster you must move to stay in orbit. This is a direct consequence of how gravity weakens with distance and the requirements for orbital motion. Close to Earth, gravity is strong, pulling hard on an orbiting object. To avoid spiralling inward, the object must move fast enough that it falls around Earth rather than into it. At the altitude of the International Space Station, about 400 kilometers, an orbital velocity of roughly 7.7 kilometers per second is required. At the altitude of GPS satellites, about 20,000 kilometers, the required orbital speed is only about 4 kilometers per second. In geostationary orbit at 36,000 kilometers, satellites move at about 3 kilometers per second. This might seem paradoxical at first. Shouldn't you need to go faster to reach higher orbits? The resolution is that reaching a higher orbit does require more energy. You have to do work against gravity to get there. But once you're at that higher altitude, the orbital speed required to stay there is actually lower because gravity is weaker. This principle has practical implications for space missions. To go from a low orbit to a higher orbit, a spacecraft typically fires its engines in the direction of a motion, increasing its speed. This causes the orbit to stretch into an ellipse that reaches the higher altitude. At the high point, the spacecraft fires its engines again to circularize the orbit. Gravity is the invisible guide that keeps orbital motion consistent. Without gravity, all the intricate choreography of the solar system would fall apart. Planets would drift off in straight lines, no longer held in their orbits. Moons would separate from their planets. The Sun's family of orbiting bodies would disperse into the galaxy. But gravity maintains order. It's remarkably stable too. Earth has been orbiting the Sun for about 4.5 billion years, completing billions of orbits, and will likely continue for billions more. The Moon has been orbiting Earth for most of that time. These orbits aren't perfectly constant. They're perturbed slightly by the gravitational influences of other planets, by tidal forces, by the solar wind, but these perturbations are small, and the orbits remain stable. Gravity provides a reliable, predictable force that allows us to calculate planetary positions years or even centuries in advance with remarkable precision. This predictability has been crucial for human civilization, allowing us to create calendars, navigate by the stars, and send spacecraft on precise trajectories to other planets. Just one more small fact, and then we drift into the Moon's gentle influence on Earth's oceans and tides. Tides happen because gravity pulls more strongly on the near side than the far side. The Moon's gravity pulls on Earth, but because gravity weakens with distance, the pull on the side of Earth nearest the Moon is stronger than the pull on Earth's centre, which is stronger than the pull on the far side. This difference in gravitational force across Earth's diameter creates tidal forces that stretch Earth slightly along the line connecting Earth and the Moon. For solid rock, this stretching is small but measurable. For water, which can flow freely, the effect is more pronounced. Water on the side of Earth nearest the Moon is pulled more strongly toward the Moon than Earth's centre is, so it bulges slightly toward the Moon. Water on the far side of Earth is pulled less strongly than Earth's centre, so it effectively bulges away from the Moon. The result is two tidal bulges, one facing the Moon and one on the opposite side. As Earth rotates under these bulges, any given point on Earth's surface passes through high tide, approximately twice per day, once when it rotates through the bulge facing the Moon, and once when it rotates through the bulge on the opposite side. The Moon is the main driver of Earth's tides. The Moon is much smaller than the Sun, about 27 million times less massive, but it's also much closer, only about 384,000 kilometres away compared to the Sun's 150 million kilometres. Because tidal force depends on the difference in gravity across Earth's diameter, and because this difference is larger for nearby objects, the Moon's tidal effect is about twice as strong as the Sun's despite the Sun's greater mass. The Moon dominates Earth's tides, creating the primary rhythm of high and low tides. In many coastal locations, there are 2 high tides and 2 low tides each day, separated by about 6 hours. The timing shifts each day because the Moon orbits Earth, rising about 50 minutes later each day. This means high tide also occurs about 50 minutes later each day, creating a cycle that's tied to the Moon's motion rather than to the solar day. The Sun also makes tides, smaller, but still real. Even though the Sun's tidal effect is weaker than the Moon's, it's not negligible. The Sun creates its own tidal bulges on Earth, following the same principle: stronger gravitational pull on the side nearest the Sun, weaker pull on the far side. These solar tides add to or subtract from the lunar tides, depending on the relative positions of the Sun and Moon. The total tide at any given time is the combination of the lunar tide and the solar tide, plus contributions from Earth's rotation, the shape of ocean basins and other factors. The solar tides alone would create a smaller variation in ocean height than the lunar tides, but they're still significant enough to affect the total tidal range depending on how the Sun and Moon are aligned. When Sun and Moon align, tides can be higher. These are called spring tides. Twice a month, during the new moon and the full moon, the Sun, Moon and Earth are approximately aligned. At new moon, the Sun and Moon are on the same side of Earth. At full moon, they're on opposite sides. In both cases, the tidal bulges created by the Sun and Moon reinforce each other. The high tides are higher than average, and the low tides are lower than average. The difference between high and low tide, the tidal range, is at its maximum. These are called spring tides, though the name has nothing to do with the season. The term comes from the idea of the tide springing forth. Spring tides create the most dramatic tidal changes, which can be particularly noticeable in locations with naturally large tidal ranges, such as the Bay of Fundy in Canada, where spring tides can create a difference of over 15 metres between high and low tide. When they are at right angles, tides can be lower. These are called neap tides. Twice a month during the first quarter and third quarter moon phases, the Sun and Moon are at right angles as seen from Earth. The Sun is pulling Earth's water one way, and the Moon is pulling it a different way, and their tidal effects partially cancel out. The high tides are lower than average, and the low tides are higher than average. The tidal range is at its minimum. These are called neap tides, from an Old English word meaning scanty or barely sufficient. During neap tides, the difference between high and low tide is noticeably smaller than during spring tides. For people living on coasts, this cycle of spring and neap tides is very familiar, creating a fortnightly rhythm of larger and smaller tides, superimposed on the daily rhythm of the tides themselves. The ocean's rise and fall is like Earth's slow, twice-daily breath. There's something profoundly peaceful about the tides when you think of them this way. Twice each day the ocean rises, flooding beaches and estuaries, lifting boats in harbours, filling tidal pools. Then it falls again, retreating to exposed beaches, leaving boats resting on mud flats, revealing rocks and creatures in the intertidal zone. This rhythm has continued for billions of years, since the Moon first formed and began pulling at Earth's oceans. It's steady, reliable, and ancient. Coastal ecosystems have evolved to adapt to this rhythm. Some creatures can survive both underwater and exposed to air, timing their activities to the tidal cycle. Humans have built civilizations around tides, learning their patterns, using them for navigation, harvesting from tidal zones. The tides connect us to the moon's motion, to gravity's reach across space, to the long history of Earth's rotation and the slow dance of celestial bodies. Tides also happen in Earth's crust. Solid ground flexes slightly. It's not just water that responds to tidal forces. The solid Earth itself is stretched by the moon's and sun's gravity. The rock of Earth's crust and mantle isn't perfectly rigid. Under sustained force, it can deform slightly. The tidal force on Earth's solid body creates bulges similar to ocean tides, though much smaller. The ground beneath your feet rises and falls by about 30 centimetres twice daily due to these Earth tides, also called solid Earth tides or body tides. You can't feel this motion because it happens over such a large area and so gradually. It's not like an earthquake's sudden jolt, but rather a slow, gentle flexing of the entire planet. Scientists can measure Earth tides with sensitive instruments, and they have to account for them in precise measurements like gravimetry or laser ranging. Even the atmosphere experiences tides, atmospheric tides driven by both gravitational forces and thermal effects from solar heating. Tidal forces gently dissipate energy as heat through friction. As Earth rotates and tidal bulges move across the planet, they create friction. Ocean water sloshes back and forth in ocean basins. The solid Earth flexes and deforms. All of this motion generates heat through friction, dissipating energy. The energy comes ultimately from Earth's rotation. As tidal friction dissipates rotational energy, Earth's rotation gradually slows down. The effect is tiny. Earth's day is lengthening by about 1.8 milliseconds per century, but it's real and measurable. Over hundreds of millions of years, this adds up. Geological and paleontological evidence suggests that Earth's day was significantly shorter in the distant past. Fossilized coral growth patterns and tidal sediments indicate that about 400 million years ago, Earth's day was only about 22 hours long. The energy dissipated by tides is substantial on a global scale, about 3.7 terawatts, roughly the power output of several thousand large power plants. This energy ends up as heat in the oceans and Earth's interior. Over long time, tides slowly affect the moon's distance from Earth. The same process that's slowing Earth's rotation also affects the moon. Angular momentum is conserved in the Earth-Moon system, so as Earth's rotation slows, the moon must speed up in its orbit to conserve total angular momentum. When the moon speeds up, it moves to a higher, more distant orbit. The moon is currently receding from Earth at about 3.8 centimeters per year. This has been measured precisely by bouncing laser beams off reflectors placed on the moon's surface by Apollo astronauts. Over billions of years, the moon has moved significantly outward. When it first formed, likely from debris after a giant impact, the moon was much closer, perhaps only 20,000 kilometers from Earth, instead of today's 384,000. This meant stronger tides, a faster rotating Earth, and a moon that appeared much larger in the sky. The recession will continue until Earth's rotation becomes tidally locked to the moon's orbit, meaning Earth will rotate at the same rate the moon orbits, so the same side of Earth always faces the moon. This won't happen for billions of years, and other factors like the sun's eventual evolution into a red giant will likely intervene before tidal locking is achieved. They also slowly affect Earth's rotation, lengthening days by tiny amounts. We've mentioned that Earth's day is growing longer due to tidal friction. This has implications for timekeeping. Atomic clocks, which measure time based on the oscillations of atoms, tick at a constant rate. But Earth's rotation is gradually slowing, so solar days, measured by Earth's rotation relative to the Sun, are slowly getting longer. To keep our clocks synchronized with Earth's rotation, scientists occasionally add leap seconds to coordinated universal time. Since 1972, 27 leap seconds have been added. In the far future, if Earth continues to slow, though other factors will complicate this, days would become significantly longer. Some calculations suggest that if the Earth-Moon system had enough time to reach tidal equilibrium, Earth's day would lengthen to about 47 current days, matching the Moon's orbital period at that distant time. But again, this is far beyond any timescale relevant to human civilization, and well beyond the Sun's current stable lifetime. Just one more small fact, and then we drift into the subtle variations in Earth's gravitational field. Gravity can be measured with careful instruments called gravimeters. These devices are designed to detect very small changes in gravitational acceleration. Some gravimeters work by measuring the position of a mass on a spring. Stronger gravity pulls the mass down farther, stretching the spring more. Others use falling masses, precisely timing how fast an object falls in a vacuum chamber, since the rate of fall depends on gravitational acceleration. The most precise gravimeters can detect changes in gravity of less than 1 part per billion. That's precise enough to measure the change in gravity when you move up or down by just a few centimeters, or the change caused by water moving underground, or the flexing of Earth's crust during Earth tides. Scientists use gravimeters for many purposes, exploring for mineral and oil deposits by detecting density variations underground, monitoring volcanic activity by detecting magma movement, measuring groundwater depletion, studying ice sheet dynamics, and testing predictions of gravitational physics. Gravity measurements have revealed a great deal about Earth's interior structure and composition. Gravity isn't exactly the same everywhere on Earth. The acceleration due to gravity varies across Earth's surface for several reasons. Earth's rotation creates a centrifugal effect that's strongest at the equator and zero at the poles, reducing the effective gravitational pull at the equator. Earth isn't a perfect sphere. It's slightly flattened at the poles and bulges at the equator, so the distance from Earth's centre varies with latitude. The composition of Earth's crust and mantle varies from place to place, with denser rock in some regions and less dense rock in others. Mountains represent extra mass above the surface. Ocean trenches represent regions where the surface is farther from dense mantle rock. All of these factors combine to create variations in gravitational acceleration. The strongest gravity on Earth's surface is at the North Pole, about 9.83 meters per second squared. The weakest is near the equator in the Andes Mountains, about 9.76 meters per second squared. That's a difference of less than 1%, but it's measurable and meaningful. Denser rock under the ground can slightly increase local gravity. If there's a region where the subsurface rock is denser than surrounding areas, perhaps a large deposit of iron ore or other heavy minerals, gravity will be slightly stronger there. The extra mass pulls downward more strongly, increasing the gravitational acceleration. Conversely, regions with less dense rock, such as areas with underground salt deposits or ancient buried river channels filled with sediment, will have slightly weaker gravity. Geologists and geophysicists use gravity surveys to map these variations. By measuring gravity at many points and looking for anomalies, places where gravity is stronger or weaker than expected, they can infer something about the subsurface structure. This technique has been used to discover ore deposits, locate oil and gas reservoirs, and map geological structures. It's a form of seeing through the ground using gravity as a probe. High mountains can change the local gravity field. You might think that being on top of a mountain would mean weaker gravity because you're farther from Earth's centre, and that's true. Gravity does decrease with altitude. But the mountain itself is a large mass of rock, and that mass has its own gravitational pull. The mountain attracts you toward its centre of mass, which creates an upward component of force that partially offsets the decrease due to altitude. The net effect depends on the size and shape of the mountain. For very large mountains, the mass of the mountain can actually cause gravity to be slightly stronger than it would be at the same altitude without the mountain. Scientists studying precision measurements in mountainous regions have to account for this terrain effect, calculating the gravitational attraction of all the nearby topography to correct their measurements. Earth's rotation creates a small outward effect that slightly reduces felt gravity at the equator. When you're on Earth's surface, you're rotating along with the planet. At the equator, you're moving at about 465 meters per second in a large circle, of radius equal to Earth's radius. This circular motion requires a centripetal force, a force directed toward the center of the circle, to keep you moving in a circle rather than in a straight line. Gravity provides this centripetal force, but only part of gravity goes into maintaining your circular motion. The rest is what you perceive as your weight, the force pressing you against the ground. The centrifugal effect, really just a consequence of being in a rotating reference frame, effectively reduces your weight at the equator by about 0.3% compared to what it would be if Earth weren't rotating. At the poles, you're not moving in a circle, so there's no centrifugal effect. This is one reason you'd weigh slightly less at the equator than at the poles. That's one reason you'd weigh a bit less at the equator than at the poles. Combining the centrifugal effect with Earth's equatorial bulge gives a total variation of about 0.5% in gravitational. acceleration from pole to equator. If you weigh 150 pounds at the North Pole, you'd weigh about 149.3 pounds at the equator, a difference of roughly half a pound. This is small enough that most people wouldn't notice it without a scale, but it's significant for precision measurements. Athletes competing in high jump or pole vault could theoretically jump slightly higher at the equator than at the poles, both because of the weaker gravity and because the reduced centrifugal force means they have to gain slightly less altitude to clear the same height. Of course, other factors like altitude and weather conditions usually have much larger effects on athletic performance, but the gravitational variation is real. Satellites map Earth's gravity to study oceans, ice, and underground structures. Modern satellite missions like GRACE, the Gravity Recovery and Climate Experiment, have created detailed maps of Earth's gravitational field by precisely measuring tiny variations as satellites orbit. GRACE consisted of 2 satellites flying in formation, about 200 kilometers apart. As they orbited, variations in Earth's gravity caused the distance between them to change very slightly, sometimes by just a few micrometers. By measuring these distance changes with extreme precision, scientists could map variations in gravity. These variations reveal information about mass distribution on and within Earth. For instance, large ice sheets in Greenland and Antarctica create gravitational anomalies. As these ice sheets melt and lose mass, the gravitational pull in those regions weakens, and satellites can detect this change. Similarly, depletion of groundwater in aquifers creates measurable changes in gravity. Major earthquake events that shift large amounts of mass can also be detected. Gravity mapping can reveal changes in groundwater over time. In many regions of the world, groundwater stored in underground aquifers is being withdrawn faster than it's being replenished. Over time, this reduces the total mass of water underground, which causes a small but measurable decrease in local gravity. Satellite gravity measurements can detect these changes, providing a way to monitor groundwater depletion on a large scale. This is particularly valuable in regions where ground-based measurements are sparse or unavailable. For instance, satellite measurements have revealed significant groundwater depletion in parts of India, the Middle East, and the central United States. This information can inform water resource management and policy decisions. It's a beautiful example of how understanding gravity allows us to observe and measure environmental changes that would otherwise be difficult to track. Even gentle changes in ice mass can be detected through gravity shifts. The polar ice sheets of Greenland and Antarctica contain enormous amounts of water frozen as ice. If all of Greenland's ice melted, global sea levels would rise by about 7 meters. Antarctica contains even more ice, enough to raise sea levels by about 60 meters if it all melted. These ice sheets are dynamic, constantly accumulating snow in some areas, and losing ice through melting and calving of icebergs in others. Over recent decades, both ice sheets have been losing mass overall, contributing to rising sea levels. Satellite gravity measurements provide a way to measure this mass loss directly. As ice melts and flows into the ocean, the gravitational pull over the ice sheet decreases. By comparing gravity measurements over time, scientists can quantify how much ice is being lost and where the losses are occurring. This data is crucial for understanding climate change and predicting future sea level rise. Gravity becomes a way to see the invisible movement of mass. This is one of the beautiful insights of modern geophysics. Mass and gravity are intimately connected. Gravity is, in essence, a field created by mass. When mass moves, the gravitational field changes. By measuring these changes in the gravitational field, we can track the movement of mass even when we can't observe the mass directly. Water moving through underground aquifers, ice flowing in glaciers, magma shifting beneath volcanoes, sediment being transported by rivers, all of these processes involve moving mass, and all of them create subtle changes in gravity. With sufficiently sensitive instruments, either on the ground or in orbit, we can detect these changes and learn about processes occurring deep underground or high in the atmosphere. Processes that would be invisible to direct observation. Gravity provides a window into the hidden dynamics of our planet. Just one more small fact, and then we drift into the elegant strangeness of how gravity affects time and light. Gravity doesn't just pull objects, it's connected to the shape of space-time. This is where we move from the classical physics of Newton to the modern physics of Einstein. Newton described gravity as a force between masses, and his equations worked beautifully for most purposes. But Einstein showed that gravity is something deeper. According to general relativity, mass and energy curve the fabric of space-time, the four-dimensional continuum of space and time. Objects moving through this curved space-time follow paths called geodesics, which are the straightest possible paths through curved space. What we perceive as the force of gravity is actually objects following these natural paths through curved space-time. It's a profound shift in perspective. Earth orbits the Sun not because the Sun reaches out and pulls Earth with a force, but because the Sun's mass curves space-time, and Earth follows the natural path through that curved geometry. An apple falls from a tree not because Earth exerts a force that pulls it down, but because Earth's mass curves space-time, and the apple follows a path through that curved space-time toward Earth's centre. In Einstein's view, mass curves space-time and objects follow those curves. Imagine space-time as a flexible fabric like a rubber sheet. Place a heavy ball, representing the Sun or Earth, on the sheet, and it creates a depression, a curve in the fabric. Now, roll a smaller ball nearby. The smaller ball will curve toward the depression, not because the larger ball is pulling it with a force, but because it's following the curved geometry of the surface. This is an imperfect analogy, because it still uses gravity. The ball sinks into the sheet because of gravity, to explain gravity, but it captures the essence of the idea. Space-time itself is curved by the presence of mass and energy, and objects move along the curves. Light too follows these curves, which is why gravity can bend the path of light, even though light has no mass. Light follows the straightest possible path through space-time, and when space-time is curved, that path appears curved to distant observers. Stronger gravity makes time pass a tiny bit more slowly. This is one of the strangest and most verified predictions of general relativity. In a stronger gravitational field, closer to a massive object, time passes more slowly compared to time in a weaker gravitational field. The effect is called gravitational time dilation, and while it's extremely small in everyday circumstances, it's real and measurable. If you could place an extremely precise clock at sea level and another identical clock on top of a mountain, the clock on the mountain would run slightly faster than the clock at sea level. The difference is tiny, about 90 nanoseconds per day for each kilometre of elevation difference, but it's been measured and confirmed. Astronauts on the International Space Station, being higher in Earth's gravitational field, experience time passing slightly faster than people on Earth's surface, though this effect is partially offset by time dilation due to their high orbital velocity. This is called gravitational. This is time dilation. The deeper you are in a gravitational potential well, the slower your clock runs compared to a clock farther from the source of gravity. This isn't just an effect on clocks, it's an effect on time itself. All physical processes run more slowly in stronger gravity. This has been confirmed by many experiments. In one famous experiment, physicists placed atomic clocks on commercial aircraft and flew them around the world, then compared them to atomic clocks that remained on the ground. The airborne clocks, being at higher altitude and thus in a slightly weaker gravitational field, ran slightly faster, exactly as general relativity predicted. Near extremely dense objects like neutron stars or black holes, gravitational time dilation becomes dramatic. Close to a black hole's event horizon, time slows to a near standstill relative to distant observers. GPS satellites must correct for time dilation to stay accurate. This is perhaps the most practical everyday application of relativistic physics. GPS works by timing radio signals from satellites. Each satellite broadcasts a signal containing the satellite's location and the precise time the signal was sent. Your GPS receiver picks up signals from multiple satellites, measures the time each signal took to arrive, and uses this information to calculate your position. For this to work, the clocks on the satellites must be synchronized with clocks on Earth to within a few billionths of a second. But the satellites are about 20,000 kilometers above Earth's surface, moving at about 4 kilometers per second. Gravitational time dilation causes the satellite clocks to run faster by about 45 microseconds per day compared to clocks on the ground. Velocity-based time dilation, another relativistic effect, causes them to run slower by about 7 microseconds per day. The net effect is that satellite clocks run about 38 microseconds per day faster than ground clocks, without correcting. For this, GPS positions would accumulate errors of about 10 kilometers per day. GPS satellites correct for these relativistic effects, adjusting their clock rates so that they stay synchronized with Earth-based time. Time runs slightly faster higher above Earth than at sea level. For every meter you climb, time speeds up by about 1 part in 10 to the 16th power, a fantastically small amount, but not zero. Over the course of a day, a clock 1 meter higher than another will gain about 1 picosecond, 1 trillionth of a second. Climb a kilometer, and the difference becomes about a nanosecond per day. These are incredibly tiny differences, far too small to matter in daily life, but they're fundamental to how the universe works. They've been measured with atomic clocks sensitive enough to detect height differences of just a few centimeters based on the difference in clock rates. This extreme precision has applications in geodesy, the science of measuring Earth's shape and gravitational field, and in testing fundamental physics. The effect is small but real and measured. The Pound-Rebka experiment in 1959 was one of the first precision tests of gravitational time dilation. Physicists Robert Pound and Glenn Rebka measured the frequency shift of gamma rays travelling up and down a 22.5 metre tower at Harvard. Gravity caused the gamma rays travelling upward to lose energy. They were climbing out of Earth's gravitational field, and their frequency decreased slightly. This is exactly analogous to time dilation. A clock at the bottom of the tower runs slower, so it emits light at a slightly lower frequency. The measured frequency shift agreed with general relativity's predictions to within about 1%. Later experiments improved this precision dramatically. Modern atomic clocks can detect time dilation over height differences of just centimeters, confirming Einstein's predictions with extraordinary accuracy. Gravity and motion both affect time, and the corrections can add up. In special relativity, motion affects time. A moving clock runs slower than a stationary clock, an effect called velocity time dilation. In general relativity, gravity affects time. A clock in a gravitational field runs slower than a clock in empty space. Both effects are real, and both must be accounted for in situations where precision matters. For GPS satellites, both corrections are significant. For astronauts on the space station, gravitational time dilation makes their clocks run faster, while velocity time dilation makes them run slower, and the two effects nearly cancel, though gravitational time dilation wins by a small amount. For particle accelerators like the Large Hadron Collider, protons moving at nearly the speed of light experience dramatic velocity time dilation, living much longer from our perspective than they would if they were at rest. Understanding how gravity and motion affect time is essential for modern physics and technology. Relativity isn't just space stuff, it's used in everyday navigation. When you use GPS to navigate to a destination, you're relying on relativistic corrections. Without accounting for both gravitational and velocity time dilation, GPS simply wouldn't work accurately. Every smartphone, every car navigation system, every aircraft or ship using GPS is making use of Einstein's theories of relativity, usually without the user having any idea. It's a beautiful example of how fundamental physics, discovered through abstract theoretical reasoning and esoteric experiments, finds practical application in daily life. Relativity has moved from being an exotic curiosity to being an essential component of modern technology. This is one of the great triumphs of 20th century physics, not just understanding nature more deeply, but creating technologies that couldn't exist without that deeper understanding. The universe keeps time in a gentle, flexible way. Time isn't the rigid, absolute framework that Newton imagined. It's flexible, dynamic, affected by motion and gravity. Clocks in different locations, moving at different speeds or in different gravitational fields, can tick at different rates. They're all measuring time correctly from their own perspectives, but when you compare them, they disagree about how much time has passed. There's no universal now that spans the entire universe. Simultaneity depends on your frame of reference. This might sound unsettling, but it's simply how the universe works, and in most practical situations these effects are so tiny that we never notice them. Only when dealing with extreme precision, high speeds, or strong gravitational fields do relativistic effects become important. The universe's timekeeping is flexible, but it's governed by precise mathematical laws that we can measure and predict with extraordinary accuracy. Just one more small fact, and then we drift into gravity's ability to bend light and reveal hidden mass. Gravity can bend the path of light. This was one of the key predictions of general relativity that distinguished it from Newtonian gravity. Light has no mass, so in Newton's theory, gravity shouldn't affect light at all. But in Einstein's theory, gravity is a curvature of space-time, and light follows the curves of space-time regardless of whether it has mass. Light always travels in straight lines through space-time. These straight lines are called null geodesics, but when space-time itself is curved, those straight lines appear curved to distant observers. The effect is small under normal circumstances. Light passing near the Sun is bent by about 1.7 arcseconds, less than 1/2000th of a degree. But this is measurable, and it was first measured during a solar eclipse in 1919 by Arthur Eddington's expedition. The observation of stars appearing slightly displaced from their normal positions because their light was bent by the Sun's gravity was one of the first major confirmations of general relativity. This bending is called gravitational lensing. The term lensing is appropriate because massive objects can focus light much like a glass lens, though the physics is different. When light from a distant source passes near a massive object, a galaxy, a cluster of galaxies, even a star, the massive object's gravity bends the light's path. If the alignment is just right, with the source, the lens, and the observer nearly in a line, the light can be focused, making the source appear brighter or creating multiple images of it. Gravitational lensing has become an important tool in astronomy. It allows astronomers to observe distant objects that would otherwise be too faint to see and to study the distribution of mass in the universe, including dark matter, which doesn't emit light but still gravitates. Lensing can make distant galaxies look stretched or multiplied. When a distant galaxy sits almost directly behind a massive galaxy or galaxy cluster from our perspective, the gravitational lensing can create dramatic effects. The distant galaxy's light is bent around the foreground mass, and depending on the exact alignment, we might see the distant galaxy stretched into an arc or even split into multiple images. Some of the most striking images from the Hubble Space Telescope show these gravitational arcs, bright elongated streaks of light curving around massive galaxy clusters. In rare cases with nearly perfect alignment, the distant galaxy can be lensed into a complete ring around the foreground mass, called an Einstein ring. These beautiful structures are direct visual evidence of gravity bending light, of space-time curvature affecting photons travelling across billions of light years. Lensing helps astronomers measure mass that can't be seen directly. One of the most powerful applications of gravitational lensing is measuring mass. The amount of bending depends on the mass of the lensing object, so by carefully measuring how much a distant galaxy's light is bent, astronomers can calculate the mass of the foreground object doing the lensing. This works even if the lensing mass doesn't emit light. You could have a massive object made of something completely dark, emitting no light whatsoever, and it would still lens background galaxies, revealing its presence through gravity. This has been crucial for studying dark matter, the mysterious substance that makes up most of the mass in galaxies and galaxy clusters, but doesn't interact with light. Without gravitational lensing, we'd have a much harder time measuring how much dark matter exists and how it's distributed. This includes the influence of dark matter. Dark matter doesn't emit, absorb, or reflect light, so we can't see it directly with telescopes, but it has mass, and mass creates gravity, and gravity bends light. By mapping how light from distant galaxies is bent by foreground galaxy clusters, astronomers can create maps of the dark matter distribution. These maps reveal that dark matter forms a sort of scaffolding throughout the universe. Galaxies sit in halos of dark matter, and galaxy clusters sit in even larger dark matter structures. The distribution of dark matter is smooth and widespread, unlike ordinary matter which clumps into stars and galaxies. About 85% of the matter in the universe is dark matter, and gravitational lensing is one of the main ways we know this. It's a humbling reminder that most of the mass in the universe is made of something we don't yet understand, detectable only through its gravitational effects. Dark matter doesn't shine, but its gravity still shapes galaxies. The rotation of galaxies provides another clue to dark matter's existence. Stars in the outer regions of galaxies orbit faster than they should if the galaxy contained only the visible matter we can see. There must be additional mass, dark matter, spread throughout and around the galaxy, providing extra gravity to keep those outer stars in orbit. Gravitational lensing confirms this picture. The total mass measured through lensing is much greater than the mass we can account for in stars, gas, and dust. Dark matter dominates the mass budget of most galaxies. Without dark matter, galaxies as we observe them couldn't exist. The visible matter would have been insufficient to gravitationally collapse into the structures we see. Dark matter provided the gravitational seeds around which ordinary matter could gather to form stars and galaxies. Galaxy clusters can act like huge lenses in space. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies, along with huge amounts of hot gas and dark matter. The total mass can be equivalent to hundreds of trillions of suns. This enormous mass creates substantial curvature of space-time, making galaxy clusters powerful gravitational lenses. Light from galaxies far beyond the cluster is bent as it passes through the cluster's gravitational field. Astronomers use this effect to study both the cluster itself, measuring its mass distribution, and the distant background galaxies whose light is magnified by the lensing. Some of the most distant galaxies ever observed have been detected because a foreground galaxy cluster magnified their light, making them bright enough to see. Lensing is like a calm, natural magnifying glass made by gravity. There's something elegant about gravitational lensing. The universe provides its own telescopes in the form of massive structures that focus light. This magnification is gentle, natural, requiring no technology or intervention. It's simply a consequence of how mass curves space-time and light follows those curves. Astronomers can take advantage of this natural magnification to peer deeper into the universe than would otherwise be possible. A distant galaxy that's too faint to observe directly might become visible when its light is magnified several times by a foreground cluster. This has allowed observations of some of the earliest galaxies formed in the universe, helping us understand how galaxies evolved over cosmic time. Even empty-looking regions can reveal mass through lensing patterns. Gravitational lensing is so sensitive that it can detect mass even in regions that appear empty to optical telescopes. For instance, weak gravitational lensing studies analyze the shapes of thousands or millions of distant galaxies. Dark matter between us and those galaxies causes tiny systematic distortions in the galaxy's shapes. Any single distortion is too small to measure reliably, but by averaging over many galaxies, the statistical pattern becomes clear. These patterns reveal the distribution of dark matter along the line of sight, even in regions with few or no visible galaxies. It's a way of mapping the invisible structure of the universe, revealing the web of dark matter that connects galaxy clusters and fills the space between them. Gravity can be a quiet messenger of what's hidden. This is a beautiful theme in modern astronomy and physics. Gravity reveals what's invisible. It tells us about dark matter through lensing and galaxy rotation. It tells us about black holes through the motion of stars and gas near them. It tells us about distant planets orbiting other stars through subtle wobbles in the star's motion. It tells us about the interior structure of Earth through tiny variations in gravitational acceleration. Gravity is transparent. We can't block it or shield against it. And this makes it an ideal messenger. Information carried by gravity can reach us from regions we could never observe directly with light. By understanding gravity and measuring it precisely, we learn about hidden aspects of the universe, from the center of Earth to the hearts of galaxies, to the cosmic web of dark matter spanning billions of light years. Just one more small fact, and then we drift into gravity's role in building stars and planets. Gravity is what makes clouds of gas collapse to form stars. Stars are born in vast clouds of gas and dust scattered through galaxies. These clouds can be light years across, containing enough material to make thousands or millions of stars. Left undisturbed, such a cloud might just sit there indefinitely, with the random thermal motion of gas molecules balanced by the cloud's overall stability. But if something disturbs the cloud, a shockwave from a nearby supernova explosion, a collision with another cloud, or just a random denser region, gravity can take over. The denser region has slightly more mass, so it pulls more strongly on surrounding gas. Gas falls toward the dense region, making it denser still, which strengthens the gravitational pull, which draws in more gas. This runaway process is called gravitational collapse. As the cloud collapses, it heats up. Gravitational potential energy is converted to kinetic energy, and then to heat as gas particles collide. Eventually, the center becomes hot enough, about 10 million degrees, for nuclear fusion to begin. Hydrogen nuclei fuse to form helium, releasing energy. A star is born. A star's gravity holds hot plasma together against pressure pushing outward. Once fusion begins, a star faces opposing forces. Gravity pulls everything inward, trying to collapse the star. But fusion releases energy, heating the star's interior to millions of degrees, creating immense pressure that pushes outward. For most of a star's life, these forces balance. Gravity and pressure reach equilibrium, and the star shines steadily, converting hydrogen to helium in its core. This balance can last billions of years for stars like the Sun. The Sun has been burning steadily for about 4.6 billion years and has enough hydrogen fuel for another 5 billion years. Only when a star runs low on fuel does the balance shift. Without fusion to maintain, pressure, gravity wins, and the star collapses. Depending on the star's mass, this can lead to various end states: a white dwarf, a neutron star, or a black hole. Planets form in disks where gravity gathers dust into larger bodies. When a cloud of gas collapses to form a star, it typically has some angular momentum, some overall rotation. As it collapses, conservation of angular momentum causes it to spin faster, and it flattens into a disk with the forming star at the centre. This is the protoplanetary disk. The disk contains gas and dust, particles ranging from molecules to sand grain-sized dust grains. These particles collide and sometimes stick together due to electrostatic forces and ice coatings. Gravity is initially too weak to matter for tiny particles, but as particles accumulate into larger bodies, pebbles, boulders, eventually planetesimals the size of asteroids, gravity becomes important. Larger bodies have stronger gravitational pull, attracting more material, growing faster. This is runaway accretion. Eventually, the largest bodies clear out their orbital regions, accumulating most of the available material. These become planets. The details are complex and still being actively researched, but gravity is central to the process, pulling matter together and shaping the architecture of planetary systems. Gravity organizes rings, moons, and stable paths around planets. Planets with sufficient mass can have their own systems of moons and rings. Moons form either by capturing passing bodies, by co-formation from a disk around the planet, or from debris created by giant impacts. Once in orbit, moons and ring particles follow paths determined by gravity. The rings of Saturn, for instance, are made of countless particles, mostly ice, orbiting the planet. Gravity holds them in orbit and also creates structure within the rings. Moons embedded in or near the rings create gaps and waves through their gravitational influence. Some moons shepherd ring material, keeping it confined to specific regions. The whole system is a dynamic equilibrium, with gravity governing every particle's motion. Moons can be captured into resonances where their orbital periods are related by simple fractions. For instance, Jupiter's moons, Io, Europa, and Ganymede, are in a 4:2:1 resonance. These patterns arise naturally from gravitational interactions and are stable over long time scales. Jupiter's gravity helps shape the asteroid belt's patterns. The asteroid belt, located between Mars and Jupiter, contains millions of rocky bodies ranging from dust particles to dwarf planet-sized objects. Jupiter's enormous mass, about 318 times Earth's mass, exerts significant gravitational influence on the asteroids. There are regions within the asteroid belt called Kirkwood gaps, where very few asteroids are found. These gaps correspond to orbital resonances with Jupiter. An asteroid in one of these resonant orbits experiences periodic gravitational tugs from Jupiter that add up over time, eventually perturbing the asteroid into a different orbit. Over millions of years, these resonances clear out certain regions of the belt. Jupiter's gravity also prevented the asteroid belt from forming a planet. The strong gravitational stirring caused by Jupiter's presence kept the asteroids moving too fast relative to each other to coalesce into a larger body. Collisions tended to fragment rather than merge, so instead of a planet we have the asteroid belt, a remnant of the early solar system, preserved by Jupiter's gravitational influence. Gravity can slingshot spacecraft, using motion and pull to change speed. This technique, called a gravity assist or gravitational slingshot, allows spacecraft to change speed and direction without using fuel. The spacecraft flies close to a planet, entering the planet's gravitational field. From the planet's perspective, the spacecraft falls toward it, swings around behind it, and flies away at the same speed it approached. But from the Sun's perspective, the solar system's reference frame, The spacecraft can gain or lose speed depending on the geometry of the encounter. If the spacecraft approaches the planet from behind in its orbit and swings around to fly in the same direction the planet is moving, the spacecraft can steal a bit of the planet's orbital energy, speeding up. Conversely, approaching from ahead and swinging around can slow the spacecraft down. The planet's velocity changes too, but because planets are so massive, the change is immeasurably small. This technique has been used for many missions, allowing spacecraft to reach distant destinations they couldn't otherwise reach with available fuel. Gravity is also why atmospheres exist on planets at all. A planet's atmosphere is held in place by gravity. Gas molecules in the atmosphere are constantly moving. Hotter gases move faster, but as long as their average speed is well below the planet's escape velocity, gravity keeps them bound. Escape velocity is the speed needed to break free of a planet's gravitational pull. For Earth, it's about 11 kilometers per second. Most atmospheric molecules move much slower. Nitrogen molecules at room temperature average about half a kilometer per second, so they stay bound. But lighter molecules like hydrogen and helium can more easily reach escape velocity, especially if heated by solar radiation, which is why Earth's atmosphere has lost most of its primordial hydrogen and helium. Mars, with its weaker gravity, escape velocity about 5 kilometers per second, has lost most of its atmosphere over billions of years. The solar wind stripped it away, a process that would have been much slower if Mars had stronger gravity. Venus, similar in size to Earth, has retained a thick atmosphere, mostly carbon dioxide. Gravity shapes not just whether a planet has an atmosphere, but also what that atmosphere is made of. Bigger planets hold thick atmospheres more easily. Jupiter, Saturn, Uranus, and Neptune, the giant planets, are mostly gas. They're so massive that they can hold on to even the lightest elements, hydrogen and helium, which make up the bulk of their atmospheres. Jupiter's escape velocity is about 60 kilometers per second. At that speed, it's almost impossible for gases to escape, so Jupiter has retained almost all of its original atmosphere from when it formed over 4 billion years ago. Smaller rocky planets like Earth or Mars have lost lighter gases but retain heavier ones like nitrogen, oxygen, and carbon dioxide. Very small bodies like the Moon or asteroids have such weak gravity, and thus such low escape velocities, that they can't hold any significant atmosphere at all. Any gas released by impacts or outgassing quickly escapes into space. Gravity creates a natural sorting mechanism, determining which worlds can have atmospheres and which cannot. Small moons may have almost no atmosphere because gravity is weak. Take Phobos, one of Mars's 2 small moons. It's only about 22 kilometers across, irregularly shaped, probably a captured asteroid. Its gravity is so weak that the escape velocity is only about 11 meters per second, slower than some rockets, and about twice as fast as a sprinting human. Any atmosphere would quickly escape into space. Even if impacts released gases from Phobos's interior, those gases would disperse within hours or days. Many small moons and asteroids throughout the solar system face the same constraint. They're simply too small to hold onto atmospheres. This creates stark contrasts. Large moons like Saturn's Titan, which is bigger than the planet Mercury, can have thick atmospheres because their gravity is strong enough, but small moons remain airless, barren, with no protection from meteorites or radiation, their surfaces marked by countless impact craters. Gravity is a builder, slow, steady, and patient. Over billions of years, gravity has built structure throughout the universe. It collapsed gas clouds to form galaxies. Within galaxies, it collapsed smaller clouds to form stars. Around stars, it gathered dust and gas into planets. It created moons, rings, and countless smaller bodies. Everywhere we look, we see the architecture that gravity has created. And the process continues. Stars are forming right now in gas clouds throughout our galaxy and throughout the universe. New planets are forming around young stars. Moons are being captured, and comets are being perturbed into new orbits. Gravity never stops working. It's patient, operating over timescales that dwarf human lifetimes, but relentless in its slow construction and organization of matter. Understanding gravity helps us understand how we came to be, how Earth and the Sun and the entire solar system formed, how our galaxy came together, how the universe evolved from a nearly smooth state just after the Big Bang to the richly structured cosmos we observe today. Just one more small fact. and then we drift into the most extreme manifestations of gravity while maintaining our calm perspective. A black hole is a region where gravity is so strong that escape becomes impossible past a boundary. In a sense, a black hole is the ultimate endpoint of gravitational collapse. If enough mass is compressed into a small enough volume, gravity becomes so intense that not even light can escape. This sounds dramatic, but it's simply an extreme case of the gravity we've been discussing. Any mass creates a gravitational field. If you compress that mass into a smaller volume, the gravitational field at the surface becomes stronger. Keep compressing, and eventually you reach a point where the escape velocity at the surface equals the speed of light. Compress further, and there's a region from which escape is impossible. That region is a black hole. The surface of no return is called the event horizon. Once anything, matter, light, information, crosses the event horizon, it cannot escape. It will inevitably fall inward toward the centre, toward what's called the singularity, where our current understanding of physics breaks down. That boundary is called an event horizon. The event horizon isn't a physical surface. It's not made of matter. It's simply a boundary in space. On one side, escape is possible if you accelerate enough. On the other side, escape is impossible regardless of acceleration. For a non-rotating black hole, the event horizon is a sphere. The radius of this sphere depends on the black hole's mass. For a black hole with the mass of the Sun, the event horizon would be about 3 kilometers in radius. For a black hole 1,000,000 times the Sun's mass, typical of those found at galaxy centers, the event horizon would be about 3 million kilometers in radius, roughly 4 times the distance from the Earth to the Moon. Despite the name black hole suggesting something small and dense, supermassive black holes have event horizons that are enormous, comparable to the size of our solar system's inner planets' orbits. Black holes can form when very massive stars finish their life cycles. When a very massive star, say more than 20 times the Sun's mass, exhausts its nuclear fuel, fusion stops. Without the outward pressure from fusion, gravity takes over completely. The star's core collapses in a fraction of a second. The collapse is so rapid and catastrophic that protons and electrons are crushed together to form neutrons. If the core's mass is above a certain threshold, about 3 solar masses, even neutron degeneracy pressure can't halt the collapse. There's no known force strong enough to stop it. The core collapses all the way to a singularity, forming a black hole. The outer layers of the star bounce off the collapsing core and explode outward in a supernova, one of the universe's most energetic events. But at the centre where the core was, there's now a black hole. This stellar mass black hole might be only a few kilometres across, but it contains several times the Sun's mass, compressed to incredible density. Despite their reputation, black holes can be quiet. No sound, no drama, just gravity. Black holes have a fearsome reputation in popular culture, often portrayed as cosmic vacuum cleaners that suck in everything nearby. But this isn't accurate. A black hole's gravity, at a distance, is no different from the gravity of any other object with the same mass. If the Sun suddenly became a black hole of equal mass, which it won't because the Sun isn't massive enough, Earth would continue orbiting exactly as it does now. The gravitational pull at Earth's orbital distance would be unchanged. You'd only notice differences if you approached very close to the event horizon. Far from the black hole, it simply sits there, a gravitational well like any other, pulling on nearby matter according to the same laws of gravity that govern planets and stars. Black holes can accrete matter if there's material nearby. As matter spirals inward, it heats up and emits radiation, which can be detected. But if a black hole is isolated with nothing nearby, it's essentially invisible, quietly existing, detectable only by its gravitational influence. Many galaxies likely have a supermassive black hole at their centre. Observations over the past few decades have revealed that most large galaxies, including our own Milky Way, have supermassive black holes at their centres. These black holes have masses ranging from millions to billions of times the Sun's mass. The Milky Way's central black hole, called Sagittarius A, pronounced Sagittarius A star, has a mass of about 4 million suns. We've observed stars orbiting it in elliptical paths, allowing astronomers to calculate its mass precisely. The black hole itself can't be seen directly, it emits no light, but its gravitational influence on nearby stars is unmistakable. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow. the silhouette of the event horizon against the glowing material around it, for the supermassive black hole at the centre of the galaxy, M87. It was a landmark achievement, directly visualising the region around a black hole for the first time. Objects can orbit black holes, just like planets orbit stars. Despite their extreme gravity, black holes don't violate the normal rules of orbital mechanics. If you're far enough from a black hole, orbiting it is no different from orbiting a star of the same mass. In fact, there are stars orbiting close to Sagittarius A at the centre of our galaxy. These stars follow elliptical orbits, speeding up as they approach the black hole and slowing down as they recede, just as Kepler's laws predict. Close to the black hole, effects of general relativity become important, orbits precess, time runs slower, light is bent. Dramatically, but stable orbits still exist outside the event horizon. There's even a special radius called the photon sphere, where light itself can orbit the black hole, though these orbits are unstable. Inside the event horizon, though, no orbit is possible. Everything falls inward toward the singularity. The strongest gravity effects happen very close. Far away, black holes behave like any mass. This is worth emphasizing because it counters the common misconception that black holes are cosmic monsters that destroy everything around them. At a distance, a black hole is just a gravitational source. Its gravity follows an inverse square law, weakening with distance, just like any other mass. If you were somehow able to replace the Sun with a black hole of exactly the Sun's mass, the planets would notice nothing different about their orbits. Earth would continue orbiting as before. The tides would be the same. The only difference would be that we'd receive no light and heat from the black hole, so Earth would freeze, but gravitationally nothing would change. It's only when you get close, within a few times the event horizon radius, that black holes reveal their unique properties. There, gravity is so strong that relativistic effects become dramatic. Time dilation becomes extreme. Light paths are bent severely. The tidal forces, differences in gravity across an object, become so strong they could rip objects apart. But these extreme effects are localized to the region very near the black hole. Gravity waves are ripples in space-time from massive events, gently travelling outward. When massive objects accelerate, they create disturbances in the fabric of space-time that propagate outward at the speed of light. These are gravitational waves, predicted by Einstein's general relativity and first directly detected in 2015 by the LIGO observatories. The detection was of waves from two black holes orbiting each other and merging, an event that occurred over 1 billion light-years away. As the black holes spiraled together, they accelerated, creating gravitational waves that rippled through space-time. By the time these waves reached Earth, they were incredibly weak. They stretched and squeezed space by less than 1,000th the diameter of a proton. But LIGO's exquisitely sensitive detectors could measure even this tiny effect. Since then, dozens of gravitational wave events have been detected, from black hole mergers, neutron star mergers, and other cataclysmic events. Gravitational waves open a new window on the universe, allowing us to observe events that emit little or no light, but involve tremendous masses accelerating. Even with all this cosmic scale, gravity in your room is simple and safe. After touring the universe, exploring time dilation and black holes, and gravitational lensing and the formation of galaxies, it's worth returning to the everyday. In your room, right now, gravity is simply pulling you gently toward Earth's centre at 9.8 meters per second squared. It's holding you comfortably on your bed. It's keeping the air in the room from floating away. It's making sure that if you set something down, it stays where you put it. There's nothing extreme or dangerous about the gravity you experience daily. It's gentle, reliable, and life-sustaining. All the dramatic phenomena we've discussed, black holes, time dilation, gravitational waves, these occur only under extreme conditions involving tremendous masses or energies, far from our everyday experience. For you, here, now, gravity is just a quiet companion, holding you safely to Earth. Gravity has held Earth, oceans, air, and you steadily, long before tonight, and it will keep holding everything as you rest. For 4.5 billion years, gravity has held Earth together. It's shaped the planet into a sphere, organised the oceans and atmosphere, held the moon in its orbit. It's been present for every moment of Earth's history, through ice ages and warm periods, through mass extinctions and the evolution of life, through the rise of mountains and the wearing down of ancient ranges. It was there long before humans existed, and it will be there long after. On a personal level, gravity has held you from the moment you were conceived, shaping your development in the womb, guiding your first movements as an infant, supporting you every day of your life. It's so constant that you forget it's there, but it never forgets you. Tonight, as you drift towards sleep, gravity is holding you just as it always has, gently and reliably, pressing you into the mattress, creating that comforting sensation of being supported, of being grounded, of being safe. Return to the room now, to your breathing, to the softness of the bed beneath you, the sheets against your skin, the pillow cradling your head, the slight weight of a blanket. All of these sensations are amplified by gravity. Without it, you'd float free, untethered, but with it, you're held. You're connected to the Earth, to the planet that has been your home, to the same force that guides the moon and the planets and the distant galaxies. Gravity is doing all the work. You don't need to think about it. You don't need to hold yourself in place. You can let go completely. Feel the gentle rise and fall of your breath. Each inhale lifts your chest slightly against gravity. Each exhale allows gravity to help your chest settle back down. The rhythm is effortless, automatic, aided by the constant presence of gravity organizing your body, pulling air into your lungs when you create space for it, helping blood circulate through your veins and arteries. Gravity is woven into every system of your body, every breath, every heartbeat, every movement and moment of stillness. You don't need to figure anything out. There are no problems to solve, no questions to answer. The universe is vast and filled with wonders, time that flows differently in different places, light that bends around massive objects, black holes and dark matter and the slow dance of galaxies. But none of that requires your attention right now. It's all happening all the time, with or without your awareness. The cosmos is running itself, gravity doing its patient work across every scale from the smallest dust grain to the largest galaxy cluster. And here, in this room, in this bed, you're part of it all, held gently by the same force. Let your thoughts slow down. If a thought arises, notice it, and then let it drift away like one of those dust motes settling gently to the floor under gravity's patient pull. You don't need to hold on to any thought. You don't need to chase any idea. Everything can settle. Everything can rest. Your body is getting heavier, sinking deeper into the mattress. This is just your muscles relaxing, releasing the tension they've held throughout the day. Gravity has always been there, but now you're allowing it to support you completely. Your shoulders sink. Your hips sink. Your legs become heavy and still. Even your eyelids, if they're not already closed, are being pulled gently downward by gravity, making it easier to let them stay closed than to hold them open. The bed is solid beneath you. The earth is solid beneath the bed. Beneath the earth's surface, miles of rock and soil and stone, all held together by gravity, all of it supporting you in this moment. You're connected to all of it, part of a vast, stable system that has existed for billions of years and will continue to exist for billions more. Nothing is required of you except to rest. Inhale gently, filling your lungs with air that's held around the planet by gravity, air that's been here in one form or another since Earth formed, cycled through countless plants and animals, through oceans and atmosphere, all organized and kept in place by gravity's gentle, invisible pull. Exhale slowly, releasing the air, letting gravity help your chest settle, letting everything in your body relax just a little more. With each breath, you're sinking deeper into rest, into the quiet support of gravity, into the stillness that has always been available to you. There's nowhere you need to be but here. Nothing you need to do but breathe and rest. Gravity is holding you. The earth is holding you. The universe, in its vast and patient way, is holding you. You're safe. You're supported. You can let go completely. And as your thoughts drift farther apart, as the space between them grows wider and quieter, you can trust that everything will continue. The moon will continue its orbit. The stars will continue their slow paths across the sky. Gravity will continue its patient work, organizing matter, bending light, shaping space-time, doing exactly what it's always done, what it will always do. You can let yourself fall now. Not in any dangerous way, but in the sense of surrendering to gravity, to sleep, to rest. Just let go. Let gravity carry your thoughts downward into sleep. Let the steady pull of the universe guide you into dreams, into the deep restorative darkness where nothing is required and everything is already taken care of. Gravity is doing its work. You can sleep now. Just let go and drift and rest. The next story is about to begin. Please relax and enjoy. The universe is made of atoms, and atoms are made of even smaller pieces, and tonight we're going to explore them all in the quietest way possible. An atom is one of the smallest building blocks that still keeps the identity of an element. When you touch a piece of copper, you're touching countless copper atoms. When you breathe in oxygen, you're drawing oxygen atoms into your lungs. The word atom comes from an ancient idea meaning uncuttable. A historical guess that matter had a smallest piece that couldn't be divided any further. For thousands of years, people wondered if you could keep cutting something in half forever, or if eventually you'd reach a final, indivisible fragment. The atom was imagined as that final piece, though we now know atoms themselves contain even smaller components. Still, the name stuck, and it's a useful one. Most everyday objects are made of atoms bonded into molecules and solids. The wood of a table, the fabric of a blanket, the glass of a window. All of these are atoms linked together in various arrangements. Atoms are so small that a single grain of sand contains an unimaginable number of them. If you tried to count the atoms in just one grain, you'd be counting for longer than the universe has existed. That's how tiny they are, and how many of them cluster together to make even the smallest visible speck. Every atom has a tiny center called a nucleus. This nucleus is the atom's heart, its anchor point, the place where most of its mass is concentrated. The nucleus contains protons and neutrons. These are the particles that give the nucleus its weight and its identity. Electrons occupy the region around the nucleus. They're much lighter than protons or neutrons, and they move through the space surrounding that central core. Protons carry a positive electric charge. This positive charge is fundamental to how atoms interact with each other and with the world. Electrons carry a negative electric charge, because opposite charges attract. The positive protons and negative electrons are drawn to one another, which is part of what holds an atom together. Neutrons have no net charge, which helps stabilize many nuclei. Without neutrons acting as a kind of cushion or glue, many atomic nuclei would fly apart due to the repulsion between positively charged protons. An element is defined by the number of protons in its nucleus. That number is the only thing that determines what element you're dealing with. Hydrogen has one proton, so it's the simplest element. Every hydrogen atom in the universe, whether it's in your body, in a distant star, or drifting through the void of space, has exactly one proton in its nucleus. Carbon has 6 protons, and that 6 is its atomic number. If you see the number 6 on the periodic table next to carbon, that's telling you every carbon atom has 6 protons. Change that number, and you no longer have carbon. You have something else entirely. If an atom gains or loses electrons, it becomes an ion. Atoms don't always keep a perfect balance of protons and electrons. Sometimes an atom will give up an electron, leaving it with more protons than electrons, which makes it positively charged. Sometimes an atom will gain an extra electron, giving it more electrons than protons, which makes it negatively charged. These charged atoms, ions, play crucial roles in chemistry, in electricity, in biology. Your nerves work because ions move in and out of cells. Batteries function because ions flow from one place to another. Atoms in your body are the same kinds of atoms found throughout the Earth and stars. The carbon in your skin is the same carbon found in a diamond, in a tree, in the atmosphere of a distant planet. The oxygen you breathe is the same oxygen that once bubbled out of ancient oceans. There's something quietly profound about that. Atoms don't belong to you or to any one place. They're universal travellers, endlessly recycled, endlessly repurposed. Just one more small fact, and then we drift a little deeper. Atoms are mostly empty space compared to their overall size. When you picture an atom, you might imagine something solid and compact, but the truth is quite different. The nucleus is extremely tiny compared to the atom's full footprint. If you could zoom in and measure the distances involved, you'd find that the nucleus occupies only a minuscule fraction of the atom's total volume. If the nucleus were the size of a pea, the atom could be the size of a stadium. That's a common scale analogy, and while it varies depending on the atom, it gives you a sense of the proportions. The nucleus is a tiny speck, and the electrons are somewhere out in the vast surrounding space. You don't fall through the floor because electrons repel each other. Even though atoms are mostly empty, they don't just collapse into one another or pass through each other like ghosts. When you sit in a chair, the atoms in your body and the atoms in the chair don't merge. Instead, the electrons in your atoms and the electrons in the chair's atoms push against each other. Touch is mostly the feeling of electromagnetic forces, not atoms physically interlocking like hooks. When you press your hand against a wall, you're not actually making contact in the way it feels. You're experiencing the repulsion between electron clouds. It's an electromagnetic sensation, a force field pushing back. The space around the nucleus is described as an electron cloud, a probability region. Electrons are not little planets on neat circular tracks in the modern picture. That old image of an atom, with electrons orbiting like tiny marbles around a central sun, was an early model and a useful one for its time, but it's not quite right. Instead, electrons occupy orbitals, which are shapes where they're likely to be found. An orbital is a region of space where an electron spends most of its time, but it's not a fixed path. The electron doesn't trace a neat circle or ellipse. It exists in a kind of fuzzy probability cloud, appearing here and there in a way that follows the rules of quantum mechanics. Atoms can be excited when electrons gain energy. If you shine light on an atom, or heat it up, or hit it with another particle, an electron might absorb some of that energy and jump to a higher orbital, farther from the nucleus. When electrons drop back down, atoms can release light, photons. The electron can't stay in that higher excited state forever. Eventually it falls back down to a lower orbital, releasing the extra energy as a particle of light. That released light can give each element a distinctive spectral fingerprint. Every element emits light at specific wavelengths when its electrons jump between orbitals, and those wavelengths are unique to that element. Scientists can look at the light from a distant star, see which wavelengths are present, and determine what elements the star contains, even from billions of light years away. The colours in neon signs come from atoms emitting specific wavelengths of light. When electricity flows through the gas inside a neon sign, it excites the electrons in the neon atoms. Those electrons jump to higher orbitals, then fall back down, releasing light. Neon gas glows a characteristic reddish-orange. Other gases glow different colours. Argon produces a soft blue, helium gives a pale yellow, and so on. Much of chemistry is the story of how atoms share or trade electrons. Chemical bonds form when atoms interact through their electrons. Sometimes atoms share electrons, creating a covalent bond. Sometimes one atom gives up an electron to another, creating an ionic bond. The details vary, but the principle is the same. Chemistry happens in the outer regions of atoms where electrons meet. The solidness of matter is a stable balance of attraction and repulsion. Objects feel solid because their atoms are held together by forces that keep them from collapsing inward or flying apart. The electrons repel other electrons, the nuclei attract the electrons, and all these forces balance out to create structures that hold their shape. Even while you rest, atoms are vibrating gently with thermal motion. Nothing is perfectly still. At the atomic level, there's always movement, a constant jiggling, a faint hum of energy. The warmer something is, the more vigorously its atoms vibrate. Just one more small fact, and then we drift further. A molecule forms when atoms bond together. Atoms rarely exist in isolation for long. They tend to link up, forming stable partnerships. Water is H2O, two hydrogen atoms bonded to one oxygen atom. It's one of the simplest and most important molecules, and it's everywhere. In your cells, in the oceans, in the air as vapor frozen in glaciers. Oxygen likes to form two bonds in many common molecules. The oxygen atom has a particular electron configuration that makes it stable when it shares electrons with two other atoms. In water, oxygen bonds with two hydrogen atoms. In carbon dioxide, oxygen bonds with a carbon atom that's also bonded to another oxygen. Carbon can form 4 bonds, which is one reason it supports complex life chemistry. Carbon's ability to bond with 4 other atoms at once allows it to create long chains, branching structures, rings, and intricate 3-dimensional shapes. This versatility is why organic chemistry, the chemistry of carbon-containing compounds, is so rich and varied. Your DNA, your proteins, your fats, your sugars, all of them are built on carbon backbones. Salt or sodium chloride isn't made of individual molecules in a crystal. It forms a repeating ionic lattice. When sodium and chlorine atoms come together, the sodium gives up an electron and the chlorine accepts it. The resulting charged ions, positive sodium and negative chlorine, attract each other strongly, and they arrange themselves in a regular repeating three-dimensional grid. Table salt crystals often look cube-like because their atoms arrange in a regular cubic pattern. If you examine a grain of salt under a microscope, you'll often see tiny geometric cubes, each one a reflection of the underlying atomic arrangement. Metals conduct electricity well because some electrons can move more freely through the structure. In a metal, atoms are packed together in a way that allows some of their electrons to drift from atom to atom, creating a kind of electron sea. When you apply a voltage across a metal wire, these free electrons flow, carrying electric current. Diamonds are carbon atoms bonded in a very rigid network, making diamond extremely hard. Every carbon atom in a diamond is bonded to 4 other carbon atoms in a tight three-dimensional lattice. This structure is incredibly strong, which is why diamond is one of the hardest natural materials. Graphite, which is also carbon, is soft because its atoms form layers that slide. In graphite, carbon atoms bond in flat sheets, and those sheets stack on top of each other like pages in a book. The bonds within each sheet are strong, but the sheets themselves can slip past one another easily. That's why graphite is used in pencils. When you write, layers of graphite peel off and stick to the paper. The same element can create different materials depending on bonding and structure. These are allotropes. Carbon can be diamond, graphite, or even buckyballs and nanotubes, depending on how its atoms are arranged. Glass is often an amorphous solid, meaning atoms are solidly packed but not in a neat repeating crystal. Unlike a salt crystal or a diamond, glass doesn't have a regular, orderly atomic structure. The atoms are locked in place, making it solid, but they're arranged somewhat randomly, like a frozen liquid. Ice is less dense than liquid water because its hydrogen bond structure creates extra open space. When water freezes, the water molecules arrange themselves in a crystal lattice that's more spread out than the loose jumble of molecules in liquid water. That's why ice floats. It's slightly less dense than the water beneath it. Your breath is a moving mix of molecules, mostly nitrogen and oxygen, each built from atoms. The air you inhale is about 78% nitrogen molecules, 21% oxygen molecules, and small amounts of other gases. Each breath is a quiet transaction. You bring in oxygen to fuel your cells, and you release carbon dioxide, a waste product of metabolism. Smells happen when airborne molecules bind to receptors, tiny molecular fits. When you smell fresh bread or cut grass or coffee, molecules from those sources drift through the air, enter your nose and lock onto receptor proteins. Each receptor is shaped to recognize certain molecular structures, and when a match occurs, your brain registers a scent. Taste is chemistry too. Atoms arranged into molecules that your body can recognize. Sweetness, bitterness, saltiness, sourness, umami, each of these. Sensations comes from molecules interacting with taste receptors on your tongue. A sugar molecule binds to a sweet receptor. A hydrogen ion binds to a sour receptor. The sensation of flavour is a kind of molecular conversation between the food and your sensory cells. Just one more small fact, and then we drift even further. Atoms of the same element can have different numbers of neutrons. These are isotopes. Remember, an element is defined by its number of protons, but the number of neutrons can vary. Carbon-12 and carbon-13 are both carbon, because both have 6 protons. Carbon-12 has 6 neutrons, and carbon-13 has 7. They behave almost identically in chemical reactions, but they have slightly different masses. Carbon-14 is a radioactive isotope used in radiocarbon dating. It has 6 protons and 8 neutrons, and it's unstable. Over time, it decays, changing into a different element. Radioactivity happens when an unstable nucleus changes to become more stable. Some combinations of protons and neutrons don't hold together well. The nucleus is a bit too heavy, or the balance isn't quite right, and it rearranges itself. This change can release particles or energy, like alpha particles, beta particles, or gamma rays. An alpha particle is a cluster of 2 protons and 2 neutrons. A beta particle is an electron or positron. A gamma ray is a high-energy photon. The time it takes for half of a radioactive sample to decay is called its half-life. Some half-lives are fractions of a second, others are billions of years. Carbon-14 has a half-life of about 5,130 years, which makes it useful for dating organic material that's thousands of years old. Potassium-40 is a naturally occurring isotope inside Earth that contributes to internal heat. Deep within the planet, radioactive isotopes like potassium-40, uranium-238, and thorium-232 decay slowly, releasing heat. That heat has kept Earth's interior molten and drives the movement of tectonic plates. Many smoke detectors use a tiny amount of americium-241 to help detect smoke particles. The americium emits alpha particles, which ionize the air in a small chamber. When smoke enters the chamber, it disrupts the ionization, and the detector sounds an alarm. The amount of radioactive material is very small and safely contained. Medical imaging and treatments sometimes use controlled radioactive isotopes under professional care. Technetium-99 melam is used in diagnostic scans. Iodine-131 can treat certain thyroid conditions. These isotopes are chosen because they emit the right kind of radiation at the right rate, and because the body handles them in predictable ways. A stable nucleus is like a quiet balance between forces holding it together and forces pushing it apart. Protons repel each other because they're all positively charged, but they're also held together by the strong nuclear force, which acts over very short distances. Neutrons act like nuclear glue in many atoms, helping the nucleus stay stable. They add mass and contribute to the strong force without adding more positive charge, which helps offset the repulsion between protons. Most atoms you encounter daily are stable and do not decay. The oxygen you breathe, the carbon in your body, the iron in a nail, all of these are stable isotopes. Even when atoms do decay, it's a natural process that happens throughout the universe. Radioactivity isn't something alien or unnatural. It's been part of the cosmos since the earliest moments of creation. Radioactive clocks help scientists estimate the ages of rocks, Earth, and even meteorites. By measuring the ratio of parent isotopes to daughter products, scientists can calculate how long the decay has been happening, and that tells them how old the rock is. Just one more small fact, and then we drift into a different kind of understanding. The periodic table organizes elements by increasing proton number. Start with hydrogen, which has one proton, and move across and down the table, adding one proton at a time. Helium has 2, lithium has 3, beryllium has 4, and so on. Elements in the same column often behave similarly, because they have similar outer electrons. The elements in the far right column, helium, neon, argon, krypton, xenon, radon, are all noble gases. They all have full outer electron shells, which makes them stable and mostly unreactive. The outermost electrons largely determine how an atom bonds. These are valence electrons. When chemists talk about how an atom will behave, they're usually talking about its valence electrons. The inner electrons are tightly held and don't participate much in chemical reactions. Noble gases, like helium and neon, are often unreactive because their outer electron shells are comfortable. They don't need to gain or lose electrons to achieve stability. They're already stable. Sodium is reactive because it tends to give up one outer electron easily. Sodium has one electron in its outermost shell, and it's energetically favourable for sodium to lose that electron and reveal a stable, full shell underneath. Chlorine tends to gain one electron, so sodium and chlorine fit together strongly as salt. Chlorine is one electron short of a full outer shell, and sodium has one electron it's eager to give up. When they meet, sodium donates its electron to chlorine, and both atoms achieve stable, full outer shells. The resulting charged ions attract each other and form sodium chloride, table salt. Helium is very light, which is one reason it can rise in balloons. Helium has only 2 protons and 2 neutrons, making it the second lightest element. It's lighter than the nitrogen and oxygen in air, so helium-filled balloons float upward. Hydrogen is the most abundant element in the universe. It's the simplest element, and it was the first to form after the Big Bang. The vast majority of atoms in the universe are hydrogen atoms. Stars are mostly hydrogen. The space between stars contains thin hydrogen, gas. Oxygen is abundant on Earth, especially because it bonds readily with many elements. Oxygen makes up a significant portion of Earth's crust. Combined with silicon in rocks, combined with hydrogen in water, combined with metals in ores. Iron is common because stellar processes make it a kind of energy endpoint in many stars. When a massive star fuses lighter elements into heavier ones, the process releases energy until it reaches iron. Fusing iron requires energy rather than releasing it, so iron tends to accumulate in the cores of massive stars. Gold appears gold-coloured because of how its electrons respond to light, including subtle relativistic effects. Gold's electrons move so fast and orbit so close to the nucleus that relativistic effects predicted by Einstein's theory of relativity, shift how the electrons absorb and reflect light. This shifts gold's colour toward the yellow end of the spectrum. Without these relativistic effects, gold would likely appear silvery, like most other metals. Copper's orange tone also comes from how its electrons absorb and reflect certain light. Copper absorbs blue and violet wavelengths and reflects red, orange and yellow, giving it that warm reddish hue. Many gemstones are the same base mineral with tiny atomic differences. Trace elements change colour. Corundum is aluminum oxide, and in its pure form it's colourless. Add a small amount of chromium and you get ruby with its deep red colour. Add titanium and iron and you get sapphire with its blue colour. The base structure is the same, but the trace elements alter how the crystal absorbs light. Small changes in atomic structure can produce huge differences in material properties. Move one element over on the periodic table, or rearrange how atoms bond, and you can go from a soft metal to a hard ceramic, from a conductor to an insulator, from transparent to opaque. Chemistry is the quiet art of electrons finding stable arrangements. All the complexity of the chemical world, all the reactions, all the colours, all the smells and tastes and textures, comes down to atoms seeking stability through the sharing or trading of electrons. It's a gentle dance, guided by the rules of quantum mechanics and electromagnetism playing out in every substance around you. Just one more small fact, and then we drift into deep time, into the stars. The earliest universe made mostly hydrogen and helium. In the first few minutes after the Big Bang, the universe was hot and dense enough for nuclear fusion to occur freely. Protons fused into helium nuclei, and small amounts of lithium formed as well. But the universe expanded and cooled quickly, and fusion stopped. For hundreds of millions of years, the universe was mostly hydrogen and helium gas, drifting in darkness. Stars are powered by nuclear fusion, light nuclei combining into heavier ones. Eventually, gravity pulled the hydrogen gas into clumps, and those clumps grew denser and hotter until fusion ignited in their cores. Hydrogen nuclei fused into helium, releasing energy in the process. That energy created pressure, which balanced the inward pull of gravity, and a star was born. Fusion in stars builds elements like carbon, oxygen, and neon over a star's life. When a star has fused much of its hydrogen into helium, it can begin fusing helium into carbon. Later, it might fuse carbon into oxygen, neon, and magnesium. The exact sequence depends on the star's mass. Massive stars can fuse elements in layers, like a slow onion of reactions. In the core, the heaviest fusion reactions are happening. In a shell around the core, lighter elements are fusing. In another shell, farther out, even lighter fusion occurs. The result is a star with a layered structure, each layer producing different elements. The heaviest elements, like gold, are associated with extreme cosmic events, such as certain supernova processes and neutron star mergers. When a massive star exhausts its fuel, it can collapse and explode in a supernova, releasing tremendous energy and creating conditions where very heavy elements can form. When two neutron stars spiral into each other and collide, the intense pressures and neutron-rich environment forge gold, platinum, uranium, and other heavy elements. When stars die, they can release elements into space. This is cosmic recycling. A supernova blasts the star's outer layers into space, seeding the surrounding region with newly forged elements. A less massive star might shed its outer layers more gently, creating a planetary nebula, and that material too enriches the interstellar medium. Nebulae are vast clouds of gas and dust where new stars and planets can form. These clouds contain the hydrogen and helium from the early universe, mixed with heavier elements created in earlier generations of stars. When a region of a nebula becomes dense enough, it can collapse under its own gravity and form a new star, and the process begins again. Planetary systems form from leftover material around young stars, shaped by gravity and time. As a star forms, it's surrounded by a disk of gas and dust. Over millions of years, that material clumps together. Dust grains stick, pebbles merge, rocks collide, and eventually planets form. The atoms in your body were once part of ancient stars, star stuff in the most literal sense. The carbon in your cells, the calcium in your bones, the iron in your blood, all of these elements were forged in stars that died before the sun was born. Earth's elements were assembled from earlier stellar material before the solar system formed. About 4.6 billion years ago, a cloud of gas and dust collapsed to form the sun and its planets. That cloud contained atoms from previous generations of stars, atoms that had been cycling through the galaxy for billions of years. Meteorites can carry very old minerals, atoms preserved from the solar system's early days. Some meteorites contain grains that predate the solar system itself, fragments of ancient stars embedded in the rock. Even in deep space, atoms can exist as thin gas, drifting for ages between stars. The space between stars isn't a perfect vacuum. It contains a few atoms per cubic centimetre, mostly hydrogen. These atoms drift slowly, pulled by gravity, pushed by starlight, waiting for the next time they'll be swept up into a star or planet. Some atoms travel inside cosmic dust grains, like tiny time capsules. Interstellar dust grains are microscopic particles, often silicates or carbon compounds, and they carry atoms from one part of the galaxy to another. Every breath you take mixes atoms that have been part of oceans, forests, and countless living things before. The nitrogen molecules you inhale may have once been in the soil, absorbed by plants, eaten by animals, returned to the soil, cycled through the atmosphere. The oxygen you breathe was likely produced by plants through photosynthesis, but before that, it may have been part of water, part of rock, part of the ancient atmosphere. In that sense, atoms are patient travellers, always changing partners, never truly leaving the universe. They move from star to nebula to planet to organism to atmosphere and back again, endlessly repurposed, endlessly recycled. Just one more small fact and then we drift back to the room, back to the present, back to the quiet. Right now, atoms in your body are constantly being rearranged through metabolism and repair. Your cells break down food molecules, releasing energy and building blocks. They use those building blocks to repair damage, to build new proteins, to replace worn-out structures. The atoms that make up you aren't fixed. They're in constant flux. Your skin slowly sheds atoms, and the environment gives you new ones through food, water, and air. Over time, the atoms in your body are gradually replaced. The you of today contains different atoms than the you of a year ago, yet you remain you. The water you drink contains hydrogen atoms that may be as old as the early universe. Those hydrogen atoms formed in the first few minutes after the Big Bang, and they've been cycling through the cosmos ever since. They've been in stars, in comets, in oceans, in clouds, in plants, in animals, and now they're in you. The air in your room is a moving sea of molecules bouncing gently in all directions. Nitrogen, oxygen, carbon dioxide, water vapor, all of them in constant random motion, colliding with each other and with the walls, the floor, your skin, creating the pressure we call air. The pillow beneath you is a structured weave of atoms holding its shape through countless bonds. The fabric is made of long polymer molecules woven together. The filling is a mass of fibres or foam, each fibre a tangle of atoms bonded in long chains. Even still objects are not perfectly still. Atoms vibrate and share energy quietly. The pillow isn't frozen in place at the atomic level, its atoms are jiggling, shifting slightly, vibrating with thermal energy. The warmer the room, the more vigorous the motion. Temperature is in part a measure of how energetically atoms and molecules are moving. When you feel warmth, you're sensing the kinetic energy of atoms. When something feels cold, its atoms are moving more slowly, and they draw energy from your skin, slowing your atoms down. Heat flows from warmer to cooler, from faster-moving atoms to slower-moving ones, always seeking equilibrium. Your breath is a steady rhythm of atoms trading places, oxygen in, carbon dioxide out. With each breath, oxygen molecules enter your lungs, cross into your bloodstream, and travel to your cells, where they're used to break down glucose and release energy. The waste product, carbon dioxide, travels back to your lungs and is exhaled. It's a quiet, constant exchange, happening without your conscious effort. Over billions of years, Atoms have arranged and rearranged into stars, oceans, mountains, and minds. The atoms around you have been part of the early universe, part of dying stars, part of the forming solar system, part of Earth's mantle, part of ancient oceans, part of early life, part of forests and animals and people. And now they're part of this moment, this room, this quiet night. And tonight, you don't have to manage any of it. Atoms will keep their calm work going while you simply rest. Just one more small fact, and then we drift, and you let the universe's smallest building blocks carry your thoughts away. The atoms in your body know what to do. They bond, they vibrate, they exchange energy. They follow the laws of physics and chemistry without hesitation, without error. They've been doing this work for billions of years, and they'll continue long after this night has passed. You can trust them. You can let your mind relax knowing that at the smallest scale, everything is proceeding as it should. The electrons are in their orbitals, the nuclei are stable, the bonds are holding, the molecules are doing their work, there's nothing you need to control, nothing you need to fix. The atoms are taking care of it all quietly, reliably, endlessly. And as you drift, you can imagine those tiny building blocks, those patient travellers, those ancient pieces of stardust, all working together to create this moment, this breath, this stillness. Just one more small fact, and then we drift, and you let the universe's smallest building blocks carry your thoughts away into the gentle dark, into the quiet, into rest. The atoms in your body know what to do. They bond, they vibrate, they exchange energy, they follow the laws of physics and chemistry without hesitation, without error. They've been doing this work for billions of years, and they'll continue long after this night has passed. You can trust them. You can let your mind relax, knowing that at the smallest scale, everything is proceeding as it should. The electrons are in their orbitals, the nuclei are stable, the bonds are holding, the molecules are doing their work, there's nothing you need to control, nothing you need to fix. The atoms are taking care of it all, quietly, reliably, endlessly. And as you drift, you can imagine those tiny building blocks, those patient travellers, those ancient pieces of stardust all working together to create this moment, this breath, this stillness. Just one more small fact, and then we drift, and you let the universe's smallest building blocks carry your thoughts away into the gentle dark, into the quiet, into rest. But before we settle completely, let's linger a little longer in this atomic world, because there's something deeply calming about understanding how reliably matter behaves, how predictable the rules are, how atoms have been following the same patterns since the beginning of time. Every atom in existence follows the same fundamental laws. A hydrogen atom in your body behaves exactly like a hydrogen atom in a distant galaxy. A carbon atom in your fingernail follows the same rules as a carbon atom in a meteorite. The universe has no exceptions, no special cases at this level. Everything is consistent, everything is orderly, and that orderliness extends across all of space and all of time. When atoms bond together, they do so according to very specific preferences. These preferences arise from the arrangement of electrons, from the shapes of orbitals, from the balance of attractive and repulsive forces. An oxygen atom bonds most comfortably with two hydrogen atoms because that arrangement allows all three atoms to achieve stable electron configurations. The angle between the two hydrogen atoms in a water molecule is about 104.5 degrees, and that angle is determined by the shape of oxygen's electron orbitals and the repulsion between the electron pairs. It's not random, it's not approximate. It's a consequence of quantum mechanics playing out in three-dimensional space, and every water molecule in every ocean, every raindrop, every ice crystal follows the same geometry. When water freezes, the molecules arrange themselves in a hexagonal pattern. Each oxygen atom is surrounded by four other water molecules in a roughly tetrahedral arrangement, and this creates a structure with more open space than liquid water. That's why ice is less dense than water, why it floats, why lakes freeze from the top down rather than the bottom up. This small fact, this consequence of hydrogen bonding and molecular geometry, has profound implications for life on Earth. If ice were denser than water, it would sink, and lakes and oceans would freeze solid from the bottom up during winter, likely killing most aquatic life. But ice floats, forming an insulating layer on the surface, and life continues beneath. The hydrogen bonds that hold water molecules together are weaker than the covalent bonds within each molecule, but they're strong enough to give water remarkable properties. Water has a high surface tension, allowing insects to walk on its surface. Water has a high specific heat, meaning it takes a lot of energy to change its temperature, which helps regulate Earth's climate. Water is an excellent solvent, dissolving salts and sugars and many other substances, which is essential for the chemistry of life. All of these properties emerge from the way water molecules interact with each other, from the distribution of charge across each molecule, from the hydrogen bonds forming and breaking and reforming in constant motion. In liquid water, each molecule is surrounded by others, all jostling and sliding past each other. The molecules are attracted to each other through hydrogen bonding, but they have enough thermal energy to move freely. They don't stay locked in one position. They drift, rotate, vibrate. At any given moment, a water molecule might be bonded to 3 or 4 neighbours, but those bonds break and form again with different neighbours billions of times per second. It's a dynamic equilibrium, a constant dance of attraction and release. When you heat water, you're adding energy to this system. The molecules move faster, vibrate more vigorously, and more hydrogen bonds break. Eventually, at 100 degrees Celsius under standard pressure, the molecules have enough energy to escape into the air as vapour. Boiling is simply the point where the thermal motion overcomes the hydrogen bonding, allowing molecules to break free from the liquid and enter the gas phase. When you cool water, you're removing energy. The molecules slow down, and more hydrogen bonds persist for longer periods. At 0 degrees Celsius, the molecules lock into the hexagonal ice structure, and the liquid becomes solid. Every phase transition, solid to liquid, liquid to gas and vice versa, is a manifestation of atoms and molecules finding a new equilibrium between their attractive forces and their thermal motion. These transitions happen at specific temperatures and pressures because the underlying physics is precise and repeatable. Water always freezes at 0 Celsius at sea level. It always boils at 100 Celsius. These aren't approximations. They're consequences of the fundamental properties of water molecules and the conditions they're experiencing. The same principles apply to every substance. Metals melt when their atoms gain enough thermal energy to break free from their rigid crystal lattice. Ice sublimates, turns directly from solid to gas when the conditions are right, which is why snow can disappear on a cold, dry day even when the temperature stays below freezing. Carbon dioxide doesn't have a liquid phase at normal atmospheric pressure. It goes directly from solid dry ice to carbon dioxide gas, which is why dry ice smokes when you leave it out. Each substance has its own set of phase transitions, determined by the strength of the bonds between its atoms or molecules and the energy available to break those bonds. Inside your body right now, phase transitions are happening continuously, though you don't notice them. Water evaporates from your skin, carrying away heat and cooling you down. Water condenses in your lungs when you exhale warm, moist air into cooler surroundings. You can see your breath on a cold day because the water vapour is condensing into tiny droplets. Lipids in your cell membranes exist in a carefully controlled semi-fluid state, neither completely solid nor completely liquid, allowing them to form barriers while still permitting movement and flexibility. Your body maintains all of these states through careful regulation of temperature and chemical environment. At the molecular level, your cells are busy managing thousands of chemical reactions simultaneously. Enzymes, protein molecules with precisely shaped active sites, bring reactants together and lower the energy needed for reactions to occur. A substrate molecule fits into an enzyme's active site like a key into a lock, though the fit is dynamic rather than rigid. The enzyme holds the substrate in place, puts stress on certain bonds, and facilitates the breaking or forming of those bonds. When the reaction is complete, the product is released and the enzyme is ready to work again. A single enzyme molecule can catalyze thousands of reactions per second, and your cells contain thousands of different enzymes, each specialized for a particular reaction. The DNA in your cells is a long, twisted ladder of atoms, a double helix held together by hydrogen bonds between complementary base pairs. Adenine always pairs with thymine, and guanine always pairs with cytosine, because those are the combinations where the shapes fit and the hydrogen bonds align correctly. This pairing is so reliable that it allows DNA to be copied with extraordinary accuracy. When a cell divides, enzymes unzip the double helix, and other enzymes build new complementary strands, creating 2 identical DNA molecules from one. Mistakes happen, mutations occur, but they're rare, thanks to the precision of molecular interactions and the proofreading mechanisms cells have evolved. The information in DNA is written in sequences of bases, and those sequences are translated into proteins through an intricate process involving RNA and ribosomes. 3 bases in a row code for one amino acid, and a string of amino acids folds into a protein. The protein's shape is determined by the sequence of amino acids and by how those amino acids interact with each other and with the surrounding water. Hydrogen bonds, ionic interactions, hydrophobic effects, all of these forces guide the protein into its final 3-dimensional structure, and that structure determines what the protein does. A protein that's folded correctly can function as an enzyme, a structural component, a signal receptor, a molecular motor. A protein that's folded incorrectly might do nothing, or it might cause problems, which is why cells have quality control systems to refold or destroy misfolded proteins. Every biological process, from muscle contraction to nerve signaling to photosynthesis, comes down to atoms and molecules interacting in specific ways. When you move your hand, you're using proteins called actin and myosin, which slide past each other in a ratcheting motion powered by ATP, adenosine triphosphate, a molecule that stores energy in its chemical bonds. When a nerve signal travels down a neuron, it's because ions, sodium and potassium, are flowing across the cell membrane through protein channels, creating an electrical pulse. When a plant captures sunlight, chlorophyll molecules absorb photons, exciting electrons that then move through a chain of proteins, ultimately driving the synthesis of sugar from carbon dioxide and water. All of this complexity, all of this function, emerges from atoms obeying simple rules. Electrons seek stable configurations. Positive and negative charges attract. Like charges repel, energy flows from high concentration to low, entropy tends to increase. These principles, applied consistently across trillions of atoms, generate the rich tapestry of chemistry and biology that makes life possible. And it's all happening right now, in your body, as you rest. Your heart is beating because calcium ions are flooding into muscle cells, triggering contraction. Your lungs are exchanging gases because oxygen and carbon dioxide diffuse across thin membranes, following concentration gradients. Your neurons are maintaining their resting potential, ready to fire if needed, by actively pumping sodium out and potassium in. Your digestive system is breaking down food molecules, cleaving bonds and rearranging atoms to extract energy and building blocks. Your cells are synthesizing new proteins, repairing DNA, processing waste, communicating with each other through chemical signals. None of this requires your conscious attention. The atoms know what to do, the molecules know where to go. The reactions proceed at the rates, determined by temperature, concentration, and the presence of catalysts. It's all automatic, all reliable, all governed by the same laws that have governed matter since the universe began. Outside your body and the room around you, atoms are behaving just as predictably. The air molecules are bouncing off each other and off every surface in a chaotic but statistically orderly way. The average speed of a nitrogen molecule at room temperature is about 500 meters per second, though any individual molecule is constantly speeding up and slowing down as it collides with others. The pressure you feel from the air is the cumulative result of countless molecular collisions, molecules striking your skin, the walls, the furniture, transferring tiny amounts of momentum with each impact. The air is mostly nitrogen, about 78% by volume, because nitrogen is relatively unreactive and stable as a diatomic molecule. 2 nitrogen atoms triple bonded to each other. That triple bond is very strong, which is why nitrogen doesn't readily participate in reactions at normal temperatures and pressures. It takes significant energy to break that bond, which is why industrial nitrogen fixation, the process of converting nitrogen gas into ammonia for fertilizer, requires high temperatures and pressures and a catalyst. Yet certain bacteria can fix nitrogen at room temperature using specialized enzymes, a reminder that biological systems can achieve remarkable feats of chemistry through precise molecular machinery. Oxygen makes up about 21% of the air. Like nitrogen, oxygen exists mostly as diatomic molecules, though oxygen's double bond is weaker than nitrogen's triple bond, making oxygen more reactive. Oxygen is essential for aerobic life because it's an excellent electron acceptor. When your cells break down glucose, they strip electrons from the glucose molecule and pass them through a series of proteins, ultimately transferring them to oxygen, which combines with hydrogen ions to form water. This process releases energy that your cells capture and use to make ATP. Without oxygen, Most complex multicellular life as we know it couldn't exist, because the energy yield from anaerobic metabolism is much lower. The remaining 1% of the air is a mix of argon, carbon dioxide, neon, helium, methane, and trace amounts of other gases. Argon is a noble gas, chemically inert, and it accumulates in the atmosphere because it's produced by the radioactive decay of potassium-40 in Earth's crust. Carbon dioxide, though only about 0.04% of the atmosphere, plays a crucial role in Earth's climate and in the global carbon cycle. Plants absorb carbon dioxide during photosynthesis, animals and decomposers release it during respiration, oceans dissolve it, volcanoes emit it, and the concentration has been rising due to human activities, particularly the burning of fossil fuels. Carbon dioxide is a simple molecule, one carbon atom double bonded to two oxygen atoms, arranged in a straight line. But it has significant effects on how Earth absorbs and emits radiation. Carbon dioxide is transparent to visible light, so sunlight passes through the atmosphere and warms the surface. But carbon dioxide absorbs infrared radiation, heat, that Earth emits back towards space. The molecules' bonds can vibrate in ways that resonate with infrared wavelengths, absorbing that energy and re-emitting it in random directions, including back toward the surface. This is the greenhouse effect, and it's a natural and necessary process that keeps Earth warm enough for liquid water and life. Without any greenhouse gases, Earth's average temperature would be well below freezing. The concern with rising carbon dioxide levels isn't the greenhouse effect itself, it's the rapid increase in that effect, which is shifting Earth's climate faster than many ecosystems can adapt. Water vapour is also a greenhouse gas, and it plays an even larger role in Earth's heat balance than carbon dioxide, though its concentration varies greatly depending on location and weather. Warm air can hold more water vapour than cold air, which is why tropical regions are humid and polar regions are dry. When water vapour condenses into clouds, it releases latent heat, the energy that was used to evaporate the water in the first place, and that heat affects weather patterns and atmospheric circulation. Clouds themselves have complex effects on climate. They reflect sunlight, cooling the surface, but they also trap heat, warming it. The net effect depends on the type, altitude, and coverage of the clouds. The atmosphere is a dynamic system, constantly mixing and moving, driven by differences in temperature and pressure. Warm air rises because it's less dense than cooler air, creating convection currents. The Earth's rotation deflects these currents, creating wind patterns and weather systems. The molecules in the air are all moving individually, yet collectively they create the wind you feel, the weather you experience, the climate that shapes the planet. On a calm night, the air in your room is relatively still on a macroscopic scale, but at the molecular level, it's as active as ever. The molecules are zipping around, colliding, transferring energy, maintaining equilibrium. The temperature in the room is the same everywhere, or nearly so, because the air molecules have distributed thermal energy evenly. If you open a window on a cold night, cool air flows in, not because cold is a substance that spreads, but because the faster-moving molecules in the warm room lose energy to the slower-moving molecules from outside, and the average energy, the temperature, equalizes. The walls of the room are solid and their atoms are vibrating in place, held by chemical bonds. The materials, drywall, wood, concrete, whatever they are, each have their own atomic structure. Drywall is mostly calcium sulfate, a compound where calcium ions and sulfate ions are held together by ionic bonds. Wood is a complex mixture of cellulose, hemicellulose, and lignin, all organic polymers made from carbon, hydrogen, and oxygen. Concrete is a mixture of cement, water, sand, and gravel, and the cement itself is a calcium silicate compound that undergoes a chemical reaction with water, hardening into a solid matrix. Every material has a thermal conductivity, a measure of how easily heat flows through it. Metals have high thermal conductivity because their free electrons can carry energy quickly from one part of the material to another. Wood and plastic have lower thermal conductivity because they lack free electrons, and heat must travel through vibrations of the atomic lattice, which is slower. Air has very low thermal conductivity, which is why insulation works. Materials like fiberglass or foam trap pockets of air, preventing heat from flowing freely. The floor beneath you, whether carpet or wood or tile, is a surface made of countless atoms bonded together. Carpet is made of synthetic or natural fibers, each fibre a polymer, a long-chain molecule. The fibres are woven or tufted into a backing, creating a soft surface. Wool, a natural fibre, is made of keratin, the same protein found in hair and fingernails. Synthetic fibres like nylon and polyester are petroleum-based polymers created through chemical reactions that link small molecules into long chains. Tile might be ceramic, made from clay that's been shaped and fired at high temperatures, causing the atoms to lock into a hard, durable structure. The objects around you, furniture, books, electronics, are all assemblages of atoms arranged in specific ways. A book is paper, ink, and glue. Paper is cellulose fibres pressed together, derived from wood pulp. Ink is a suspension of pigment particles in a liquid or binder. The pigments are molecules that absorb certain wavelengths of light and reflect others, giving the ink its colour. Black ink absorbs nearly all wavelengths, reflecting very little, which is why it appears black. Coloured inks contain pigments with more selective absorption. Blue ink absorbs red and green wavelengths and reflects blue. A smartphone or laptop is a marvel of atomic engineering. The screen is glass made from silicon dioxide and other oxides, heated until molten and then cooled into a transparent amorphous solid. The display itself might be an LCD or OLED, both of which manipulate light at the molecular level. In an LCD, liquid crystals, molecules that flow like a liquid but have an ordered structure like a crystal, are sandwiched between polarizing filters. When an electric field is applied, the liquid crystals rotate, changing how much light passes through. In an OLED, organic molecules emit light when electrons and holes recombine within them, a process similar to what happens in LEDs, but using carbon-based compounds instead of inorganic semiconductors. The processor inside the device is made from silicon, doped with tiny amounts of other elements to control how electrons flow. Silicon is a semiconductor. It's not a good conductor like copper, but it's not an insulator like glass either. By carefully controlling the arrangement of atoms and introducing impurities, engineers can create transistors, diodes, and other components that control electric current. A modern processor contains billions of transistors, each one a tiny switch made from precisely arranged atoms, all working together to perform calculations. The battery is a chemical system where atoms exchange electrons through oxidation and reduction reactions. In a lithium-ion battery, lithium ions move from one electrode to the other through an electrolyte, and electrons flow through an external circuit providing power. When you charge the battery, you reverse the process, using electrical energy to drive the ions back to their original positions. The battery works because lithium atoms have a strong tendency to lose an electron, and the other electrode material has a strong tendency to gain electrons, creating a voltage difference. All of this technology, all of this function, comes from understanding how atoms behave and arranging them in useful ways. It's applied chemistry, applied physics, applied materials science, and it all rests on the same fundamental principles. Electrons seek stability, atoms bond in specific geometries, energy flows from high to low, and reactions proceed toward equilibrium. The light from a lamp or screen comes from atoms emitting photons. In an incandescent bulb, a tungsten filament is heated until it glows. The atoms vibrate so vigorously that they emit light across a broad spectrum. In an LED, electrons recombine in a semiconductor, and the energy is released as photons of a specific wavelength determined by the materials used. In a fluorescent tube, electricity excites mercury atoms, which emit ultraviolet light, and that ultraviolet light strikes a phosphor coating, causing it to fluoresce, emit visible light. Each method is a different way of persuading atoms to release energy as light, and each relies on understanding atomic and molecular behaviour. When light hits your eye, it's absorbed by molecules in your retina called opsins. These molecules contain a chromophore, a light-sensitive part, that changes shape when it absorbs a photon. That shape change triggers a cascade of chemical reactions, ultimately producing an electrical signal that travels to your brain. Vision is chemistry and physics working together. Photons, molecules, ions, and electrical impulses, all coordinated to give you the experience of sight. Sound, too, is atoms in motion. When something vibrates, a guitar string, a speaker cone, your vocal cords, it pushes and pulls on the air molecules around it, creating regions of higher and lower pressure that travel outward as a wave. Your eardrum vibrates in response to these pressure changes, and tiny bones in your middle ear amplify the vibration and transmit it to the fluid-filled cochlea. There, Hair cells detect the motion and convert it into electrical signals. Hearing is the perception of molecules in motion, translated into neural activity. Smell, as mentioned earlier, is molecules binding to receptors. Taste is molecules binding to different receptors on your tongue. Touch is mostly the deformation of cells in your skin, which opens ion channels and generates electrical signals. Every sense you have is, at its root, a molecular event, atoms and molecules interacting in specific ways, triggering responses that your brain interprets as sensations. Your brain itself is an incredibly complex network of neurons, each one a cell filled with molecules carrying out reactions. Thoughts, memories, emotions, all of these emerge from patterns of electrical and chemical activity in the brain. When you remember something, it's because certain synapses, connections between neurons, have been strengthened through repeated use, making it easier for signals to travel along those pathways. When you learn something new, your brain is literally rewiring itself, forming new synaptic connections and reinforcing others. The molecules involved include neurotransmitters like dopamine, serotonin and glutamate, which carry signals across synapses and receptors that bind those neurotransmitters and trigger responses in the receiving neuron. The fact that consciousness emerges from atoms following physical laws is one of the great mysteries, but it's not in doubt that it does. The atoms in your brain are the same atoms found everywhere else: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and traces of others. There's nothing special about them individually. What's special is how they're arranged, how they interact, the patterns they form. Complexity builds on complexity, from atoms to molecules to cells to tissues to organs to systems, until you have a brain that can think about atoms. And tonight, as you rest, your brain is still active, even if you're not consciously thinking. It's consolidating memories, processing the day's experiences, maintaining basic functions like breathing and heart rate. It's doing all of this through chemistry, through ions flowing, neurotransmitters binding, proteins changing shape, genes being expressed or suppressed. It's all atoms, all the way down, following the rules, doing the work. The carbon in your body, the carbon that forms the backbone of every organic molecule in your cells, came from ancient stars. Carbon is created in stars through a process called the triple alpha process. 3 helium nuclei, each containing 2 protons and 2 neutrons, collide and fuse to form a carbon nucleus with 6 protons and 6 neutrons. This process requires very specific conditions, a certain temperature, a certain density, and it was only discovered after astronomers realized there was a puzzle. Carbon is abundant in the universe, but the conditions for making it seemed too narrow. The solution came when physicist Fred Hoyle predicted that carbon must have an energy level that makes the reaction much more likely, and experiments confirmed he was right. Without that particular energy level, carbon would be rare, and life as we know it probably wouldn't exist. Oxygen, the second most important element for life on Earth, is created when carbon fuses with another helium nucleus. Neon comes from oxygen fusing with helium. The process continues, building heavier and heavier elements as long as the star is massive enough and hot enough. Each fusion reaction releases energy, and that energy creates the pressure that keeps the star from collapsing under its own gravity. But fusion only releases energy up to iron. When you fuse lighter elements into iron, you get energy out. When you try to fuse iron into heavier elements, you have to put energy in. That's because iron has the most stable nucleus. It has the lowest energy per nucleon of any element. This means that a massive star, once it builds up an iron core, is in trouble. The core can no longer produce energy through fusion, so it can no longer support itself against gravity. The core collapses in a fraction of a second, and the outer layers crash down onto it. The result is a supernova, a catastrophic explosion that outshines entire galaxies for a brief time. In the intense heat and pressure of a supernova, elements heavier than iron can be created. Neutrons flood the collapsing core and they can be captured by nuclei, building up heavier and heavier elements. This is called the R process, the rapid neutron capture process, and it's responsible for about half of the elements heavier than iron. The other half are created through the S process, the slow neutron capture process, which happens in certain types of stars over long periods of time. Recently, astronomers detected gravitational waves from the collision of 2 neutron stars, and they also observed the electromagnetic radiation from the event. Analysis of that radiation revealed the signatures of heavy elements being created: gold, platinum, uranium. It was the first direct observation of heavy element formation in a neutron star merger, confirming what had been theorized for decades. Those collisions are rare, but over the billions of years of cosmic history, they've seeded the universe with enough heavy elements to make planets and people. The gold in a ring, the uranium in a nuclear reactor, the lead in a car battery, all of these atoms were created in the death throes of stars or in the violent collisions of stellar remnants. They've travelled through space, mixed with gas clouds, been incorporated into new stars and planets, and eventually ended up here, on Earth, in your environment, sometimes even in your body. Earth itself is a ball of atoms sorted by density. The densest materials, mostly iron and nickel, sank to the centre early in Earth's history when the planet was molten from the heat of formation and radioactive decay. The lighter materials, silicates, mostly compounds of silicon and oxygen, floated to the top, forming the mantle and crust. This differentiation happened over millions of years, driven by gravity and heat, and it gave Earth its layered structure: a solid inner core, a liquid outer core, a solid mantle, and a thin crust. The inner core is under such immense pressure that iron, which would normally melt at the core's temperature, is forced to remain solid. The outer core is liquid, and its motion generates Earth's magnetic field through a process called the geodynamo. Charged particles, ions of iron and other elements, flow through the liquid core, and because Earth is rotating, these flows create electric currents, and electric currents generate magnetic fields. The details are complex, but the result is a magnetic field that extends far into space, protecting Earth from the solar wind, the stream of charged particles, flowing from the sun. The mantle is solid but not rigid. Over long timescales, it flows like a very thick fluid, driven by heat from the core and from radioactive decay within the mantle itself. This flow causes tectonic plates to move, which leads to earthquakes, volcanic eruptions, and the slow drift of continents. The atoms in the mantle are mostly silicon, oxygen, magnesium, and iron, arranged in crystal structures that can deform and flow under the right conditions of temperature and pressure. The crust is the thin outermost layer, the solid skin of the planet, and it's where we live. Continental crust is mostly granite and similar rocks, rich in silicon and aluminum. Oceanic crust is mostly basalt, denser and richer in iron and magnesium. The rocks of the crust are made of minerals, and minerals are crystalline solids with specific chemical compositions. Quartz is silicon dioxide. Feldspar is a group of aluminum silicates. Mica is a layered silicate. Each mineral has each characteristic crystal structure determined by the arrangement of its atoms. When molten rock cools, atoms arrange themselves into crystals, and the size of those crystals depends on how quickly the rock cools. Slow cooling allows large crystals to form. Granite, which cools deep underground, has visible crystals of quartz, feldspar, and mica. Rapid cooling produces small crystals or even glass. Obsidian, which forms when lava cools very quickly, is volcanic glass, an amorphous solid with no crystal structure at all. Erosion breaks rocks down into smaller particles: sand, silt, clay. These particles are carried by water and wind and deposited in layers. Over time, the layers compact and cement together, forming sedimentary rocks like sandstone, shale, and limestone. Limestone is mostly calcium carbonate, often formed from the shells and skeletons of marine organisms. When those organisms die, their calcium carbonate structures accumulate on the seafloor, and over millions of years they lithify into rock. If sedimentary or igneous rocks are subjected to high temperature and pressure, through burial or tectonic forces, they can transform into metamorphic rocks. The atoms rearrange into new mineral structures without melting. Shale becomes slate, then schist, then gneiss, as the temperature and pressure increase. Limestone becomes marble, sandstone becomes quartzite. The rock cycle, igneous to sedimentary to metamorphic and back to igneous, is a slow churning of atoms, driven by Earth's internal heat and the movement of tectonic plates. The soil beneath your feet is a mixture of mineral particles, organic matter, water, air, and countless living organisms. The mineral particles come from weathered rock. The organic matter comes from decaying plants and animals. Bacteria, fungi, insects, and other organisms break down organic matter, recycling nutrients and making them available to plants. Plant roots absorb water and dissolved nutrients, nitrogen, phosphorus, potassium, and many others, and use them to build tissues. When the plant dies, the atoms return to the soil, ready to be used again. This cycling of atoms through ecosystems is continuous. Carbon cycles through photosynthesis and respiration. Nitrogen cycles through fixation, assimilation, and denitrification. Water cycles through evaporation, precipitation, and runoff. Every atom in your body has been cycled through ecosystems countless times. The nitrogen in your proteins may have been in the air, then in the soil, then in a plant, then in an animal, then back to the soil, many times over. The water in your cells has been in oceans, clouds, rivers, plants, animals, and back again, endlessly. Life is not separate from the environment. It's part of the same cycling of matter, the same flow of energy. The atoms that make up your body are borrowed from the environment, and they'll return to it. You're a temporary arrangement, a pattern that matter has taken for a while. The atoms themselves are ancient and will persist long after the pattern that is you has dissolved. But that's not a sad thought. It's a connecting thought. You're part of a continuity that stretches back to the beginning of the universe and forward into the indefinite future. The atoms in your body have been part of stars, part of interstellar clouds, part of the early Earth, part of ancient oceans, part of the first life, part of dinosaurs and forests and countless other organisms. And after you, they'll be part of other things: soil, air, water, new organisms, perhaps even new stars if Earth's atoms are ever scattered back into space. For now, though, those atoms are you. They're arranged in a specific, intricate pattern that thinks and feels and experiences the world. They're maintaining that pattern through constant work, metabolism, repair, signalling, movement. And they'll keep doing that work as long as you're alive, following the same rules they've always followed. The same rules that govern all matter everywhere. As you lie here tonight, you can trust those atoms to continue their work. You don't need to direct them. You don't need to worry about them. They've been doing this for billions of years, and they're very good at it. The electrons will keep orbiting. The bonds will keep holding. The reactions will keep proceeding. The energy will keep flowing. And you can simply rest, carried by the reliable, quiet work of the universe's smallest building blocks. The darkness around you is not truly dark. If you could see infrared light, you'd see the glow of thermal radiation from every object in the room, the walls, the furniture, your own body. Everything above absolute zero emits electromagnetic radiation, and the wavelength of that radiation depends on the temperature. At room temperature, objects emit mostly in the infrared. Hotter objects, like the filament in an incandescent bulb, emit visible light. Even hotter objects like the sun emit across a wide spectrum, including ultraviolet. The atoms in any object are always vibrating, always moving, and charged particles in motion emit electromagnetic radiation. The silence around you is not truly silent. There are always sounds: the hum of electronics, the settling of the building, the distant sound of traffic or wind, the rhythm of your own breathing and heartbeat. Sound is vibration, and vibration is atoms in motion, pushing on neighbouring atoms, creating waves of compression and rarefaction that travel through matter. Sound can't travel through a vacuum because there are no atoms to vibrate, which is why space is silent. But here, surrounded by air and solid objects, sound is always present at some level. Even your thoughts right now are atoms in motion. Neurons firing, neurotransmitters binding, ions flowing, all physical processes, all governed by the same laws that govern everything else. There's no separate realm for thoughts. They're part of the physical world, patterns of activity in a physical brain made of atoms. That doesn't diminish them. If anything, it makes them more remarkable. The fact that atoms can arrange themselves into a structure capable of thinking about atoms, capable of understanding the universe, capable of experiencing wonder and curiosity and love, that's astonishing. You are made of star stuff, arranged in a way that can contemplate star stuff. You are the universe experiencing itself, a local concentration of complexity in an otherwise simple cosmos. And tonight, you can let that universe continue its work while you rest. The atoms will keep their vigil, the molecules will keep their functions, the cells will keep their metabolism, the organs will keep their rhythms, all of it automatic, all of it reliable, all of it grounded in physical law. Just one more small fact, and then we drift completely. The hydrogen atoms in your body, the most common atoms in your cells, present in water, in proteins, in every organic molecule. Those hydrogen atoms are the oldest matter in your body. They were created in the Big Bang, in the first few minutes of the universe's existence. They've been cycling through the cosmos for nearly 14 billion years. They've been in stars, in planets, in living things, in oceans and atmospheres and ice. And now they're in you, part of your structure, part of your function, part of this moment. And in this moment you can rest. You can let go of the need to understand everything, to control everything, to manage everything. The atoms know what to do. They've always known. They've been following the same rules since time began, and they'll continue following those rules without any effort from you. You can trust the process. You can trust the physics. You can trust the chemistry. You can trust the quiet, patient work of matter, doing what matter does, bonding, vibrating, reacting, flowing, maintaining the patterns that allow you to exist. Just one more small fact, and then we drift. And you let the universe's smallest building blocks carry your thoughts away into the gentle dark, into the quiet, into the deep rest that comes from knowing that everything, at the smallest scale, is exactly as it should be and will continue to be, long after this night has passed into memory, and then into the endless recycling of atoms through time and space. The next story is about to begin. Please relax and enjoy.